Hey guys, welcome back. It's lesson 1 of Physics 468. That's atomic and nuclear physics, basically the second semester of quantum mechanics. I want to take a moment to just give a brief overview of the course. We're going to start out looking at what happens when we have more than one particle in the system. That means we have to look into the difference between distinguishable particles and indistinguishable particles and various symmetry effects that those differences make. We're going to talk about perturbation theory, both time-independent perturbation theory and then time-dependent perturbation theory, so we can deal with things like time-dependent interactions and so on that might occur in a system. We'll discuss the variational principle and different techniques for estimating ground state energies and ground state wave functions. And in particular, we're going to do a lot of work with Monte Carlo techniques. And in fact, we'll spend a fair amount of time dealing with Monte Carlo simulations of various kinds and computations and learning how to use those techniques to make different kinds of estimates. And finally, we're going to round out the semester with nuclear and particle physics, a little bit of standard model, a little bit of nuclear theory, and apply many of the techniques we've developed through the course of the semester to those topics. So that's the overview of the entire course. Now, the other thing I'd like to point out is that we've got a fair amount of flexibility here to do things that you're interested in. So I'm going to be asking you, when I get back from my trip, to articulate some thoughts on what you're interested in studying of all the topics, atomic, molecular, nuclear, particle physics, which topics are most interesting to you, and I'll see if we can incorporate as many of those ideas as possible into the course. So, what happens when you have multiple particles? Well, if you have identical particles come in two flavors. There are bosons and there are fermions. The difference between bosons and fermions is that when you swap two bosons in a system, that the wave function is the same as it was before the swap. But if you swap two fermions, two identical fermions in a quantum system, the wave function gets a phase of -1, or a phase of pi, you could say. You multiply by e to the I pi, which is -1, so the wave function has to change sign. And this has dramatic consequences in terms of the behavior of particles that are fermions and particles that are bosons in how they interact with each other and how you build up a quantum system out of those particles. So we'll see how that goes here in a little bit. Bosons are social. They like to get together. Fermions are antisocial. So one of the consequences of the symmetry requirement is that you can't put two fermions in exactly the same quantum state. They're loners. They only allow one fermion in a particular quantum state of the whole system. And so what that means is they tend to avoid one another. Okay? So we'll see how that comes out soon. So I want you to imagine we have an infinite square well. We're going to do the infinite square well again, but this time we're going to put particles into the infinite square well that are either bosons or fermions. And what we're going to discover is that, first of all, if you have distinguishable particles in an infinite square well, and the particles don't interact with each other, so there's no potential associated with the particle being near another particle. So these are non-interacting, distinguishable particles. Then you can get a wave function for the pair of them as simply the product of the wave functions of the individual particles. This is in the case that they're distinguishable. But if they're indistinguishable, then you have two different wave functions. One is the bosonic wave function, where you have to write the wave function out with particle 1 in state n1 and particle 2 in state n2, and then write it out again, add to that another term that enforces the symmetry requirement that if you swap the two particles, you get the same wave function. So notice that the second term in this sum has n2 for particle 1 and n1 for particle 2. And the consequence of that is if you swap x1 and x2, the first term becomes the second term and the second term becomes the first term, but the overall wave function doesn't change. So this would be a bosonic or symmetric form of a infinite square well wave function. And if you have fermions, you've got to cook it up in such a way that when you swap x1 and x2, in other words, you swap the positions of the two particles in the wave function, you get the same wave function back but with a minus sign. So notice that the second term here has a minus sign, and that enforces the anti-symmetry requirement that fermions have to satisfy. So what happens to a fermion state if n1 is equal to n2? I'll let you think about that. Look at that expression, see if you can't figure it out. Maybe we can talk about it in class. All right, I want to take a minute now to show you the demo for the first computing project, which is a lot like computing project 8 from last semester, the two-dimensional infinite square well, except now it's a one-dimensional infinite square well with two particles. But you'll find that much of the code that you developed for project 8 last semester will immediately work for this project this semester because the two problems are actually quite similar. Alright, so here we are looking at the code for computing project 1. This is very similar to computing project 8. You'll notice in the handout I make a lot of references to computing project 8, and so basically 90% of the code is identical. The things that have changed are that now instead of using x and y, we're using x1 and x2, because in this project we're talking about a one-dimensional infinite square well in space, but with two distinguishable particles, or two indistinguishable particles in it, depending on how you set the initial conditions. The way the program works is if you want to use bosons, you set bosons to 1 and fermions to 0, like that. If you want to use fermions, you set fermions to 1 and bosons to 0. And if you want to use distinguishable particles, you set them both to 0. That's the plan. Let me just show you here. Let's just go ahead and use distinguishable particles to see how it works. The other thing is there's two sets of initial conditions here that I've pre-set up for you. This set that I just uncommented has the probability of being between 0 and half of A, half of the well width, equal to a constant for both particles. So both particles are equally likely to be found anywhere between 0 and A over 2 at the beginning. Now you're going to discover that that actually doesn't work very well for fermions because you'd be trying to put both fermions in the same state. So there's another initial condition here that you can use for fermions where particle 1 is between 0 and A over 4 and particle 2 is between A over 4 and A over 2. And that actually works better for fermions. And you can see that you can do that for bosons as well, but I wanted to start out simple. Anyway, the project is almost exactly identical. There's one other big difference. When you create the basis states, the basis states are different for fermions, bosons, and distinguishable particles. It's all described in the handout, but you should notice the major difference here is that the fermionic and bosonic basis states are symmetrized when they're constructed. So they're automatically constructed to have the correct symmetry properties for fermions, bosons, and in this case distinguishable particles have no particular symmetry, so you can just write those out as the product of particle 1 in state 1 and particle 2 in state 2. And energies are calculated in exactly the same way, and the one part I haven't given you in the starter code that I give you is the time evolution, but of course time evolution works exactly the same way as it did for last semester, so nothing terribly profound there. Let's go ahead and run the program and you can see how it goes. Basically, let's see, why didn't that? Oh, there we go. Okay. So we get a graph, we get a 3D view. So remember the idea here is that this direction is particle 1 coordinate, this direction is particle 2's coordinate, x coordinate, and you can see that the uniform probability density of being in the lower left hand corner. If I turn on the time, you'll see that the wave function evolves in time. I want to remind you the way these cylinders work. These cylinders show a complex amplitude at every point point in space at different times, the height of the cylinder is the real part. Notice that the height can become negative, so you can have a negative real part. And the radius of the cylinder is the imaginary part, but the imaginary part could be negative, and it's hard to see a negative radius, so what we do is we switch the color. If the imaginary part is positive, it's red. If the imaginary part is negative, it's blue. So you can see the imaginary part, the real part, and you can see that this thing evolves in time. Where the cylinders are big, there's a big probability of finding the particle. Where the cylinders are small, there's a small probability, and so on. And you'll recognize this graph from, this is sort of looks like the graph we had on the slide before we went to the demo. Anyway, that's kind of how it works. You can fiddle with the initial conditions set up in the program, change the particles to bosons, to fermions, and change the initial wave function by uncommenting or commenting these two lines. And while the code is very similar to Project 8, and I expect you guys all did Project 8 or maybe remember Project 8, if you have any questions about the code, please don't hesitate to consult with me, because I want to make sure you guys understand how it all goes. And that's it. Okay, I just remembered there's one other thing I must show you quickly. I'm going to go down and set the initial conditions up so that fermions can work. I'm going to change the particle type to bosons and just very briefly point out that when I run this thing, this is the boson case. You can see that there's no restriction on having bosons right next to each other. Notice that if you look at the thing, this diagonal here is x1 equals x2, and there's lots of amplitude for x1 and x2 to be equal to each other, which means the bosons can be right up next to each other. If I change this to fermions, on the other hand, and run it, now we have an antisymmetric state, and I want you to notice that there's kind of an exclusion zone there. x1 can never equal x2, and that's because the basis states for the fermions are explicitly antisymmetric, and that means they have a zero there along the middle, and so the fermions can never see each other, and that has significant implications. Anyway, I just wanted to show you that quickly. Okay, so I want to point out, you see these graphs I have here on this page, and I didn't explain what they are. These are the graphs of the probability of finding both particles in the left half of the infinite square well in the three cases that the two particles are distinguishable, that they're bosons, and that they're fermions. And you'll notice that there's sort of qualitative similarity here between the three cases. But I want to emphasize that the details of the exact time dependence of the three different cases are different. And that's because the fact that you have a boson or a fermion or distinguishable particles has measurable consequences that mean that's important. So you have to pay attention to that and understand the distinction between those cases. When you finish your project, you'll be able to run the thing using bosons, fermions, or distinguishable particles and see these exact same graphs and answer some of the questions that I cooked up for you to try to hopefully deepen your understanding of what's going on. I want to finish out today, this is not a long set of slides today, but I want to finish out by going over a section of the text. Griffiths describes something called the exchange force, and I just wanted to sort of redo his calculation using Dirac notation, just to point out that you don't necessarily have to write out all these integrals explicitly to kind of see what's going on. The idea is to compute the expectation value of the square difference between the position of the two particles. In the case of distinguishable particles, you just use the distinguishable ket AB. Now, the fact that it's written AB, the order is important. It means that particle 1, the first particle, is in state A, and particle B, particle 2, the second particle, is in state B. So we have particle 1, that's the first slot, particle 2 is the second slot, and this ket would say that particle 1 is in state A, particle 2 is in state B. And in that situation, you can compute this expectation value by simply sandwiching the expression x1 minus x2 squared between the bra and the ket, AB. You can expand the binomial and actually calculate the whole thing fairly directly. Now the fact x1 means that we're talking about the particle in slot 1. x2 means we're talking about the particle in slot 2. So when we go to evaluate these expectation values, the first term only involves the A state because it's x1, and that means it's the first slot, and A is the first slot. The first term, the B's, just hit each other because there's no x2 in that first term in the expression. On the other hand, the second term is all about slot 2, and so it's the expectation value of x in the state corresponding to the second slot. And finally, the last term is the expectation value of x in the first slot and the expectation value of x in the second slot. So it turns out to be the product of the expectation value of x in state A and the expectation value of x in state B. We can march ahead here and rewrite that. Notice that B on B is 1 and A on A is 1, so those bras and kets just sort of evaporate, and you get the expectation value of x in state A, the expectation value of x squared in state A, plus the expectation value of x squared in state B, minus twice the expectation value of x in state A times the expectation value of x in state B. This would be the expectation value of x1 minus x2 squared in the distinguishable case. I want to notice that if we had put particle 1 in state B and particle 2 in state A, we would have gotten the same answer, because you can see that if you swap A and B in this expression, it doesn't change anything. So which particle is in state A and which particle is in state B is not relevant in terms of computing this particular expectation value. All that matters is that that's the two different states they're in. Okay, so let's talk about indistinguishable particles. What's the difference here? Well, for indistinguishable particles, we've got to use a symmetrized or anti-symmetrized state for bosons or fermions, respectively. So if it's a boson, you get the plus sign, and if it's a fermion, you get the minus sign. But you can write the whole thing out as just AB plus or minus BA over root 2. So then what happens when we go to compute this same expectation value? Well, it gets a little more complicated, because psi sub I now has two pieces, and since there's a psi sub I in the left-hand bra and a psi sub I in the right-hand ket, we end up with many terms, and not to mention the fact that the binomial has 3 terms. So there's lots of terms we have to evaluate. We can expand the binomial again and rewrite this as the first term plus the second term minus 2 times that last bit. But each of these now has 4 pieces. There's because we have to expand all these bras and kets out. So it gets fairly complicated. Let's take the first term, x1 squared, and see how that comes out. We'll go ahead and expand that whole spiel. I want you to notice it's similar to the thing we had before, except now we have to be a little careful about keeping track of which slot corresponds to which number. Notice that the fact that we're talking about x1 means that it's only the first slot that counts in any of these terms. So we get x1 in state A squared, and then B on B gives us 1. And then the last term we have x1 squared in state B, and A on A gives us 1. But notice in the 2 middle terms, those guys go away, because we get A on B and B on A, and I'm assuming in this case that the 2 states A and B are different. If the 2 states are the same, then we only have to worry about the boson case, and we can talk about that later. But for the moment, let's just imagine they're different. And notice that the same thing works out for particle 2, x squared of particle 2, because it's basically the same algebra. You just have to plug in the other state. But when the last term, the one where we get x1 times x2, it's a little different, so we should work that one out. So let's go ahead and expand that all out, and you'll see that we have a new kind of term here that didn't exist before. We still have the x in state A and the x in state B, but now we have these cross terms where we have x taken between states A and B, and x taken between the states B and A. Now remember, these states are all stationary states, and x isn't observable, so that means these inner products have to be real numbers. The expectation values have to be real, even though they're two different states. So basically, A on x on B and B on x on A are going to end up being the same thing. And so we can simplify this quite a lot using the same kind of notation we had before. Notice that when the whole thing comes out, it looks similar to what we had before, but we've got an extra term. The first three terms in the result are the same thing we had for the distinguishable particles, but this last term is due to the fact that the two particles are identical. And notice that the sign there is important. If they're bosons, we take the upper sign. If they're fermions, we take the lower sign. And the upper sign means that for bosons, the particles are closer together than they would be if they were distinguishable. And for fermions, it means the average distance between the two particles is greater. So they avoid one another more than they would otherwise. And the degree of avoidance has to do with the size of this so-called exchange integral, the AXB, where the two states are both acting on the displacement operator. But we kind of saw that in the demo. I hope you sort of recognized it in the demo, but also you can see it works out here mathematically. And I also hope that you found this notation a little bit easier to see and to understand than the detailed integral version that was in the text. But we'll see you guys. I'm not going to be here next time. I'll be back on Friday, but hopefully you guys are being well taken care of. There'll be another tutorial on Wednesday for you to work through. The tutorial for today is going to involve fermions in three-dimensional infinite square well situations. Anyway, talk to you soon. Hey guys, welcome back. It's lesson 2, atoms, structure, and all that. This is going to be a quick lesson. We're going to start talking about helium. Helium has 2 protons and 2 neutrons in the nucleus, and of course it has 2 electrons. So that makes it an interesting atom from our perspective. In the ground state configuration, both the electrons are in the n equals 1, l equals 0 state. So they're in a sort of hydrogenish configuration. Let's talk about the Hamiltonian. The Hamiltonian has the kinetic energy of electron 1, that's the first term. Then it's got the potential energy between electron 1 and the nucleus. And then we have to add to that the kinetic energy of electron 2 and the potential energy of electron 2 relative to the nucleus. And then the last term here is the potential energy of interaction between the 2 electrons. So we can think about those terms as being broken down into those pieces. But to solve the problem, the Schrödinger equation, which is that this Hamiltonian acting on the wave function is equal to some constant energy times the wave function, the eigenvalue problem, it's easiest to begin by ignoring this last term, because it's a lot of trouble. But if we ignore that term, then you'll notice that the first brace term, the term in braces there, is nothing other than the hydrogen Hamiltonian, except that there's a 2 in front of the electron charge. And the same thing for the second term. One deals with electron 1, one deals with electron 2, and there are no terms in the Hamiltonian, ignoring that last one, that deal with the interaction between the electrons. And so we can think of that as being 2 independent electrons that don't interact with each other at all. And that's nice, because that means we can factor the wave function. You know, this is the problem now. It's the eigenvalue problem. Hamiltonian 1 plus Hamiltonian 2 acting on the wave function is the energy times the wave function. But let's see what happens when we factor the wave function into a part that only depends on electron 1 and a part that only depends on electron 2. We can do that in this circumstance and see that that allows us to satisfy the Schrödinger equation because the Hamiltonian 1 only acts on wave function 1 and Hamiltonian 2 only acts on wave function 2. And we already know if those are hydrogenic wave functions, exact hydrogenic wave functions, and the Hamiltonians are exact hydrogenic Hamiltonians, that we already know the solution to that problem. And it has an energy of 13.6 electron volts for each electron, and times 4 because of the 2 in the charge. When you go back and work out the energy, you'll notice that the 2 gets squared, and so you end up with 4 times the energy. And so that means that when you add the two energies together, electron 1 and electron 2, you get about 109 electron volts compared to 13.6 electron volts for the hydrogen atom. And if you measure the energy, it turns out to be about 80 electron volts. So we lost 30 in there somewhere. That means that the term we left out is not negligible, but we're not in crazy land either. We're sort of close. We're going to find out soon enough how to fix this problem and various strategies to improve our approximation. But that doesn't come today. We'll deal with that a little bit later. But what I wanted to talk about is what happens if I have atoms with more than 2 electrons, and how do we deal with that? The answer is, as you add more protons and electrons, you can no longer use the 1s shell. You have to go to the 2s shell and the 2p shell and so on. And so, for example, for carbon, there's 2 electrons in the n equals 1, L equals 0, and there's 2 electrons in the n equals 2, L equals 0, and 2 electrons in the n equals 2, L equals 1. So that's what those configuration things mean. But of course, the total angular momentum of those electrons would be capital L, and the total angular momentum of the spin plus the orbital angular momentum of both of the electrons is going to be capital J. And the way folks have cooked up to represent that, the condition of the total angular momentum and the total spin and the total orbital angular momentum, is this so-called term notation. So for example, if you have a system with a total spin of 1, a total orbital angular momentum of 1, and a total angular momentum, spin plus orbital, of 2, you'd write that as 3p2. The 3 comes from the spin of 1, the p comes from the L of 1, and the 2 comes from the J of 2. And for a given configuration, for example carbon at the top of the screen, the term that has the lowest energy is 1, the one with the maximum total S, consistent with the Pauli exclusion principle. It's got the highest L, consistent with anti-symmetry, that the overall wave function has to be anti-symmetric with respect to interchange of any 2 electrons. And for a given subshell that's not more than half full, J is going to be L minus S, but if it is more than half full, J will be L plus S. And that's it. That's the whole lesson. I know that's a lot to chew there. You should read the section 5.2 on atoms and configurations and all, and you should also listen to this podcast carefully, and we'll work on some board work in class, a couple of homework problems, and these will ultimately become your homework as well. So we'll see you guys next time. Hope that wasn't too bad. Talk to you later. Welcome back, guys. It's time for lesson 4. So we're going to talk about atoms and solids. I wanted to start from last time. We didn't quite get the board work done, so I wanted to remind you about problem 512 in the book, which was to determine the electronic configurations of some atoms and the corresponding angular momentum and term symbols. So the table of atoms that we're dealing with is right here, table 5.1 out of the book, and we were going to work on 1 through 10 for the configurations, but the interesting part is actually the term symbols, those guys on the right. So and the other problem we talked about is to use Hund's rules to figure out which states of the possible states are the ground states, the lowest energy states, and those are the term symbols in the 3rd column there, or I guess the 4th column that starts with 2s 1/2 and so on. Now we worked out the term symbols for the first 4 because they're trivial. They only involve S states in which L is equal to 0, and so all you have is S. And it's quite obvious how those have to add up. The first really interesting case is boron. So I want to treat boron as an example, but carbon and nitrogen we'll work out in class today in detail at the board. But let's look at boron and see what it has to do. So what's the configuration of boron? It's got a helium shell, then it's got 2 electrons in a closed s shell, and 1 sort of trailing electron, a valence electron, in the 2p shell. Now what does that mean? Well, it means L is equal to 1 because it's a p electron, and it means S is equal to a half because there's only 1, and each electron has a spin of a half. And as you know, J then could either be 1 plus a half or 1 minus a half, because you can either get the the long added together, the long or the jackknife, when they're subtracted. So you get L plus S and L minus S as possible combinations. Remember when we had 2 electrons in an S shell, you either have, and you add the 2 spins together, that you either get S total equals 1 or S total equals 0. It's the same idea. The 2 spins either add or subtract. But here now we've got an orbital and a spin angular momentum, so they either add or subtract. That's sort of how it works out. So what are the possible terms? Well, if J is 3 halves and L is 1 and S is a half, then it would be a p state since L is equal to 1. It would be a 2p state because S is a half. And it would either be 2p 3 halves or 2p 1 half. So those are the possible term symbols. So that's pretty easy. It's actually not that complicated. It gets a little more interesting when you have more than 1 electron, which we will in class today. But that's the basic idea. Now the question is, of these 2 term symbols, which one is the ground state? Because remember, in the hydrogen atom, energy didn't depend on any of these things, spin, angular momentum, or whatever. But when you have multi-electrons, that electron-electron repulsion means energy now does depend on these properties. So how do we figure out which of these states has the lower energy? That's where Hund's rules come in, and there are 3 of them. The first rule is to maximize S. Well, in this problem, there's only 1 spin that's not in a closed shell, so S is already maximum, it's just a half. If we had more than 1 electron, of course you'd want to put the spins aligned, so you'd want to have 2 spins pointing up. Now if you're in an S shell and you have 2 spins, there's only room for 2 spins, so you can't have them both pointing up because you'd be violating the Pauli exclusion principle. So the rule is you need to maximize S, but you have to also satisfy the Pauli exclusion principle. So in a p shell, you can get 3 electrons pointing up. If you try to put a 4th one in, then you can't put a 4th one in pointing up, and so one has to point down. It goes kind of like that. Anyway, the second rule is you need to maximize L. So in this case, there is only 1 L. There is only 1 electron. L is fixed at 1, so we can't really do anything about L. With more than 1 electron, of course, it becomes more interesting. And the typical issue you run into is you have to maintain the overall antisymmetric property of the overall wave function. So if the spins are all aligned, they would have a symmetric combination, and that would mean the L would have to be antisymmetric. And in the case of multiple electrons, that can be a little tricky to figure out, but we'll see how to do it, at least for nitrogen and carbon in class today. But that's the idea. You maximize L with the constraint that you have to satisfy the overall asymmetric property of the wave function. And finally, if the shell is greater than half full, the J you want to use is L plus S. But if it's less than half full, you want to use L minus S. Well, this shell is certainly less than half full. There's room for 6 electrons, and we only have 1. So that means that J is going to be L minus S, so the correct term is the 2p 1 half. That's kind of how it works. Okay, the other thing I want to talk about here is the exchange force. We talked about a potential board work problem. We never really did this. This actually is related to a homework problem in the book, where you'd write out the unnormalized wave function for the three cases of distinguishable, fermion, and boson when one particle is in the n equals 1 state and one particle is in the n equals 2 state. That's an interesting problem. It's not that hard to do. What I want to talk about now is a follow-up question. What if for those three cases, distinguishable, bosonic, and fermionic, you'd want to compute the expectation value of x1 minus x2 squared. In other words, the expected squared difference between the position of the two particles in those three cases. And we talked about that a little bit, and I know I discussed how you calculate that with the bra and ket notation. But what I want to do, just to extend it a little bit, is to talk about how would you handle this using some kind of a computer algebra system. So you could use Sage or Mathematica or Maxima. There's a bunch of different computer algebra systems out there. I happen to like Sage most of the time, and so I'm going to demonstrate with that. Okay guys, I just wanted to point out that you can use symbolic algebra to solve analytical problems in quantum mechanics. Here is the solution using a system called Sage. Now, Sage is it's a computer algebra system that's free, which is why I like it. We don't have a license for Mathematica at my place, and so this is what I've come to use, but of course you can use anything. You could use Mathematica or Maple. There's another free one called Maxima. So whichever you like. The point is only that it is possible to use a computer algebra system to calculate things that are complicated to calculate directly with pencil and paper. Here's an example. We have a wave function. I call it psi f, which is the fermionic wave function. It's the sine of n1 pi x over a times the sine of n2 pi x over a, x2 over a. We have x1 over a here. And we subtract from that the sine of n2 pi x1 over a times the sine of n1 pi x2 over a. So the point is, if you swap x1 and x2 in this wave function, it's anti-symmetric, and that means it's appropriate as a wave function for fermions, which are identical particles that have to have an anti-symmetric wave function. I just want to print out a solution. This is how you solve for the normalization constant. You say that when you integrate psi f star, psi f, in other words, psi f multiplied by itself, integrated where x1 goes from 0 to a, and x2 goes from 0 to a, you need to get 1. So this is the integral, double integral of the product psi f squared, where x1 goes from 0 to a and x2 goes from 0 to a, and we're demanding that it be equal to 1, and we're solving for the unknown. The only unknown, of course, is the normalization constant. So we're going to print that out, but then I happen to know the answer is the square root of 2 over a for the normalization constant. And so I'm going to put that in, but here I'm going to calculate psi f times x1 minus x2 squared, and again x1 goes from 0 to a and x2 goes from 0 to a, and print out the answer. So this is going to compute, using the correct normalization, the expectation value of x1 minus x2 squared. Then it's the same thing, but with the bosonic wave function. Here we get a plus. The normalization constant is the same, and we get a plus here to make the wave function symmetric with respect to x1 and x2, and we print out the expectation value of exactly the same integral, but now using the bosonic form of the wave function. And finally, in the distinguishable case, there's no particular symmetry at all. The normalization constant then is not the square root of 2 over a, but just 2 over a. Okay, and we print out the same expectation value for that one. If we go ahead and run this, Sage, you can run it in a web browser, but I like to run it from the command line because I'm that kind of a person. Notice it printed out the solutions for AF, for AB, and for AD. And indeed, AF is the square root of 2 over A, AB is the square root of 2 over A, but the distinguishable case has a normalization of 2 over A. Notice that's just the square of the one-dimensional distinguishable particle, or the single distinguishable particle normalization function constant. But I'll let you guys think about why this is a square root of 2 here for the boson and the fermion case. But the most important thing to notice is that the expectation value of the distance between the electrons, or fermions, we don't know that they're electrons, is 0.41 A, whereas for the bosons it's 0.19 A, and for the distinguishable particle it's 0.32 A. So it's almost half an A for the fermions, a fifth of an A approximately for the bosons, and a third of an A for the distinguishable particles. So they're clearly different, and that's what's interesting. Okay, so next we're going to move on from atoms. We're just getting a flavor of how this stuff works. We're going to move on and talk about solids. So first of all, we're going to start with the simplest possible treatment. We have non-interacting electrons in an empty box. So we're ignoring electron-electron repulsion, and we're ignoring the fact that the box is made of atoms. We introduce a concept of K-space. We get a Fermi energy out of that, and we get a very important concept called the density of states. So I want to touch on all those things. Obviously, these are severe idealizations, but they're idealizations that are useful because it turns out that the dominant issue when you talk about electrons in a solid doesn't turn out to be the atoms so much, especially in conductors, so like conducting metals. You can't really intelligently talk about insulators without discussing the atoms, but anyway, let's move on. So the idea is, first of all, let's imagine this is the potential in the neighborhood of a single atom. It might look something like this. If I add more atoms, I get an overall potential that looks something like that. That might be what one free electron would see inside of a solid. But if you average this over distances that are large compared to the atomic spacing, you get an average potential that ends up looking something like that. And that's sort of the average potential we want to think about in dealing with the free electron model. So obviously on a microscopic scale it's not very accurate, but if you look on a large scale, so for a long wavelength electron, for example, at a fairly low energy, this is going to be a reasonable approximation. And we already know the answer. If you have a three-dimensional box like that, you satisfy boundary conditions where the wave function goes essentially to zero at the boundaries, and you get this result, which we're already familiar with. And what I want to do is start looking at counting the eigenstates. So I want you to imagine having a sort of a grid, and the grid is in k-space. So the horizontal direction is kx, and kx can be pi over the size in the x direction, 2 pi over the size, 3 pi over the size. So this would be sort of like pi over a, 2 pi over a, 3 pi over a. I've just generalized it a little bit to a cube that doesn't happen to have the same dimension on all three sides. What about in the y direction? In the y direction, it's also discrete k values, pi over l, 2 pi over l, 3 pi over l, like that. And finally, in the z direction, you get pi over l, 2 pi over l, 3 pi over l, and so on. Now let's imagine counting, or enumerating, I guess, the states that are available. In the y direction, you could be in the pi over ly state, but in the x direction, you could be in the pi over lx, the 2 pi over lx, the 3 pi over lx, and so on. The 4 pi over lx. But don't forget, you could also have the y direction be 2 pi over ly, and the x direction be pi over lx, and so on. So you can imagine counting more states that are available. And then finally, we could start bumping up the z direction. So you could have pi over l in the z direction, and 2 pi over l, and so on. So you can see that in three-dimensional k-space, the states that are available correspond to these discrete points that can either be occupied or not. That's kind of the idea. And we need to be able to count and calculate what the probability of these different states being occupied and so on, and also to be able to count the total energy in the system depending on which states are occupied. That's kind of the idea. So I want to do another demo that sort of illustrates that in 3 dimensions. Hi guys, here's another cute little demo. The idea here is to visualize K-space, and there are two basic options having to do with boundary conditions. So, for example, you can choose Dirichlet boundary conditions, which are those we've been discussing, where the wave function goes to 0 at the edges of the three-dimensional box. And an alternative is periodic boundary conditions, where the wave function has to repeat every time it goes through a distance a. I want to show you both of those so you can see the difference between the two. The other thing we can adjust is if I have a limited set of 10 k values in each direction, so pi over a, 2 pi over a, 3 pi over a, up to 10 pi over a in the x direction, and then the same thing in the y direction and the same thing in the z direction. That'll give us 1,000 points in k-space potentially. In one case, all of those are displayed, and it looks like a cube, and that would be all energies equals 1. The other case, down here, I'm calculating the energy of each point, and I'm only creating a representation of those points if they fall in the range that's less than the maximum for any one direction. So that'll give you an idea of what it looks like when you have states that are limited by total energy. So when you're adding electrons to a solid at 0 temperature, you know the electrons always go into the lowest states up to a maximum energy, and that produces a sort of a octant of a sphere in Dirichlet boundary conditions or a full sphere in periodic boundary conditions, and I just wanted to show you sort of how that works. So for now, let's look at Dirichlet boundary conditions with all energies. I'll go ahead and run the program, and you'll see here that you get something that looks sort of like a cube. There it is. Let me go ahead and make that a little bit bigger, and you can see that we have all the states all the way up to 10 on each in each direction, and that would be k-space. So this is the x direction, the y direction, and the z direction is blue, and it's kind of fun to look at, but I hope that gives you an idea. Notice that this is sort of a cubic array of possible states. Okay, now what I want to do is change this to Dirichlet, or to non-Dirichlet. Let's look at periodic boundary conditions, and you can see the difference. Now notice that the k values are no longer restricted to be positive only, but they can be negative, and you still get a kind of a cube, but now it's 10 points on a side, so there's only 5 on each side of the origin. So it looks like the density in k-space is reduced by a factor of 2, but the density in energy is not any different, because now for every point on this side, there's another point on that side. So the points are twice as far apart from each other, but now there's double the number, and so if you go through and calculate the overall density, it turns out to be the same. Okay, let's see what happens if we go to Dirichlet boundary conditions, but now we limit the energies to be within a certain range. This gives us a sort of a Fermi surface, and you can see that now we've got a kind of a octant of a sphere, and the spherical surface is determined by the fact that the sum of the squares of the k values in the 3 different directions has to add up to something less than the maximum in this case. So you can kind of visualize the it's like you take an apple and slice it into halves in 3 directions. This is what you'd wind up with. Of course, if you go back to periodic boundary conditions, let's go ahead and do that, then you get something that looks like a real sphere. So this is now a sphere in k-space. Now it looks a little chunky because I've only got 10 potential values of k in each direction. So just to show you that it smooths out if you go to larger numbers of k, I'm going to go ahead and double this so you can see what it looks like with twice as many. And we'll blow that out a little bit, and then look at it. It's a little sluggish because it's a lot more points to manage, but notice that that's looking pretty darn spherical. In a real situation, of course, 20 times 20 times 20, what is that? That's going to be 8,000 points. So that's we've multiplied by 8 the number of points in k-space that we have. In a real system, of course, you're going to have something like Avogadro's number of states, and so the spacing here would be much too small to even see. And all right, so that gives you an idea, I hope, of what K-space looks like. When you're doing calculations, I find it useful to literally visualize, that space, and maybe draw some pictures to help you think about it, and so on. So good luck. Okay, and finally, if we have time today, there's another board work we're going to do. It's actually, I just want to take some time and go over that tutorial. The tutorial basically had a sequence of problems where you would work out the volume of a single state in K-space, compute energy eigenvalues of those points in K-space, and then calculate average, like the total energy, the Fermi energy, the pressure, stuff like that. So that's what we'll be doing. If we have time in class, I'll try and go over some of the questions in that tutorial. I'll try to remind you also to bring your tutorial, as much of it as you've worked out, to class, so we can discuss that. All right, have a good one. Hey guys, welcome back. It's time for more atoms and solids. We're going to begin with carbon. So we started talking about boron and carbon and nitrogen, and this stuff is endlessly entertaining. So there were numerous questions that were asked during class last time, and I wanted to take a few minutes to tell you the real story of how this stuff works. We're going to need it anyway later when we get to perturbation theory, so I figure why not get it done now. So that's the idea. So talking about carbon, it's got a helium shell, and then it's got a filled 2s shell, and then a partially filled 2p shell, only 2 electrons there. And what I want to point out is that you can understand what's going on with carbon completely only by working out the detailed angular momentum states involved. So let's remind ourselves how that works. First, I want to remind you of this table from Chapter 4. It's the terrible and hideous Clebsch-Gordon coefficients. You basically need these guys anytime you need to add 2 angular momenta together. And I'm going to explain to you how you can compute them yourself if you feel like it, but they're difficult enough to compute, and they're used often enough that enterprising souls have created tables so that we don't have to compute them. That's the idea. But today we're adding 2 p electrons. Each p electron has an angular momentum of 1. We're adding those 2 angular momenta together to get a total angular momentum that could be 1 or 2 or could be 0. And the question is exactly how does that come about? Well, this table enables you to add 2 angular momenta together. You'll notice in the upper left-hand corner there's a spin 1/2 plus a spin 1/2. And you'll recognize that table from Chapter 4. We used it to get the 2 possible total angular momentum states for spin 1/2, and that was 1 and 0. There was a 1 plus 1, 1 0, 1 minus 1. And you'll notice that the vertical columns tell you how to compose the total spin, total angular momentum quantum states. And you can see that 1 1 is simply both spins pointing up, plus 1/2, plus 1/2. But 1 0 is a superposition of plus 1/2, minus 1/2, and minus 1/2, plus 1/2, and they're added together. They're both positive. And finally, 1 minus 1 is both spins down, minus 1/2, minus 1/2. But the 0 0 superposition, the singlet superposition, is plus up down minus down up. And the fact that there are halves there means that you need to use coefficients of 1 over the square root of 2 and minus 1 over the square root of 2. So every coefficient is really square rooted. There's a little note about that at the top of the table. And also notice the notation. The total angular momentum states are labeled at the top in the horizontal direction, and the angular momentum states that go into the superposition are labeled on the side in the vertical orientation. So we'll see how that works here with the carbon. So let's focus on the 1 plus 1 situation. We're adding 2 angular momenta together, each of which has a magnitude of 1, to form angular momenta that have magnitudes of 0, 1, or 2. That's what that lower left-hand table does. Let's move some stuff out of the way here, and let's talk about the highest angular momentum state you could make, and that's the 2, 2 state. a total angular momentum of 2 with a z component of 2. The only way to make that is to make both angular momenta of the individual electrons plus 1. So you can see that both of the 1 unit angular momenta are pointing up. Okay? Now, what if I want to know the 2-1 state? In other words, it's got a total angular momentum of 2, but a z component of only 1. Well, there's 2 states of the individual electrons that could do that. There would be the 1-0 plus the 1-1, or the 1-1 plus the 1-0. But we don't know offhand what the superposition is going to be. Well, to get that, we can apply the L minus operator. If you apply the L minus operator to the 2-2 state, you'll get 2-0. But you can see that you'll also get 1-0 plus 1-1, and then you'll get plus 1-1, 1-0. So let's see how that looks. It looks something like that. And you'll notice that the table tells you what the coefficient is on each of the individual eigenstates in order to make the total thing properly normalized. That's the idea. And properly weighted. So you could do this by hand by applying L minus, but somebody's already done it for you, and that's what this table is. What if you apply L minus again? Well, then you get a little bit of 1, 1, 1, 1 minus 1, 1, 0, 1, 0, and 1 minus 1, 1, 1. Notice these are the only combinations of the 2 individual electron eigenstates that have a z component that adds up to 0. So you have to add a little bit of each of the possible combinations. And the fact that it turned out to be in this proportion is due to the behavior of the L minus operator. You'll notice that there's 2 contributions to 1, 0, 1, 0, because I can hit L minus on the first electron in the first state of the 2-1, or I can hit L minus on the second state of the 2-1, on the second electron of the 2-1. So there's 2 different ways to make that middle term, but there's only one way to make the outside terms. To make the first term, I have to hit L minus on the second electron of the first term of the 2-1, and to make the last term, I have to hit L minus on the second term of the 2-1, on the first electron of the 2-1. Whew. Okay. Anyway, if I hit L minus again, I get 2 minus 1. If I hit L minus again, I get 2 minus 2. And if I hit L minus on that one, I get nothing, because you can never have a z component that's greater in magnitude than the magnitude of the angular momentum itself. So I end up with 5 states of total angular momentum 2 with the 5 possible z components. And you can see that those are composed of various combinations of the individual electron states. Now what I want you to look at is symmetry. If I swap the 2 electrons in any of these superpositions, notice what happens. In the 2-2 state, obviously if I swap them, I end up back where I was. In the 2-1 state, I just exchange the 2 terms, but the total superposition remains unchanged. In the 2-0 state, if I swap the 2, the first and the last terms change places. The middle term doesn't make any difference because they're both in the same state. And so you can see that no matter what I do, these guys are all symmetric under interchange of the 2 particles. So they're no good if I'm looking for an anti-symmetric state. In the state of carbon, we want the maximum spin, and the maximum spin occurs in the triplet. The triplet is symmetric, and so I need the spatial part of the wave function. The angular momentum part of the wave function has to be anti-symmetric, and you can see that these guys are all symmetric, so it's no good. The L equals 2 cannot be used for carbon. So I've got to look further. So let's figure out what is the what about the angular momentum of 1 states. Now in this case I need the maximum z component of angular momentum I can get if the total angular momentum is 1 is 1, 1. So I got to start with the 1, 1, and it's got to be orthogonal to the 2, 1, and you can see that the only combination of 1, 1 and 1, 0, which is what I need to get a z component of 1, that's orthogonal to 2, 1, is the same thing with a minus sign. So 1, 1 has to be orthogonal to 2, 1. If I apply L minus to that, I get 1, 0. If I apply L minus to that, I get 1, minus 1. Now I want you to look at these 3 states and notice what happens when I interchange particles. They all have anti-symmetry. That is, under interchange of the 2 particles, they are anti-symmetric, so they satisfy the Pauli exclusion, or the Pauli exclusion principle. Since we have a symmetric spin state, we need an antisymmetric spatial wave function, and these guys do it. Just for completeness, I'll go ahead and try to figure out what is the 0, 0 state, because there is a 0, 0 state in this system. You can see from the Clebsch-Gordan coefficient table, it's got to be that superposition. You know that it has to be orthogonal to both 1, 0 and 2, 0, and but it's got to be a superposition of these three states, and so it turns out this is the only orthogonal combination of 1, -1, 0, 0, and -1, 1 that's orthogonal to 1, 0 and to 2, 0. So that's the idea. And that's why carbon ends up with L equals 1, not L equals 2. And since it's half full, it means that J has to be L minus S. S is 1, L is 1, so I think J turns out to be 0 in carbon. But I don't have that slide in front of me, so I'm not positive of that. But that's basically how it works. Okay, so what about nitrogen? Well, for nitrogen, we've got 3 electrons. And what I'd like to do is to point out that we can use our understanding of the carbon situation to work out nitrogen. So let's see how that turns out. First of all, I want to point out that there's an easy way to construct an antisymmetric wave function in general. It's called a Slater determinant. So if I have a bunch of quantum states, A, B, C, D, E, and I have a bunch of particles, 1, 2, 3, 4, 5, or whatever, and I want to form a totally antisymmetric combination of the wave functions using those particles, I can form what's called a Slater determinant. I put the wave functions in the columns, and I put the particles in the rows, and then I just simply calculate this determinant. So for example, if we want to put 3 electrons in the L equals 1 state, but with different values of m sub L, 1, 0, and -1, we'd put them in something like this. So that would mean, what have I got? I've got electron 1 in the plus state, electron 1 in the 0 state, electron 1 in the -1 state is the first row. The second row is electron 2 in the up, electron 2 in the 0, electron 2 in the down, and so on. If I multiply all that out and use the normal rules of matrix algebra, okay, I get the first electron is up, and I multiply that by the second electron is at 0, the third electron is at -1, minus the second electron is at -1, and the third electron is at 0. And I do that for all 3 rows using the normal rules of matrix of determinant calculation or whatever. Now I can go ahead and multiply that all out, and I get this hideous mess. But basically it tells you that there is a superposition of the 3 electron states that is totally antisymmetric, and this would be the spatial part of the wave function, because the spin part is going to be symmetric in view of the fact that we've maximized the spin. All 3 spins have to be up, and then the only way to make all 3 spins up is if it's symmetric. So that's one way to calculate, but the question is, what's the angular momentum of that state? We know what the state is. That's got to be the angular momentum state of the 3 electrons, but it's hard to look at that and know what angular momentum it corresponds to. So what I want to point out is that we can work out the I'm going to claim that that's the 0, 0 state, that's the total angular momentum of 0 and a spin of 0. And what I want to show is that we can use the Clebsch-Gordan coefficients to basically the approach we had before to demonstrate that. Let's see how that works. Okay, so this is the 0, 0 state, and we want to form this. Here's the idea. If we combine the first 2 electrons, we need them to be antisymmetric. The only way to make the first 2 electrons antisymmetric is if they're in a L equals 1 state of some kind. Any L equals 1 state will be antisymmetric. So the idea is, if we let the first electron in this 3 electron set be the first slot in the 0, 0 state, and let the second slot be filled by the 2 electrons forming an L equals 1 state together. So the idea is the last 2 electrons we know have to be in some superposition of 1, 1, 1 minus 1, and 1, 0, because those are the only antisymmetric states we can track down. And we put those in as the second angular momentum in the full 3 electron 0, 0 state. Okay? That's the idea. And we notice that if you go back and look at the determinant structure from the Slater determinant, what do you get? You get the first electron in the 1 state, the second electron in the 0 state, the third electron in the negative state. But if you look at what you get from the first term of this overall superposition, we get the first electron in the 1 state, the second electron in the 0 state, and the third electron in the -1 state. That would be the result of plugging the 1 minus 1 of the 2 electrons into the first term of the 0, 0. And notice that the 1 over the square roots of 2 and the 1 over the square roots of 3 multiply to give us the 1 over the square root of 6 in the original Slater determinant. So we haven't exactly proved this is the only way to do it, although it does turn out to be that way. But it at least demonstrates that what we have constructed using the Slater determinant is in fact a 0, 0 state made up of the first electron in a superposition of 1, 1, 1, 0, and 1 minus 1, and the other 2 electrons in superpositions of 1, 1, 1, 0, and 1 minus 1 themselves, so that the total angular momentum ends up being 0. So this would be the so-called jackknife situation. If you multiply it all out, you get exactly the same thing we had before. Okay, so that is why, or that is one way to look at the reason nitrogen ends up being an orbital angular momentum of 0, carbon ends up being an orbital angular momentum of 1. And I know this stuff is nuts. We will get better at it as we get more practice. Okay, let's talk about a periodic potential. One way to make a periodic potential in one dimension is just as a superposition of delta function potentials. We had some experience with delta function potentials last semester in Chapter 2. Within a unit cell, there is no potential at all. So we're just talking about a free particle. That means that it needs to be some kind of superposition of sine and cosine. There's a thing called Bloch's theorem, which says that if you have a periodic potential, the wave function in any other place has to be periodic. In other words, if you've got the wave function at point x and you want to know what it is 1 unit spacing away, you can take the wave function at point x and just multiply it by this complex exponential using a real value of capital K. So capital K is sometimes called the crystal momentum. It's produced by solving a transcendental equation typically, and we're going to see how that comes out. If you apply the boundary conditions at the delta function, just like we did in Chapter 2, you end up with an equation that looks like this. And notice that this means that if you tell me capital K, I can solve this transcendental equation to find the little k. Or the other way around, if I solve this transcendental equation, if I put in a little k, this tells me capital K. So this gives me a relationship between the crystal momentum and the k value, but the k value is determines the energy, right? Determines the energy of the thing. So of course, Griffiths likes to parameterize these things, so he defines Ka to be Z, and he defines M alpha A over h bar squared to be beta. So beta is a measure of the strength of the potential and the crystal spacing, the unit cell spacing. You can think of it as a strength parameter, a geometry parameter. And Z, of course, is related to the energy. So let's do a little demo to see how this equation actually produces solutions. Okay, so this is the equation that Griffiths comes up with. This is the equation for the cosine of capital K times A, and I'm letting x be Griffiths z, which is little k times A, and you notice the function is a cosine, and then it's the sine of x divided by x, which sometimes is called a sinc function, but it's the sum of those two guys that has to be equal to the cosine of big K times A. And I've got a dial here where I can adjust the value of beta, so I can make beta big and small. One thing to notice is that if beta is 0, that means that I get rid of the potential altogether, that the function stays always within the bounds of -1 and +1, which means there are solutions for all values of little k. But if beta gets to be big, notice that the function grows. I think Griffiths uses 10 in the book, in the diagram in the book. In that case, this function exceeds the bounds of -1 and 1, and there's no value of capital K that can match the value of this function. And so these points where the function exceeds 1 or -1 are forbidden. There is no solution in that region. And since the energy depends on little k, that means that these are regions of forbidden energy in the final system. And so this is what gives rise to the so-called gaps. So in a real solid, there are energy gaps that electrons in those solids aren't allowed to occupy. And those gaps have to, if let's say we have a band of energy levels, so the set of solutions, since the capital K is quantized to have only particular values, in the periodic boundary conditions, basically n times the k times the lattice spacing has to be 1. So that means, that's not quite right, it has to be an integer. So it means that capital K has a discrete set of possible values. So you can imagine if you zoomed in here, a set of horizontal values here of K that would correspond, of big K, that would correspond to solutions that have a certain value of little k. And so this range of values of little k between here and here corresponds to a band of energies, and then there's a gap, and there's another band of energies, and there's a gap, there's another band of energies. In a real solid, if you have a band that's full of electrons and a band that is empty of electrons, then in order to get from the full band to the empty band, which happen to be called the conduction band and the valence band, for example, you have to jump across a gap. In an insulator, that gap is big, and because this band is full, all the positive and negative K values are gobbled up, there's no possibility of conduction. You'd end up with an insulator. If the gap is not too big, then you have a semiconductor, and if there is no gap, or if a band is half full, then you'd have a metal. So because there would be no energy required to go from a full band to, well, a full state to an empty state. Anyway, that's the idea. Now, the question is, what do these bands actually look like? So I cooked up a little Python program. Here is the function that you recognize, and I went ahead and took its derivative. So this is the derivative of the function. And I started out, I just picked some z values that were convenient. I create an array of n values that goes from -n/2 to +n/2. I picked n to be 1,000. And then I created the large k, I'm going to call it kappa, the large k array, to be integer multiples of 2 pi over big N. And the idea is that these are going to be crystal momenta, so-called crystal momenta. Then, I don't know if you're familiar with Newton's method, it's a way of finding zeros. You basically, we can talk about it a little bit in class if you have questions, but basically you give it a function and the value you want that function to have. You pass in the derivative of the function primed. The uncertainty, you're permitting the difference between the value of the function that you're willing to permit, and then a starting place to evaluate the function. And basically what you do is you evaluate the function at the starting place, you figure out its derivative at that location, and you project what z would have to be in order to make its value 0, assuming that that derivative is good. Then you reevaluate and keep going, and you just keep zooming in until you find the place where the function is very, very nearly equal to the value that you wish. As long as the derivative doesn't go to 0, the thing is pretty well behaved. If the derivative goes to 0 or becomes very small, it's not so good. But it turns out it's okay for this application. And then what I'm going to do is go through all the values of kappa and calculate the cosine of kappa times a, and then use Newton's method to find the value of z that satisfies the transcendental equation, and then calculate the energy at that location and throw it in a list, and then we can graph it. Then we're going to graph kappa versus the energy for the 3 bands. Let's see how that goes. If we run the program, we get, this is the energy for the lowest energy band, and then here's the next energy band, and here's the highest energy band. One thing I want to point out is that if I zoom in here and look at this energy band right around the origin, so I'll have to zoom in twice probably. There you go. You can see that near the origin, this thing is very nearly quadratic, and what that means is the energy goes like k squared, which is the correct behavior for a free particle. So for low energies in this band, the energy of the electron in the band is very nearly the same as a free particle. But when you go out to higher energies, the behavior changes, and you don't have free particle behavior. So what this means is as k gets bigger, the energy increases in a quadratic way. Here, as k gets close to a band edge, it starts to behave kind of strangely, where it sort of maxes out. And here, if you are in this band, as k gets bigger, the energy actually drops. So that's quite strange. And you'll have to take a course on solid-state physics to understand what all that means, but it's fun to think about, and if you have questions, of course, I'm totally happy to talk. Anyway, I think that's all for today, so we'll see you guys next time. Hi guys, welcome back. It's time for lesson 6. We're going to start looking at statistical physics. I know you guys just finished a course in thermodynamics, so I'm not going to go over all this in detail, but we will have some board work today where you'll get to exercise your combinatorics a little bit. But let's talk about 3 particles in an infinite square well. Let's suppose I have 3 particles in an infinite square well of size A, and one of them is in state capital A, one of them is in state capital B, and one of them is in state capital C. And the question is, how are they sharing the energy? Let's say they have a total energy that's fixed. Well, since the energy is proportional to the sum of the squares of the state numbers, then it means that the sum of the squares of the state numbers has to be constant. Now let's just take a random number. Actually, it's not completely random, because it turns out if the sum of the squares of the states is 363, there's several different ways to achieve that. You can have NA, NB, and NC all equal to 11. You could have 2 of them equal to 13 and 1 equal to 5, or 2 equal to 1 and 1 to 19, or you could have 1, 5, 1, 7, and 1, 17. So on the board today, we're going to be working through the various combinations of these guys to see what happens when we're dealing with distinguishable particles, fermions, and bosons. So that'll be on the board today. There is a couple of conclusions you can make in general. If you have a total number of particles is capital N, and you've got N1 in state 1, and N2 in state 2, and N3 in state 3, and so on, and the degeneracy of each of the states is D1, D2, and D3, then the total number of ways you can have those particles distributed in that fashion turns out to be this monstrous looking product, if the particles are distinguishable. On the other hand, if they're fermions, there are some combinations that can't happen, and as a result, the number of ways you can combine the particles is diminished from what you'd get for distinguishable particles. And finally, if they're bosons, then it turns out the number of ways is also different, and we're actually going to revisit this formula, discover how it comes about in detail when we talk about solids here in a little bit. I am going to work through the case of the Einstein model of solids in some detail. So what is the occupation number, or the expected number of particles in the nth state? It turns out it depends on the energy of the state and the degeneracy of the state. And it turns out it depends on something called beta, which we'll discover is related to the temperature, and another number which is basically a normalization constant that's needed to get the total number of particles to work out right. If the particles are distinguishable, the formula ends up looking like this. If they're fermions, it's a little different, and if they're bosons, it's a little different. So the idea is the expected, or the most likely distribution of particles in states depends also on the nature of the particles. And Griffiths does a lovely job of describing where these formulas come from and how they come about, so I'm not going to repeat all that in the slides, but we can talk about it in class if you're interested. Alright, so I want to work through an example in detail that shows sort of how this works at an elementary level. And the idea is, if you have a solid that's made up of atoms, in some very elementary way, you can think of each atom as a quantized simple harmonic oscillator. But a three-dimensional symmetrical quantized simple harmonic oscillator is really just three one-dimensional simple harmonic oscillators, because the potential is proportional to the sum of the squares of x squared, y squared, and z squared, and so the Schrödinger equation factors into three separate equations, and each one looks like a one-dimensional simple harmonic oscillator. And this, by the way, is an approach that's used in an elementary textbook called Matter and Interactions, introductory textbook by Bruce Sherwood and Ruth Jabay. And I'm just stealing their idea. I think it's a lovely plan, and it's a nice approach that I'm familiar with, and I think it helps students understand where this stuff comes from. So I want you to imagine we have an atom in a solid that can be approximated as three independent quantum simple harmonic oscillators. And the idea is, let's imagine for a moment that at this moment it happens to have four quanta of energy. That is, that it's got, if you look at the three different directions, the total energy, including the three different directions, adds up to 4 h bar omega. How many ways are there to distribute 4 quanta of energy among the three? Well, you could have one in the n equals 4 state, and 2 in the n equals 0 state. You could have the middle one in the 4 and the 2 in the 0, the outside one's in the 0, or you could have the right-hand one in the 4 and the other 2 in the 0. That's one possible combination. But you could also have these guys in different combinations of 3, 0, and 1, or you could have 2, 2, and 0, or 2, 1, and 1. So, and if that turns out to be all the different ways you can do it, that adds up to 15, if I'm not mistaken. And so there are 15 ways, and those are called microstates. So it turns out there's 15 ways to distribute 4 quanta among 3 oscillators. But each of those ways, we're going to call that a microstate. And in statistical thermodynamics, the idea is that every possible microstate is equally likely. And in the end, we really don't care about the microstates. All we care about is the stuff we can see and measure, and those are called macrostates. So a macrostate is simply not a particular way of distributing the 4, but the fact that there are 4 quanta there distributed in some way. That's kind of the idea. Okay, now suppose we have 2 atoms. Each of them has 3 oscillators, but let's say they're connected in some way. So they share a total amount of energy, like, for example, 4 quanta, but that at any given moment, one of them could have 4 and the other could have 0, or the first one could have 3 and the other one could have 1, and so on. How can that energy get distributed between the atoms? So, for example, let's say, how many ways can one have 4 and the other have none? Well, there's only one way to have none, and there's 15 ways to have 4. So that means that there are 15 ways of one having 4 and the other having none. But what if one had 1 and the other had 3? Well, you can work out, just as we did, the number of ways of having 3. It turns out there are 10 ways. How many ways are there of having 1? Well, an atom has 3 directions, so it could either be 1 in the x direction, 1 in the y direction, or 1 in the z direction. That would be the only way to have, there are 3 ways to have 1. Well, there's 10 ways to have 3 and 3 ways to have 1, so altogether there's 30 ways that one atom could have 1 and the other atom could have 3. Does that make sense? If you keep doing that, of course they could each have 2 and so on. If you keep working that out with 2 atoms, each with 3 oscillators, and a total of 4 quanta, you end up with a picture that looks something like this. There's 15 ways of the first atom having 0 and the other atom having 4, and there's 30 ways of the first atom having 1 and the second atom having 3. Turns out there's 36 ways of both of them having 2, and so on. And so you can see that the most likely situation is the one that has the most possibilities, and that turns out to be each of them getting 2. Is there a way to come up with a formula that would enable us to reproduce these numbers even if the number of atoms and the number of oscillators was larger? And yeah, it's actually Griffith's equation for bosons, because these oscillators behave like bosons. Since there's no restriction on the number of quanta you can have in any one oscillator, then these things are basically bosonic in nature. And the formula turns out to look like this. It's the number of quanta plus the number of oscillators minus 1 factorial divided by the number of quanta divided by the number of oscillators minus 1. And we'll talk about in class where that actually comes from. There's a nice picture you can use to convince yourself that that's correct. But basically, it's straightforward mathematically, at least, to compute how many combinations there are. So suppose we did the same project, but now we used 300 oscillators in one clump of material and 200 oscillators in a different clump of material, and calculated the number of ways of one of the clumps of material having so many quanta and the other clump of material having so many quanta. We'd get a graph that looks something like this. What you have there is the fraction of quanta. Let's say, this is an example with 100 quanta altogether distributed between these 500 oscillators. And the most likely situation is when 60 of the quanta is in the first chunk of material and 40 are in the second chunk of material. So we're looking at the number of quanta of energy in the first chunk as a function as the horizontal axis, and the number of combinations of ways of doing that as the vertical axis. Notice that the numbers here are dramatically larger. The numbers go up to 7 times 10 to the 114th number of microstates. So it becomes dramatically larger, and this is with only 500 oscillators. In a real chunk of material, of course, you've got 10 to the 23 oscillators, and so the distribution of microstates becomes very, very sharp. If you take the logarithm of the number of microstates and you graph that, it also has a peak at the same place. Notice something about the logarithm of the number of microstates. There's the omega 1 is the number of ways of putting Q1 oscillators in block 1, and omega 2 is the number of ways of putting Q2 oscillators, or Q2 quanta, excuse me. Let me start that over again. Omega 1 is the number of ways of putting Q1 quanta in block 1, and omega 2 is the number of ways of putting Q2 quanta in block 2. Notice that if there are 0 quanta in block 1, there's only one way to do that, but the natural log of 1 is 0. So the natural log of omega goes to 0 when the number of ways of putting that many quanta in is 1. But as you go to the right, as you increase the number of quanta in block 1, the number of microstates goes up. But at the same time, the number of microstates for block 2 goes down. It starts at a maximum when you have 100 quanta in block 2, and it goes to 0 when you get only 0 quanta in block 2, because there would be only one way to put 0 quanta in block 2, and that would have a natural log of omega 2 of 0. But how many ways are there to put Q1 quanta in block 1 and Q2 quanta in block 2, it's going to be omega 1 times omega 2, because for every configuration of the Q1 quanta in block 1, there are omega 2 configurations of the Q2 quanta in block 2. And so overall, it's the product. So we're looking at the natural log of the product of the two, but the interesting thing about natural logs, of course, is that the natural log of the product is the sum of the natural logs. So if you think of the natural log of omega 1 as a number and the natural log of omega 2 as the number, the natural log of the product is just the sum of those two numbers. So you add those two curves together to get the total, or the natural log of the product, and you can see that the equilibrium is the point where those two curves added together has a maximum. Okay, so it turns out we defined something called entropy. Entropy is related to the number of microstates that are available in a certain macrostate. So in other words, for a given total energy, it's or distribution of energy, it's the number of ways you can have that configuration. We use the natural log of the number of states because it matches, the natural log of the number of states actually matches the historical notion of this concept of entropy. And so we calculate the entropy as a constant called the Boltzmann constant times the natural log of the number of microstates. The Boltzmann constant you're familiar with, I'm sure. It's got units of joules per Kelvin. Some folks use entropy in terms of information theory, and they usually use the natural log base 2 of the number of microstates, and they call it the information. Information and entropy are exactly the same thing. So what happens if our system begins out of equilibrium? Well, let's say we had 90 quanta in the first block and 10 quanta in the second block. Well, it's more likely that it's going to move toward the equilibrium configuration because there's more ways of doing that. And since there's more ways of doing it, that means that if you choose at random a particular configuration, you're vastly more likely to find yourself at equilibrium than in any other place. I also want you to notice that in order to reach equilibrium, the condition is that the slopes of those two curves be equal at equilibrium. Because notice that if the slopes are not equal, then that means that it pays to move in the direction of the line that has the greater slope. So if let's say we were down at Q1 equals 20, the curve for S1 has a greater slope than the curve for S2. That means moving to the right increases the entropy more by increasing S1 than it decreases S2. But if you reach the point where the two slopes are equal, then you don't buy anything by moving to the left or to the right, because the increase and the decrease is going to be the same either way. And so that's the point where you're balanced between the two directions. And so the condition for equilibrium is that ds dq is equal for the two objects. But it turns out ds dq is directly related to the energy, or to the temperature, excuse me, ds dq. And in fact, we're going to define temperature to be the reciprocal of the slope of this curve of S versus energy. Now remember, Q is the number of quanta, but each quanta is h bar omega, so dE is h bar omega dq. So they're directly related to one another. On the other hand, this idea of specific heat capacity is that if you throw some heat into a system, its temperature changes, and the heat capacity is related to the rate at which the energy goes up, or the energy required to change the temperature by some fixed amount. So the way you find the heat capacity statistically is you throw in one quantum of energy, you calculate the change in the entropy on either side of that number of quanta, and then you calculate the change in the entropy to get the temperature, and then you use the change in the energy for a small change in temperature to get the heat capacity. And if you do that process, which so anyway, when you work all that out, it turns out you get a fairly simple result. At low temperatures, the heat capacity goes to 0. At high temperatures, it reaches a limit. It works out to be about 3 Boltzmann constants per atom in terms of joules per Kelvin per atom. So that's kind of a neat universal result, and we're going to check it out in class today. But and of course, at low temperatures, the heat capacity approaches zero in a way that's predicted pretty well by this very simple model. There are more sophisticated models that do an even better job at low temperature, but the fact that the Einstein model does as well as it does is pretty amazing. Now, finally, we're going to do a fun topic. It turns out I want to start working on our quantum computing business and how you actually build quantum computers. And so I want to introduce the idea of an ion trap. An ion trap is basically, this is a particular kind of ion trap called a quadrupole trap, where you have 4 electrodes. 2 of them are positive and 2 of them are negative. And you notice that at any given moment, the field that's produced is unstable. That is, there's a force that tends to push the ion toward the center along one direction, but it tends to pull the ion away in the other direction. The trick of the ion trap is to have the field oscillate quickly so that the 2 directions change places periodically. And here's an example of such a trap that's actually been built. And what I'm going to show in a little bit is a demo. Actually, I'll probably show it in class. We'll do a demo of a visual Python program that illustrates the actual trajectory that this thing has. And so that just gives you a little teaser to think about how it all works out, and we'll see how it looks in visual Python in class. We'll see you then. Okay, welcome back. It's time for lesson 7. We're doing some more statistical mechanics before we wrap up this block. We're going to start with ion traps. I'm going to do that ion trap demo I promised last time but never got around to. We're going to wrap up our discussion of the statistics of different types of particles, and in particular we'll look at a couple of Monte Carlo demos that I cooked up to illustrate the behavior of fermions, bosons, and distinguishable particles. And finally, probably in class today, we'll talk about how you generate random distributions of numbers of various types, not just uniform distributions, but other exponentials and cosines and sines and stuff like that. So that's what's online. Let's start with the demo of the ion trap. We already talked about this in the slides for last time, but let's see what they really look like. Okay, let's see if this works. I want to run a little Python application that simulates this ion trap. So what we have here are the 4 conductors. 2 of them are positive and the other 2 are negative. Every half cycle, then they switch. These guys become positive, these guys become negative. This is the origin of the coordinate system, and that little yellow guy is my ion. So I'm going to start the time, and I want you to notice that first thing you see is that the ion wiggles very quickly. That's the high frequency response to the alternating electric field, but that there's also a low frequency response, which is sort of the average motion over many of the short or the high frequency cycles. And you can see that the thing is bound to a region near the origin. It feels a net restoring force back toward the axis of the system, and then there's also an electric field, a convergent electric field along the longitudinal direction that keeps the thing confined in the z direction, and you can see that it wiggles around. Now the thing I haven't explained is that if you apply a strong, slightly detuned laser field, that has the net effect of producing a damping force. It causes a little bit of radiation pressure, which pushes the thing away from the origin a little bit, but it also causes a damping force. And what I plan to do is to add little bits and pieces of the theory in every couple of lessons, so that by the end of the semester we have a fairly complete picture of how you can build an actual quantum computer using ions in one of these traps. And they can communicate with one another, and you can actually do calculations. So you can see the damping force is sort of causing the thing to die down now, and it's slowly approaching the origin. And that's how it works. Okay, now let's go back to discussing different kinds of particles and the number of ways we can distribute them. So for distinguishable particles, the big Q here is the number of ways that you can distribute capital N distinguishable particles among a set of states where you have little n can be any number from 1 to infinity, and big N sub little n is the number of particles in that particular state, the little nth state, and d sub little n is the degeneracy of the little nth state. So that's the idea. In the distinguishable case, you get this monstrosity. For fermions, it's looks still fairly monstrous, but the difference is you can't put more than d sub little n fermions into into the nth state, and so there's a limit, whereas for distinguishable particles there's no such limit. For bosons there's not a limit either, except that for bosons, if you put 5 bosons in a level that can hold 10, then it turns out there's only so many ways you can do it, but you can't count. There aren't as many states there as there are for distinguishable particles, because if you've got 311, for example, that's the same as 113 or 131 and so on, because you can't tell which particle's in which state exactly. That's kind of the idea. Anyway, there are fewer bosonic states available than there are for distinguishable particles, because they don't have labels. So putting 3 bosons, there's only one way to put 3 bosons in one state, right? You can't, their order doesn't matter, because the order doesn't make any sense, because bosons are indistinguishable particles. Okay, very good. The whole idea is that you want to find the combinations, the distribution of values of big N sub little n that maximize Q. But there are some constraints. For example, we are assuming that there are a fixed number of particles, that the sum of the big N sub little n's has to add up to big N. If you've got 5 bosons, you've got 5 bosons. You can put them in different states, 4 of them in one and 1 in the other, or 3 in one and 2 in the other, and so on. But they still have to add up to 5 all the time. And the same way with the energy. If you take the number of particles in the first state times the energy of the first state, plus the number of particles in the second state times the energy of the second state, and add all those up, you've got to get a total amount of energy that's not allowed to vary. We're not allowed to create and destroy energy. We can just move it around by moving particles around. But the idea is that those two constraints, we want to maximize Q given that we have to maintain those constraints. So one way to do that is to maximize this quantity that I'm going to call capital G, which is the natural log of Q plus alpha times the difference between n and the sum of the n's, plus beta times the difference between the total energy and the sum of the n's times the corresponding energies. Notice that if the constraints are satisfied, the coefficient of alpha and the coefficient of beta are going to be 0 here. This is a trick that was invented by a fellow named Lagrange. You've probably heard of him before. But the idea is you take the derivative of g with respect to n sub little n, and you set that equal to 0. Then you take the derivative of g with respect to alpha and the derivative of g with respect to beta and set that equal to 0, and that gives you your constraints, and it maximizes Q. So the idea is you think of alpha and beta as kind of variables in a space where the n sub little n's can vary and the alpha and the beta can vary, but the derivative with respect to g, the derivative of g with respect to alpha, beta, and n sub n all have to be 0. So that produces some equations that you can solve. If you do solve those, you get these 3 results, that big N sub little n is equal to this first expression for distinguishable, to this next expression for fermions, and to this last expression for bosons. If you divide n sub n by the degeneracy of each corresponding level, you get what's called an occupation probability, or an occupation number. The expected occupation number of a particular level is how much each degenerate state, how many particles each degenerate state is expected to have, and it's called its occupancy. Okay, and so what are the Lagrange multipliers? Well, alpha turns out to be basically a normalization constant. It's related to something called the chemical potential. So, and beta turns out to be, it's related to the energy, and it's also called, or related to, the temperature. So if we redefine the chemical potential to be minus alpha times the Boltzmann constant times the temperature, and we define the temperature to be 1 over the Boltzmann constant times beta, then we can plug all that stuff back in, and we get the occupation number for the Maxwell-Boltzmann distribution, for the Fermi-Dirac distribution, and for the Bose-Einstein distribution. And the mu in this guy is now the chemical potential. It was basically put in there instead of alpha. So that's the idea, and these are the guys you'd use to go and calculate things like the expectation value of the energy of a particle, or the pressure or the compressibility of a material, and based on the distribution of energies and so on. So we'll do that in class today. We're going to use the Fermi-Dirac version to estimate the compressibility of a metal at room temperature, say. And the occupancy of the Bose-Einstein distribution we can use to estimate the heat capacity of a material at room temperature. Now, what I want to show you now is a couple of demos I've cooked up that illustrate how these distributions can come about as a result of a Monte Carlo procedure called the Zeeman algorithm. So I'll describe the Zeeman algorithm here, and you can see how it works. Okay, here's a little example of the Bose-Einstein. This is a graph. X is the energy. Y is the occupation number, basically. And what you have here is the comparison between the Bose-Einstein distribution, which I'm showing here for alpha equals 0, which means that this thing, if you plug in x equals 0, then you get 1 minus 1. This thing blows up. So it's super exponential for small values of energy. On the other hand, the Fermi-Dirac distribution is just a plain old exponential. It falls off nicely. I'm sorry, the Maxwell-Boltzmann distribution, the classical distinguishable particle distribution, is just a simple exponential. And then the Fermi-Dirac distribution is this one. It starts at 1 at low energies, and then it drops to about a half at when the energy is equal to the Fermi energy, and then it drops off. Notice that at high energies, all these guys approach one another. So if the energy is much greater than the temperature, they all basically look exponential. What that means is you can ignore this 1 down here in the denominator, and they all look just like the Maxwell-Boltzmann distribution. You can ignore this 1 for high energy in the Bose-Einstein distribution, and you get the simple Maxwell-Boltzmann deal. But at low energies, the Bose-Einstein is super exponential, the Fermi-Dirac is sub-exponential, and the exponential one is the classical distinguishable particle version. Now, I cooked up some demos here that illustrate how that comes about in a kind of a Monte Carlo way. So I want to see if I can go back here and let's start with the distinguishable case. It's called the Zeeman algorithm. Actually, maybe I should show it to you. Let me just pop it open here. So the Zeeman algorithm, you basically pick a random particle or state, and then randomly bump a particle up or down in energy. And there's this Zeeman. Whenever you take energy out of the system, you give it to the Zeeman. Whenever you want to put energy into the system, you get it from the Zeeman. Now, if the Zeeman doesn't have enough energy, you can't do it. And if the particle doesn't have any energy, if the particle is not in a state that allows you to take energy out, you can't do it. So n sub m here is the number of particles in the nth state, or and E sub d is the energy of the Zeeman. So you just sort of iterate that process over and over again. And what the Zeeman does is it sort of gives you the effect of the particles exchanging energy with one another. Even though you don't have any explicit mechanism for that to happen, you assume there is some mechanism for that to happen. But other than that, you're just insisting on the rules of quantum mechanics, that you count states as boson states or fermion states or distinguishable particle states, and you see what happens. So let's go ahead and run this. for the case of the distinguishable particles, and what you're seeing here is the number of particles in the lowest energy state, the next energy state, the next energy state, and so on. And you'll notice that because I'm just randomly moving energy around, what's happening is the system is naturally evolving to the states that are the most likely, the distribution of energies that's most likely. And you can see that it evolves toward a very nice exponential looking distribution. So that's the Maxwell-Boltzmann distribution. If you do the same thing with bosons, you get a similar kind of behavior, except that the distribution ends up being somewhat super exponential. Now, I haven't done a fit or anything to prove that, and maybe I can get that done before the next class, but I think you can kind of see that this is going up faster than this exponential curve would suggest it would hit over here somewhere, but it's actually going up faster than that. And that's a typical behavior in the Bose-Einstein case, and it's all about what we call a state and how you count that. So that gives you an idea for the Bose-Einstein state. The Fermi-Dirac situation is much more dramatic, so we'll look at that. You'll notice that here the occupation number is 1 for low energies, and then it drops off to 0 for high energies, and there's a sort of a narrow range in the middle where the occupation number falls, and the Fermi energy is right here in the middle, where the occupation number goes through 1/2. The only difference between this and the Bose-Einstein case is that states are never allowed to have more than one particle in them, and that's basically it. So in the Bose-Einstein case, of course, states can have as many particles as they like. So that's the idea. And let's see, was there anything else? I think that's all I have time for today, so we'll see you in class, and we'll do some of those board work calculations I told you about. Okay, finally in class today, you'll actually do on the board. I'll give you some hints and get you started, but I want you to be able to calculate the compressibility of a metal and the heat capacity of a solid material. And that's the idea. We'll talk to you soon. Okay, so let's try this again. This will be lesson number 8, take 2. Had a little confusion about the first try, but I think I've got it all sorted out, so here we go. First of all, I want to discuss a technique for generating an essentially arbitrary collection of random numbers. So we already know how to generate random numbers that are uniformly distributed, say between 0 and 1. And we know if we wanted a distribution between 0 and 5, we could just multiply all those numbers by 5 and we would get such a distribution. If we wanted a distribution between 1 and 8, we could multiply by 7 and add 1, and that would produce such a distribution. So uniform distributions are straightforward. But what if we want a distribution that isn't uniform, but has some sort of higher density of probability in one area and a lower probability density in some other area, such as we find often in quantum mechanics, for example? So here's an example of a distribution. It's called a Lorentzian. I just sort of pulled it out of the air as an example. There are zillions, literally, of different possible distributions you could imagine. Basically, any mathematical function that you could normalize could be used as a distribution function for random numbers. And I just wanted to give this thing a try. One thing we have to do is to normalize it, so we have to figure out what this number A is. And we can use our favorite symbolic algebra package to do that. We'll show you here. Okay, so here's my favorite symbolic algebra package. I'm going to define a function. I'll call it f. And what we're going to try to do is see if we can integrate that guy. And the way you spell integration in Sage, this is the open source package that I use sometimes, is integrate, and I'm going to integrate this function I've defined from -infinity to infinity, and Sage tells me that that's equal to pi over a. So I'll go ahead and redefine the function now, as the same thing it was before, except now I replace the 1 with a over pi. That means that when I integrate, I'll go ahead and tell it to integrate, I get 1. So that tells us that indeed the normalization constant is a over pi. And we discover that the proper normalization is a over pi, where a is a measure of the width of the distribution, and of course pi is pi. Now, we start with that distribution. The question is, how can I use that to generate random numbers that have that distribution? And in order to accomplish that goal, it's useful to introduce the concept of a cumulative distribution function, which is related to the probability density. It's the integral from minus infinity to x of the probability density. And you can see what it does is it gives you the probability of having a number between negative infinity and x. If you think about it, that means that if the distribution is normalized, you got to get a number between 0 and 1. So let's look at some properties of that guy. So now that we see that it's normalized, we want to define the cumulative distribution function, which is the integral of f of x from minus infinity to x. Of course, in order to make a function of x, I want to integrate over a different variable, so I'll integrate over z. And let's see what that CDF looks like. Here we go, CDF. It's a mapping of x to the arctangent of x minus b over a, all thing divided by pi plus a half. I could rewrite that, I suppose. Let's see, if I say CDF of x, it comes out looking just like a function. Anyway, I've gone ahead and made in the grapher application a function that does that. This is my cumulative distribution function, and here is my original probability density. I've turned a into a thing I can fiddle with, so if I adjust a, you see that affects the width of the distribution, but I always get a normalized distribution, and all that happens to the CDF is that it becomes sharper. If I make a very sharp distribution, the CDF goes from 0 to 1 over a very short range of x. If I make a bigger, it goes from 0 to 1 over a longer range of x. Now, here's the interesting part. What if you imagine generating a random number that is uniformly distributed between 0 and 1? So all these random numbers are going to correspond to different heights. And if I use the CDF to map back from that uniform distribution back down to x, so there's a mapping here between x and the CDF. If I run that thing backwards, I invert the CDF, then my uniform distribution of random numbers maps from 0 to 1 all the way back to the x-axis. And in this case, it's x goes from minus infinity to plus infinity because the CDF is defined over that whole range. The interesting thing is dy here, if I think of this as the y direction, dy is equal to the derivative of the CDF times dx, and but the derivative of the CDF, is the probability density. So if I have a small range of y's here with some probability, I'll have the corresponding range of x's here with the probability equal to the probability density, the derivative of the CDF. So that's why I can invert the CDF and take a random number in the range 0 to 1 and convert it to a random number pulled from my original probability distribution. And what we discover is that if you start with a random number r that's uniformly distributed between 0 and 1, and you take the inverse of the cumulative distribution function of r, the result of that inverse function is distributed as the original probability density p of x. And we can see how that works. Okay, now I have a very simple program. We're going to generate 100 random numbers from 0 to 1, and I'm going to define a and b as I did in the grapher application. If I do this calculation, this is the inversion. I'm inverting the cumulative distribution function, and I'm calculating a bunch of x's based on these random r's that I calculated up here. And then I'm just going to histogram those guys and show the histogram. So let's run that. And you can see what I get. It looks like some kind of a distribution that's centered around 2, but it's not at all obvious that that's Lorentzian. Let's try bumping the number up a little bit. Let's try 1,000. And that's looking a little better. Let's go ahead and try 10,000. Now we're getting something that's definitely looking Lorentzian. Let's try 100,000. Okay, now you can clearly see the curve. And finally, let's just try 1,000,000 for the fun of it, just because we can. So let me close that. Try 1,000,000. I think I can. Hang on. Oh, I got to make that active. There we go. There's 1,000,000. And now it's looking quite nice. So you can also see how fast it is. The NumPy random number generator is extremely fast, and it's extremely good. So we shouldn't have any trouble with that. Now, the next technique I'd like to talk about is something called rejection sampling. The idea is that you want to generate random numbers according to a probability density P2, and you already know how to generate random numbers according to a probability density P1. Can you use your knowledge of P1 in order to generate P2? And the idea, of course, P2 in this graph is meant to go to 0 at 1.5 and 2.5. I just couldn't easily get it to not go below 0 with straight lines, and so just ignore the parts that go below 0. P2 is 0 up to 1.5, and then it's a linearly increasing function, then it's a linearly decreasing function, then it's 0 from 2.5 on. So that's the intent there. How could I generate that distribution if I know how to generate the distribution P1? The idea is you pick a random x according to the distribution P1, and then you reject it or accept it depending on the value of the ratio of P2 to P1. So obviously, because of the way we've cooked up P2, it's always less than P1 everywhere. It's not normalized, but it's a function that's less than P1 everywhere. And so if I accept the x value with the probability that's equal to the ratio of P2 to P1, you'll notice that what I'm doing is throwing away some of the x's from the P1 distribution in such a way that the x's that I accept will automatically have the distribution P2. That's the idea. So you accept x sub I with the probability equal to P2 divided by P1. And you reject the other one, since that's why it's called the rejection sampling scheme. Let's get a demo of how that's going to work. So this is the rejection method, and here we have the P1 probability and the P2 probability, which you recognize. Here's the Lorentz generator encapsulated as a function. Here I have a list of results that I'm collecting, and then the idea is I first generate x random numbers according to the Lorentz distribution. Then I compute the ratio P2 to P1, and I keep those where a random number is less than that ratio, a uniformly distributed random number between 0 and 1. If it's less than that ratio, I keep them. If it's not less than that ratio, I just ignore those guys. And then I'm going to calculate here, the first time through, I'm going to calculate the fraction of the numbers that I accept. And I'm going to use that to predict how many new numbers I need to generate in order to produce the number that I want. So I add the new x's to my list of results. Then I generate a new n, which is the number I need to request in order to get the number that I want. And notice I take the difference between the number that I want and the number that I have, divided by the acceptance fraction, which means, let's say I got 70% the first time. If I divide that by 0.7, then that'll give me a big enough number that I should get it in the next go. So hopefully this only runs once or twice at the most. Maybe occasionally it might run 3 times, but most of the time you'll get it in two shots. And then I just make a histogram of the results. So let's try that. I'm going to ask for 100, and let's see what we get. And we get something, you can see it's sort of distributed between 1.5 and 2.5, but it's not looking terribly triangular. Let's try with 1,000. And this time it's getting more triangular. How about 10,000? Now we're getting a decidedly triangular sort of look. Let's try 100,000. Now with the 100,000 numbers, you can definitely see that triangular nature there. So it's clearly working. We'll go up to 1,000,000 just for grins. And there you have it. 1,000,000 random numbers distributed with this triangle shape. Fascinating. Very good. So next is the Metropolis algorithm. I had incorrectly labeled the rejection sampling Metropolis algorithm before. I apologize. The Metropolis algorithm is slightly different, although it's slightly similar. And because of the similarities, I had mixed it up in my head. And but now I've got it all straight. If you start with any distribution of x's, and then you give them a little bump. So you just give them a little random kick, move them around a little bit, and then if the new probability, if the probability of one of the bumped x's is greater than the old probability, in other words, you take the probability density function you want to produce, and you compare the probability at the new x to the probability at the old x. If it goes up, you accept it unconditionally. Now obviously if you've got 1,000 x's and you bump all 1,000 of them, some of them are going to go up in probability, some of them are going to go down. The ones that go up, you take. The ones that go down, you accept with a probability equal to the ratio of the new to the old. Now, you only do this for the ones where p new is less than p old, so this probability will definitely be less than 1, which is good for a probability. And so it turns out you'll reject the ones where the new probability goes down a lot. But if the new probability only goes down a little bit, you'll generally accept those guys. And so, and you can prove, which I'm not going to prove because I don't have time for that, but you can prove that if you do that for a long period of time, that on the average, the x's will distribute themselves according to the probability distribution that you wish to produce. So we'll get a little demo of how that works. Okay, so here's the Metropolis algorithm. Here's the basic idea. We start with a certain number of random numbers, and we're going to iterate this many times. This is the size of the bump when I bump them on each time step. I still have the parameters of my desired probability distribution, but now I no longer have any other probability distribution, just the one I'm interested in. And here's the function that shakes the numbers up. You just add a Gaussian with the width of delta, and that shakes them around. I'm going to keep track of the acceptance ratios, the fraction that I accept. I'm going to start with a uniform distribution between b minus a half a and b plus a half a, roughly. And no, I'm sorry, b minus a and b plus a, just a little tiny bit less than b minus a to b plus a. And I can evaluate the probability at the current x's just by applying x to the function. And I'm going to make a histogram of where everybody is. And here, these two guys, I can either display the histogram every step, or I can accumulate the histogram every step, or I can just wait till the end and accumulate it at the end. So if these are both 0, I just wait till the end. Otherwise, I'm displaying the particle histogram on every step. Here I display the accumulated particle histogram on every step. And basically this just executes the Metropolis algorithm. You shake up the x's, you calculate the probability of the new x's, you take the ratio of the new probability with the old probability. If that ratio is greater than 1, you definitely accept it. If it's not greater than 1, you accept it conditionally. And the condition is that the ratio is less than a random number. So here's the ratio. You check to see if a random number is less than that ratio. Sorry, I had it backwards. You check to see if the random number is less than the ratio. If it is, you accept. If it isn't, you reject. And that means that if the probability goes down just a little bit, chances are you'll accept it. But if it goes down a lot, you probably won't accept it. And then you just iterate that over and over again, and that's all this code does.
You can display at every step, display accumulated over the entire run, or you can just wait till the end. That's what these guys do. So the details aren't that critical at this moment. I just want you to understand the idea. So let's go ahead and run it. At the moment I have this thing set up to show the histogram every step, so I'll get this out of the way and we can watch it. Notice it started out as a uniform distribution, and you can see that random numbers are bouncing around, and they look like they could very well be semi-triangular. But let's bump the numbers up a little bit. Let's go to 10,000 particles, and you can see now it's looking much more triangular. But still, you can see there's a lot of variability in there, and it's hard to tell if the average really works out to be triangular exactly. So let's see what happens if I show the accumulated histogram. In other words, now every time step we're going to add the histograms together, and you can see what happens to the overall histogram. Notice the scale is getting bigger now because we keep adding the histograms together. But look at what's happening to the sides of our distribution. It's straightening out nicely. And let's bump up the number of iterations a little bit. We'll go to 100,000 particles, and let's go for like 1,000 iterations and see what happens. Now you can really see the thing becoming triangular. So that's how that works. Let's go ahead and change it so that it just shows us, goes ahead and accumulates over all time. Just show us the answer. Don't bother us with the animation in the middle, and we'll see what happens. Hopefully this won't take too long. There we go. Okay, beautiful. And also this way we get to see the acceptance ratio, and notice that the acceptance ratio is somewhere in the neighborhood of 70%, a little more than 70%. So you get the idea that most of the time we accept. All right, and that's how it works.
Finally, I just want to introduce you to the concept of quantum Monte Carlo, diffusion quantum Monte Carlo. It's just a trick, basically, that enables you to use Monte Carlo techniques to estimate quantum wave functions. Generally, quantum wave functions of ground states, but it is possible through various tricks to do excited states as well. But let's just discuss the concept. If you take the time variable in the Schrödinger wave equation and you make it imaginary, the Schrödinger wave equation is suddenly transformed into a real differential equation. It happens to be exactly the diffusion equation. You can use Monte Carlo techniques to solve the diffusion equation by simulating the diffusion process. And in the end, the density of the diffusing particles in the diffusion equation turns out to take a shape that's exactly the solution to the diffusion equation. And of course, if the Schrödinger wave equation is written in such a way that its solutions become solutions to the diffusion equation, then you can generate solutions to the Schrödinger wave equation by solving the diffusion equation using a Monte Carlo technique. That's the idea. And that's the whole show. I hope it was somewhat useful, and we'll see you guys next time. Hey guys, welcome back. It's time for Lesson 11. We're going to start with time-independent perturbation theory and a little more about ion traps. So let's get started. The whole idea here is, let's suppose we already have a problem we've solved, like the simple harmonic oscillator or the hydrogen atom or the infinite square well, and we want to add a little change, not a big change, but a small change to the original Hamiltonian. So h hat is going to be our full Hamiltonian, and h0 hat is the original Hamiltonian we started with, the one we already know how to solve, and h1 hat is going to be some small change that we're going to make to the Hamiltonian. So like a bump or a little added force or a little added potential energy, something like that. And the idea is to expand the quantum states
of the perturbed Hamiltonian as a superposition of the known solutions to the unperturbed Hamiltonian. So we're going to think of the perturbation as changing our solution states from being the original states to the original states plus some little bits and pieces of the other states, because we know that any state can be written as a superposition of the solutions to the original Hamiltonian. So thinking that we could use the solutions to the original Hamiltonian as a basis to describe the solutions to the perturbed Hamiltonian seems like a reasonable place to start. So the idea is the energy of the perturbed states, we're going to think of it as kind of like a power series or a Taylor series, something like that, where the zeroth term is the original energy, the unperturbed energy, and then there's the first order correction and the second order correction and the third order correction, which we'll have to add to that in order to get the solution to some level of accuracy. And the idea is that if the perturbation is small, you don't have to do very many terms in this series to get an idea of the effect. Okay, the superscripts here I need to point out are not exponents. So E0 is not e to the power 0, it's just the zeroth order or the original energy of the unperturbed Hamiltonian. And E1 is a first order correction. So you could think of that as something that's, say, linear in the perturbation. That's the idea. And we'll see exactly what that means here in a minute. So the idea is that you think of the solution to the perturbed Hamiltonian as the original state plus a little added bit, that's the first order correction, and then a little even tinier bit, that's the second order correction, and so on. And of course, the problem we want to solve is the Hamiltonian acting on the nth solution is equal to the nth energy times the nth solution back again. But we can put in what we know the energy eigenvalue is going to be in terms of its perturbation components, the zeroth order, first order, second order, and also put in what we expect the solutions to be, the superpositions of the different orders of the solution to the perturbation, and we get a new eigenvalue equation. And the idea is to multiply this thing out and then collect terms of like powers. So for example, the zeroth order term, you take the zeroth order terms from the left-hand side and the zeroth order terms from the right-hand side and see what you get. Of course, what you get is that the original Hamiltonian acting on the original state is equal to the original energy times the original state again. That's just a statement of the eigenvalue problem for the unperturbed Hamiltonian. So that's clearly okay. Then you say, well, what's the first order situation? Well, there's two first order terms. There's the original Hamiltonian acting on the perturbed state, and there's the perturbation acting on the original state. And that's got to equal to the unperturbed energy multiplied by the perturbation, the first order perturbation, plus the perturbed first order perturbation of the energy times the unperturbed state. So notice that each of those terms, if you add the orders, they add up to 1. So that's kind of the idea. And you can get the same thing for the second order. You get the unperturbed Hamiltonian on the second order correction plus the first order Hamiltonian on the first order correction is equal to the original energy times the second order state plus the first order perturbation of the energy times the first order perturbation of the state plus the second order perturbation of the energy times the original state. That's hard to say, but it's easy to see what's going on. Okay, so let's collect some of this together and see if we can get any answers. The first question is, what's the situation with the first order perturbation to the energy? So the idea here is if we multiply on the left by the unperturbed state, what we get is if we multiply everything out, notice that first term on the left, you can multiply the unperturbed Hamiltonian to the unperturbed state on the left, and you get E0, the unperturbed energy, times N0 on N1. Then the middle term, there's not much you can do with that. This term on the right, the first term on the right, notice that the E0 that's just a number. It's the original unperturbed energy, so it comes out, and you get N0 and N1. And then E1 is also just a number, but it's multiplied by N0 on N0. But of course, N0 on N0 is just 1. And the term that we had out in front, the E0 on N0 inner product with N1, shows up on both sides of the equal sign. So it cancels. And what you get is that the inner product, or I should say the expectation value of the perturbed Hamiltonian, the perturbation part of the Hamiltonian, in the original unperturbed state is the first order perturbation to the energy. So that's an important result. That's our first real result of perturbation theory. And basically what it says, you can read it, the perturbed energy is the expectation value of the perturbation Hamiltonian in the unperturbed state. Very nice. That's kind of even easy to remember. And we're going to do a board work problem today where we'll work that out for a concrete example. So what about the first order perturbed state? Let's go to see if we can calculate the some kind of a superposition for N1. And we'll go back to the first order correction that we wrote out earlier. And what I want to do is to take the inner product with some other state, let's call it M0, that's not the, so I want to find an expression for the correction to the eigenstate of a particular state, and I want to take the inner product with a different unperturbed state. So for example, if I wanted to find the perturbation of the ground state of the infinite square well, I would take the inner product with some other state, not the ground state, maybe an excited state of some kind. And what you find is the following thing. Again, you can apply H0 on the left and get the mth unperturbed energy. The middle term, there's not much you can do with that. It's just something you need to compute. It's an integral of some kind. The perturbation integrated sandwich between the mth and the nth unperturbed state. And then, of course, on the right-hand side, these energies are all just numbers, so they come out. One thing I want you to notice right away is that M0 and N0 are different unperturbed states, and they generally are orthogonal to each other, so we can get rid of that. And you notice that if we fiddle around with that a little bit, you've got an M0 on N1 on the left, you've got an M0 on N1 on the right. You can move those guys over to the left-hand side, move the M0 H1 on N0, and solve the thing for the inner product of M0 on N1. This tells you how much of the mth, not the nth, but the mth original unperturbed eigenstate is in the perturbed state N1. And notice that it's proportional to this inner product of the perturbation between the unperturbed states, and there's a denominator here. It's sometimes called the energy denominator, and it's the difference in energy between the two states involved in the matrix element, in this inner product calculation. And so what I want to do now is to go back and rewrite N1 is the identity times N1. But the identity is the superposition. Remember how the identity worked? It's the superposition of all the basis states of the ket times the bra. But I want to exclude the original unperturbed state because I have assumed all along that I'm going to ignore any component of the unperturbed state in the value of N1 because N1 is the change of the state, and of course I'm already adding it to the unperturbed state, so I don't want to include any component of the unperturbed state because I've already got it in there. So the point is the sum is not a complete sum, but it's only the sum over the states excluding the original unperturbed state it started with. And if you plug all that in, you put in the result we just got for M0 and N1, and you get the following result. That the perturbation to the state is m0 times m0 on h1 acting on n0. So it's this. It's sort of like the identity, except it's not, because there's this perturbation and I have to divide by the energy difference. So it's a little more complicated. Probably worth doing a few problems just to kind of see how that works, but it gives you an idea of how to compute the new state in the presence of this perturbation. Okay, and how do we get the second order energy? It's basically the same kind of deal, except now we use that second order line that we started with on the first slide. Again, we take the inner product with n0 and we multiply it all out, and we see what we're left with. The first term, again, we apply h0 on the left. The middle term, there's not a lot we can do with that. These guys on the right are all just numbers, so we can pop those guys out. And let's see what we've got there. First of all, the E0 on the inner product of N0 and N2 is the same on both sides, so it goes away. We also see that N0 on N1 is 0. Remember, N1 is a superposition of only states that exclude the unperturbed state, N. And N0 on N0 is just 1. So we get out of this an expression for E2. Now this is even easier in a way. E2 is the expectation value of H1 between the unperturbed state and the perturbed state. But we can put in our expression for the perturbed state in terms of the unperturbed states. We just worked it out. Plug that into the expression we just got for E2. Take the sum out to the outside, and notice that what we have is N0 H1 M0 times M0 H1 N0. Those are just complex conjugates of one another, so I can simplify the expression by simply calling this the magnitude squared of that quantity, and that gives us an expression for the second order correction to the energy. Looks a little complicated. Again, with some practice, you'll see how this actually comes out. Next time, not today, but next time we're going to talk about what happens if we have degenerate states. So we've assumed that the original unperturbed eigenstates are all non-degenerate. This would be true if it was a one-dimensional problem. In a higher dimensional problem, like the hydrogen atom or the two-dimensional simple harmonic oscillator or something like that, you often have cases where you have states of degenerate energy, and you see we're going to run into trouble with that denominator if we permit states of degenerate energy. So we have to be a little careful in those cases, and that requires a whole nother day to think about. So we'll do that next time. I don't want to give you guys too much in one day. And I do want to, though, point out a little bit more about ion traps. Remember, we talked about a potential. If you have a potential that satisfies Laplace's equation, the sum of the coefficients of the quadratic terms has to be 0. But if you throw in a oscillating factor, like cosine omega t, you can make the thing stable. And I want to keep marching down the road of getting you guys plugged into how that works. Let's go ahead and compute the electric field, take the gradient of the thing, then put in Newton's second law. The mass times acceleration is equal to q times e. Of course, we just worked out e, so we can write that out. And then I want you to remember about this demo. So I'll run the demo again here briefly. And let's look at the actual motion of the guys in the presence of this oscillating field. Okay, so here we are looking at our ion trap again. I'm going to turn on the time. And I just want you to notice that there's a kind of a slow motion of the ion. But if you look at it closely, you'll see that there's also a high frequency sort of wiggle that's going on. I would call that the fast motion. And so the idea of the approach we're going to take is to separate the fast motion from the slow motion. The slow motion is sort of the drift of the ion back and forth. The fast motion is this little wiggle that's going on. And that's the idea. Okay, what you noticed, I hope, is that you've got really two motions. There's sort of the slow drifty motion of the ion through the field, and there's the fast wiggly motion that's in response to this cosine that's wiggling very quickly. And I want to think of R as being a superposition of a slow part and a fast part. Now the fast part, if you plug that into Newton's second law and take mr double dot, the fast part is going to have a bigger double dot than the slow part because it's just got a lot more acceleration. It's wiggling like crazy. That's that wiggle that I want to think of as the fast part. If I take the second derivative, I'm going to get something like minus omega squared times the fast part again. So let's look at that. I'll neglect the slow part compared to the fast part when I take the second derivative. And that means for our mr double dot, I can just put in minus omega squared times the fast component of the motion. And if I break out the x and y components of this equation, I can solve for the fast and the slow component, or the fast x and the fast y components of the motion. You can see that the magnitude of the fast part is inversely proportional to the frequency squared. But the other thing I want to notice is that the amplitude of the fast part is proportional to how far the ion is from the origin. So I want to pull the demo back up again here briefly and point out that it also follows that basic behavior. Okay, real quick, I just want to point out one other thing and just show you that it works out the same as our model. If you watch the amplitude of this motion, notice that when it crosses near the origin, the amplitude becomes quite small. So it is true that the amplitude of the fast motion goes to zero as the particle passes close to the origin. So that gives us some hope that the thing is valid. All right, here we are at lesson 12. Hard to believe. It's time for perturbation theory again, but this time we're going to deal with the case when the eigenstates we start with are degenerate. And you may remember that that's problematic with just the perturbation theory we worked out last time, because there was this denominator that had the difference between the energy that of the state you started with and the energy of the other states. And if you're incorporating a state that has the same energy, then you're going to have trouble. And we're also going to talk about ion traps again. We're going to deal with the slow motion. Last time we dealt with the fast motion. Now we're going to deal with the slow motion. So let's get started. So the idea is, what if we have two states in the unperturbed system that have the same energy? So for example, you've got state A that has the energy E0, and you've got another state, state B, that also happens to have the same energy. A superposition of these two states also happens to be an eigenstate with the same energy. So these two states, in fact, form kind of a subspace that of the full solution that have all the states that have the same energy. They're like a two-dimensional subspace that happens to have the same energy. If you have a superposition, then that superposition also has the same eigenvalue of energy. So you can imagine what happens if I have a perturbation. So I add a perturbation to the original Hamiltonian. I still have the what you call eigenvalue problem, but notice that I can throw away the unperturbed part because it already solves its own eigenvalue problem. And what I get is kind of a new eigenvalue problem with the perturbation acting on the superposition and the correction, the first order correction to the energy times the superposition. And we can work out what that means. So for example, if I factor out H1 and then take the inner product with psi A again, I get this equation. Now notice that psi A H1 psi A, that's just an integral I can do. It's a number. Psi A H1 psi B, that's a different integral. These things are called matrix elements, but they're basically just numbers. And psi A on psi A, of course, is 1. And I can do the same thing with psi B, and you can see that, again, I get A times this number plus B times another number is equal to B times the correction to the energy. And when I put those two equations together, you can see that, in fact, what I have is a system of equations just two linear equations with two unknowns. And I can solve that with linear algebra. I can think of that as a matrix, which with these matrix elements times the vector AB is equal to the correction to the energy times the vector AB. Does that problem look familiar to you? Of course, it's the eigenvalue problem. It's the same problem we solved last semester when we were dealing with finite systems with finite number of states, like the ammonia molecule or the spin of an electron. We ended up with these finite matrices, and the eigenvalue problem is basically the way you find solutions to the Schrödinger equation. At this point, we're looking for simultaneous eigenvalues of the original and perturbed Hamiltonians. You know that any superposition of the two originally degenerate states is going to be an additional degenerate state, and so we're looking for superpositions of the degenerate state that also happen to diagonalize the perturbation. In other words, that are solutions to the eigenvalue problem for the perturbation. That's the idea. And the eigenvalues we get from this eigenvalue problem are going to be the first order energy corrections. Now that's all kind of abstract, so let's do a concrete example. Let's imagine we have a two-dimensional simple harmonic oscillator with the potential that you guys all know, and we throw in a perturbation that messes it up. So this particular perturbation I'm imagining is the product of x times y. And you can generate that by adding an electric field that solves Laplace's equation, and we can talk about that at some other point, but let's just imagine we have this potential that we are adding to the original isotropic two-dimensional simple harmonic oscillator, and gamma is just some number that has units of energy divided by length squared, but it's small compared to the typical energies you'd find in the simple harmonic oscillator, let's say. Small compared to maybe h bar omega. And so let's march ahead. Now let's look at the ground state. The ground state of the system is singular. There's only one. It's not a degenerate state, so we can just use regular old perturbation theory to deal with that one. So I'm going to ignore that for the moment, and let's look at 1, 0, and 0, 1, and see what happens to those guys. Now they are degenerate. 0, 0, of course, has the energy h bar omega over 2. 1, 0, and 0, 1 both have the same energy, 3/2 h bar omega. And so they're degenerate states. Let's just call the one where the x direction is excited and the y direction is in the ground state A, and we'll call the one where the x direction is in the ground state and the y direction is excited, let's call that B. So psi A and psi B form a little subspace of degenerate energy eigenstates, and any superposition of those two is also degenerate with both of those guys. So we can think of a superposition as being a little bit of A and a little bit of B. You can think of it in linear algebra terms as a vector, with the top element is the coefficient of psi A and the bottom element is the coefficient of psi B. And just as we worked out a few minutes ago, you can imagine solving the eigenvalue problem, which is the perturbation acting on the superposition is equal to the first order correction to the energy acting on the superposition. So let's work on that. We need to find these matrix elements, AA, AB, BA, and BB, but now we have a concrete perturbation, so let's go in and compute them. If I put the perturbation in, it's x times y. But remember, x is a plus plus a minus, and y is a plus plus a minus. Of course, they're individual raising and lowering operators that act only on the x and y parts, but that's how they go. And you'll notice that since I have the same state on the right and the left, that this thing has to be 0, because a minus on 1 gives you 0, but I've got 1 on the left, and a plus on 1 gives you 2, but I've got 1 on the left, and that, so both of those are going to give me 0. Same thing with the y direction, so I get nothing out of H1AA. But what about H1AB? Here, the a plus x on the left is going to act on 0 on the right-hand ket, and it'll give me a 1. But there's a 1 in the left-hand ket, so that is not nothing. In fact, the x and the y operator in this matrix element each give you 1, And so the answer turns out to be gamma x0 squared over 2. And by symmetry, HBA is equal to HAB, and HAA is equal to HBB. So now I know the 4 elements of my matrix. I can go ahead and write those out, and they look like this. So now the plan is I rewrite this by moving the E1 to the other side of the equation, and I get the eigenvalue determinant has to be equal to 0. And you can see that that means that E1 squared has to be gamma x0 squared over 2, which means E1 has to be plus or minus gamma x0 squared over 2. So now we have our 2 eigenvalues. These are the 2 eigenvalues that solve the eigenvalue problem. So if I stick these eigenvalues back into the original equation, it's fairly easy to show that if E1 is plus gamma x0 squared over 2, then the solution has to be A and B are equal to one another, which means that you get the solution psi plus, which is the sum of the 2 eigenstates, A and B. And if you put in E1 is minus gamma, then you get psi minus is the difference, and A is equal to minus B, in other words. And so if you graph the energy of those guys as a function of gamma, essentially, you see that psi plus goes up in energy, psi minus goes down in energy. So the point is that this perturbation breaks the symmetry of these degenerate excited states, 1, 0 and 0, 1, and makes them into 2 different states with different energy. So that's the idea. Okay, now back to ion traps. Now you may remember we worked out last time the fast motion, and we did it by taking the potential, the time-dependent potential, and sticking it into Newton's second law, separating out the slow and the fast motion, and then making the claim that the second derivative of the position of the fast motion was much, much larger than the second derivative of the slow position. And we got, as a result of that, the fast position as a function of time in the x direction and the y direction. Now notice there's a sign difference here between x and y, and that is significant. If we put this fast motion back into the equation, and then what I want to do is to average this differential equation, Newton's second law, over one full cycle. Notice that there's a sign difference in the fast solution for x and y, and there's also a sign difference in the electric field for x and y. The x has a minus sign in the electric field, the y has a plus sign in the electric field. But if we average all these pieces over one cycle, let's see what we get. So if we average the slow second derivative over one cycle, remember the slow motion doesn't have the high frequency omega in it, so when you average over one cycle, you don't get a big change. It's basically just the second derivative of the slow motion. On the other hand, if you average the fast second derivative over one cycle, it does have the cosine omega t in it, and the average of cosine omega t is 0. So you don't get anything from from averaging the fast motion over one cycle. Now what if you average the x slow motion times the cosine of omega t over one cycle? Well, the slow motion doesn't have any high frequencies in it, so if you multiply the slow motion by the cosine of this high frequency, you're not going to get much, because you're going to get a full cycle of a cosine times something that's almost constant, and that's going to give you 0. But what happens if you average the fast motion times the cosine of omega t? Well, if you put the solution in for the fast motion, remember the fast motion has a cosine in it already, and if you multiply by cosine, you're going to get a cosine squared. Now the average of a cosine squared over one cycle is not 0, because cosine squared never goes below 0. And so you can put in for the average of cosine squared just a half. Notice also that the fast amplitude was proportional to the slow position. So what I wind up with is a constant times the slow position. And similarly, if you put in the y fast motion and average it times the cosine of theta, cosine omega t over one cycle, you get a constant times the slow y coordinate. And notice again there's a sign difference between the x and the y. But if I put this average back in to Newton's second law, the sign differences in the electric field and the sign differences in the average of the fast coordinate over a full cycle combine so that now there's no sign difference between the two sides. X and Y both have a minus sign overall. And notice that what we have is minus a constant times the slow coordinate I hat plus the y coordinate j hat. But that's nothing other than the r vector, the slow r vector. So what we really have is rs double dot is minus a constant times rs. Well, that you'll recognize is the recipe for simple harmonic motion. So what we get is rs is minus omega squared, capital omega squared times rs, and I'm sorry, rs double dot is minus capital omega squared times rs. Omega is the square root of all that junk, and we get the solution that the slow motion is simply the original coordinate, the position coordinate, times the cosine of omega t plus phi. And of course there could be a velocity term in there, I guess, but anyway, you get the idea. The point is that what we have is simple harmonic motion. The initial conditions determine, well, the phi. The phi gives you the initial conditions. So that tells you the whole story, and that's all there is to it. Hey guys, it's time for lesson 13. We're going to be applying some of the things we've learned about perturbation theory to a few situations that we sort of left from the hydrogen atom, but we didn't deal with. So the theory of the hydrogen atom that we used last semester ignored the fact that the speed of the electrons is borderline relativistic, and the fact that the electron in the hydrogen atom has a spin and an associated magnetic moment. And as a result of having a magnetic moment, it can interact with magnetic fields. Now you might think, well, there's no currents around, there's no sources of magnetic field around, so what relevance does that have? And the answer is, in the frame of reference of the electron, there is a magnetic field. And the magnetic field comes from the electric field of the proton. So we'll talk about that more in a minute, but let's start with the relativistic correction. So it turns out that the kinetic energy that we used to solve the hydrogen atom looked like this. It's the classical kinetic energy, p squared over 2m, and it's wrong. It's wrong because the actual kinetic energy is the total relativistic energy minus the rest energy. And so we ought to use this expression. Now there's a way to do that, which is you cook up something called the Dirac equation and you solve it. But that's way beyond the scope of what we're going to do this semester. So one way to deal with it is to say, well, what if I treat that square root as a power series? So what I'm going to do is notice that the square root of 1 plus x squared you can expand as a Taylor series, and it's 1 plus x squared over 2 minus x to the 4th over 8, and so on. Then if I put in x is pc over mc squared, I get that k is the classical kinetic energy, and then I have to add in a few corrections, and of course if I want to get it exact I have to add an infinite number of corrections. But what we're going to find is that these corrections become extremely small extremely quickly. So, for example, K0 is the kinetic energy of the electron. That has the same order of magnitude as the total energy of the electron. It's about 13.6 electron volts in the ground state, something like that. So we'll call it 10 electron volts. And then K1, the first correction to the kinetic energy, goes like p squared over m cubed c squared, and then the next correction goes like p to the 6th. So let's look at the size of these things. K0 is around 10 electron volts, mc squared is like 500,000 electron volts, and so the ratio of K1 to K0 is the same as the ratio of the kinetic energy of the electron classically to the rest energy. And that kind of makes some intuitive sense. Then notice that because k squared goes like p to the 6th, the ratio between k2 and k1, the second order correction and the first order correction, is also order of magnitude k0 over mc squared. But what is k0 over mc squared? Well, it's something like 10 to the negative 5. And so what that means is that K1 is about 1 part in 100,000 of the classical kinetic energy, and K2 is something like a part in 100,000, 2 parts in 100,000 of that. So we're going to worry about the first correction, but we're not going to worry about the second one because it's 100,000 times smaller, or 50,000 times smaller. So we'll worry about K1. We're going to forget about K2. So let's throw K2 out and focus on K1. K1 is p squared, basically, over mc squared. Of course, there's another m squared in there. So we want the expectation value of K1 in the state of the electron, the first order correction of perturbation theory, the first order correction to the energy, is the expectation value of the perturbation in the state that you're interested in. And so what we're after is the expectation value of p to the fourth, essentially, in any particular state of the hydrogen atom. Now, the interesting thing is p to the fourth, you could think of it as the original Hamiltonian, the unperturbed Hamiltonian, plus the negative of the potential energy. Now remember, the original unperturbed Hamiltonian is the kinetic energy plus the potential energy. So if I subtract the potential energy, I've just got the the kinetic energy, which goes like p squared. And so H0 minus the potential energy squared is going to be proportional to p to the fourth. And why is that useful? It's useful because I can use it to figure out a way to compute the matrix elements of p to the fourth using the known matrix elements of the original Hamiltonian and the potential energy. So that's what we're going to do. So we square that thing. We're going to get 3 terms. We're going to get an H0 squared, we're going to get an H0 divided by r, and we're going to get a 1 over r squared. So the H0 squared is easy because that's just the square of the unperturbed energy. Then the next thing we have to worry about is the H0 times 1 over r. But of course H0 is just the unperturbed energy, and so that reduces to the unperturbed energy times the expectation value of 1 over r. But of course there's a thing called the virial theorem that allows you to know that the expectation value of the potential energy is minus twice the expectation value of the kinetic energy. You might have done the virial theorem when you were taking your analytical dynamics class. But anyway, you can look it up. It's a neat little theorem. The relationship between kinetic and potential energy has to do with the power of r in the potential. And for potentials that go like 1 over r, it turns out the potential energy is minus twice the kinetic energy, something like that. Anyway, there you can easily calculate this just using the virial theorem. You don't even have to do an integral. But the last term is the 1 over r squared term, and for that you do need to do an integral. The integral turns out to be like this. It has an L plus a half in the denominator and an n cubed down there. There is a complete treatment of all this stuff in the Hans Bethe and Edwin Salpeter quantum mechanics, 1 and 2 electron atoms. You can look that up if you want to, but basically I'm just telling you the answer. I don't expect you to actually work that out at this point. And when you plug all that back in, what you get is the expectation value of the perturbation. When you put all 3 terms back together, it looks like this. Notice it only depends on L. So if you know L, then you can work out the expectation value of the perturbation. Okay. Now let's go ahead and talk about the spin-orbit coupling. The spin-orbit coupling is, remember I mentioned that the magnetic field that the spin magnetic moment, that the electron's magnetic moment sees, has to do with the magnetic field produced in the frame of reference of the electron by the electrostatic field of the proton in the laboratory. So, and that Hamiltonian, of course, is minus the magnetic moment dotted into the magnetic field. So this is a formula you probably learned in your electrodynamics class. I'm just going to write down the answer. I'm working on a explanation of this effect that's a little more detailed than what you see in the book. The book basically goes into the frame of reference of the electron and treats the proton as a Biot-Savart current that produces a magnetic field at the location of the electron. But then you have to do all kinds of monkey business to get back to the right answer. Anyway, I'm working on something. I don't know if I'll be able to work it out, but anyway, you can read what Griffiths has to say. You can just take my word for it. But there is a correction to the energy. The perturbation is proportional to S because the magnetic moment depends on S, and it's proportional to L because the Biot-Savart magnetic field from the proton depends on L. Or if you like, the magnetic field observed by the electron due to the Lorentz transformed electrostatic field of the proton depends on L. So you end up with the dot product of S and L, and that is the perturbation. Now the thing is, the total angular momentum J is L plus S, and what we're going to find out is that while L no longer commutes with the Hamiltonian, does not commute with the perturbation, and S does not commute with the perturbation, that the sum of the two, J, does happen to commute with the perturbation. Let's look at that. If you calculate the commutator of L dot S and L, you do not get 0. The commutator of L dot S and L almost magically turns out to be the cross product of L and S. And the commutator of L dot S and S turns out to be the cross product of S and L. But if you calculate the commutator of L dot S and J, that's the commutator of L dot S and L plus the commutator of L dot S and S. And if you know anything about cross products, you know that if you take the cross product of A cross B, it's the negative of the cross product of B cross A. Well, that's also true of L and S. So if you add those two cross products together, guess what you get? Nothing. So what that means is, while L dot S does not commute with L, and L dot S does not commute with S, L dot S does commute with their sum, which is J. So what does that mean? Remember that the time rate of change of an expectation value of an operator is the commutator of that operator with the Hamiltonian. If the operator commutes with the Hamiltonian, it means that it is a conserved, its eigenvalues, if you measure it, it doesn't change in time. So J is a conserved quantity. J does not change in time. But L and S do not commute with the perturbation. Therefore, under the influence of this perturbation, neither L nor S are conserved. They change in time. Now, you can also show that L dot S does commute with the length of L, the magnitude of L, and L dot S does commute with the magnitude of S. So the magnitude of L and the magnitude of S don't change, but the individual components of L and S do change. Having said that, the sum of L and S does not change, and the magnitude of the sum, obviously, if the sum doesn't change, then the magnitude of the sum doesn't change. And so we get J squared, L squared, and S squared are all conserved. J is conserved, but L and S alone, individually, are not conserved. Now, what is J squared? J squared is the dot product of L plus S with itself. But if you work that out, that's the magnitude of L squared plus the magnitude of S squared plus twice the dot product of L and S. And we can use that as a trick to figure out what L dot S is in terms of the magnitudes. L dot S is half of J squared minus L squared minus S squared. This is a really important trick. We use it all the time if we're doing angular momentum calculations, and so it's sort of burn that into your memory banks or whatever. But the point is, since the spin-orbit coupling perturbation is proportional to L dot S, we can use that to work out the size of this guy We do need the expectation value of 1 over r cubed, because you can see that it depends on 1 over r cubed. And so when the smoke clears and you put everything together, you get the following result, that the perturbation, the first order perturbation energy of the spin-orbit coupling goes like J times J plus 1 minus L times L plus 1 minus S times S plus 1. That's just the L dot S term. Of course, S is a half, so S times S plus 1 is 3/4. And downstairs, we've got L times L plus a half times L plus 1. That comes from the expectation value of 1 over r cubed. And that's how the whole thing turns out. You can simplify that. If you add the spin-orbit coupling correction and the relativistic correction together, it turns out they have roughly the same order of magnitude. The whole thing ends up depending only on J, which is sort of amazing. And if we have time, we can work some of that out. It's a little tedious, but it is possible to do it. And you can see how it turns out. But the total fine structure, this is the so-called fine structure correction. It's a combination of the spin-orbit coupling correction and the relativistic correction. And it ends up only depending on J, the J quantum number. The very last thing I want to discuss is the Zeeman effect. And the Zeeman effect is what you get when you put a hydrogen atom, or any atom basically, in a magnetic field. You get a Hamiltonian that comes from two pieces. There's the magnetic moment the electron has as a consequence of its spin, plus the magnetic moment that it has as a consequence of its orbital angular momentum. You add those two together, and you dot them into the external magnetic field. So this is another mu dot B thing. But this time the B isn't internal. It's not built into the hydrogen atom like the spin-orbit coupling, but it's actually something in the laboratory. You have a magnet in the laboratory, and you stick the atom in the magnetic field, and you look at what happens to its energy levels. And the answer is the energy levels change. Now here's the thing. The spin magnetic moment is E over m times the spin of the electron. The orbital angular momentum magnetic moment is half of E over m times the orbital angular momentum. So what that means is when you put in all that stuff and you calculate the perturbation, you get L plus twice S. Now here's the thing. We found out, due to the spin-orbit coupling, that L plus S is conserved. J is conserved. But this Hamiltonian is not equal to J, or not proportional to J. It's proportional to L plus 2S. But I can rewrite L plus 2S as J plus S. And if I have a weak magnetic field where the perturbation due to the Zeeman effect, or due to the external magnetic field, is much smaller than the fine structure, in other words, much smaller than the spin-orbit part, then I can treat the Zeeman effect as kind of a perturbation of the solution we got for the spin-orbit situation. So we're going to be talking about very weak fields for the moment, and in that case, J is a good quantum number. J is conserved because J is conserved in the spin-orbit coupling, and it's much larger than the energy that we're talking about calculating. And so the idea is you can think of J as being good and S as varying. But the thing is, so parts of S are going to average out to 0, and parts of S are going to be are going to have a finite average contribution, but we got to figure out which parts we need to worry about. So the idea is J, the total angular momentum, is conserved. Neither L nor S are conserved, and so you can think of L and S as sort of processing around the vector J. And in the presence of the magnetic field, of course, the vector J is going to process around the magnetic field, but S and L process around J.
So the precession of S and L around J is due to the spin-orbit coupling. The precession of J about the Z direction is the Zeeman effect, but it's very slow compared to the precession of S and L around J. And so what we end up with is that the only piece of S that survives is the projection of S in the J direction. How do you calculate the projection of a vector in another? Well, you take the dot product of the vector with the direction you're interested in, and you multiply by the direction you're interested in. And that's, of course, a unit vector in the direction you're interested in. And so if we write that out for S and J, if we want to know what's the projection of S along the J direction, we end up with this expression. And if we put all that in, we get the expectation value of J plus S is it's J, and then we have to add in just the projection of S along the J direction. We're going to work this out as a board work problem today if we have time, but I can tell you that the answer turns out to be that the Zeeman effect, perturbation energy, is proportional to the magnetic field. It's proportional to the Z component of J, and to the this thing called the Landé factor, which we'll work out on the board today. And it's also, of course, in the book. You can see how that turns out. But that's all for this time. Next time, we're going to go ahead and look at the strong field limit. What happens if the Zeeman field is much greater than the internal field, so that the Zeeman Hamiltonian is much greater than the spin-orbit coupling Hamiltonian. And then what about if the two perturbations are roughly the same order of magnitude? How do we handle that? That turns out to be a little bit of a mess, but we need to see how it's done, and so we'll do that next time.
All right, it's lesson 15. We're going to talk about the Zeeman effect, and in other words, degenerate perturbation theory. And before we get into that, it turns out it gets to be kind of technical and a little bit complicated. And in order to be more clear, I thought it might be useful to address a problem. I'll call it a toy problem that has some of the same features, but is a little easier to grasp what's going on. Now, you may remember last semester I had a similar toy problem where we had two different basis sets, and we were expanding various kets in terms of one basis or the other basis, and looking at operators and how they looked in one basis or a different basis. And that's kind of the game we're playing here. I have two sets of basis vectors, the A basis with A plus and A minus, and the B basis with B plus and B minus. And the notion is that we have two different Hamiltonians. We have the original Hamiltonian, which we solve, and we discover that the eigenvectors and eigenvalues of that Hamiltonian are most simply expressed in the A basis. In fact, A plus and A minus could be eigenvectors of the original Hamiltonian. And then there's a perturbation to that Hamiltonian, but the perturbation has a different set of eigenvectors and eigenvalues, and those are most simply expressed in the B basis. So B plus and B minus, for example, could be eigenvectors of this perturbation. And so let's think about that. Let's say we have a Hamiltonian A, which has eigenvectors A plus and A minus, and eigenvalues plus big A and minus big A. And at the same time, there's a Hamiltonian HB, which has eigenvectors B plus and B minus, which are distinct from Hamiltonian A, and it has eigenvalues. Those eigenvectors have eigenvalues plus capital B and minus capital B. And the idea here is to say, well, what happens if I have a Hamiltonian, which is the superposition of those two, the A Hamiltonian and the B Hamiltonian. Now, understand, there's no reason why, for example, capital A could be 0. If capital A is 0, that means that the eigenvalue of those two basis vectors, A plus and A minus, is degenerate. If A is 0, then they have the same eigenvalue, 0 in other words. I can always add or subtract a constant to a Hamiltonian, so that even if I have two energy states that are degenerate but have non-zero energy, I can always add or subtract whatever that energy is to make them zero eigenvectors. So this is not all that, I mean, it doesn't seem general at first, but it's not that ungeneral, it's not that specific. So anyway, the total Hamiltonian is going to be the superposition of the A part and the B part, and gamma is going to represent some kind of a variable strength, so that I can turn on HB. I can make it as strong as I like by making gamma a big number. If I want to turn off the perturbation, I can make gamma equal to 0. And you can see that the results of our calculations are going to depend on gamma. Gamma is like a knob of a magnetic field generator in the laboratory, or electric field generator in the laboratory, something. Okay. So the notion is that you can represent the A Hamiltonian as a matrix in the A basis. You can see it's quite simple because the A basis is the eigenbasis, so that means it's diagonal in that basis. But what about HB? What about HB? So the idea is you know that HB acting on A plus, that's the question we need to ask ourselves when we're trying to find the representation of HB in the A basis. I can decipher that by rewriting A plus as a superposition of B vectors in the B basis. So at the very beginning we had the dictionary that told us how to go back and forth between the A basis and the B basis. And you can see that if I write out what A plus is in the B basis, then I can easily determine what happens, because we know that B plus is an eigenvector of HB with an eigenvalue plus capital B, and B minus is an eigenvector of HB with an eigenvalue minus B. So immediately we get this result. If I want to recast that in terms of the A basis, I can simply use the same dictionary to express B plus and B minus. In terms of A plus and A minus, it gets a little ugly, but notice you can pull the A plus terms together, you can pull the A minus terms together, and the thing simplifies quite a lot, and you can see that it ends up looking like this. Similarly, you can pull the same trick with A minus, and ultimately it turns out that HB acting on A minus looks like this, and at this point we can just read off the A plus and A minus components and put them into a matrix, which tells us that HB expressed in the A basis ends up looking like this. So you see, for example, the A plus component of HB acting on A plus is 1/3, and the A minus component is -2, the square root of 2 over 3. Of course, all multiplied by capital B. But you can see where this matrix comes from looking at those two lines above. So now, let's form the overall Hamiltonian as HA plus gamma times HB. And how does that turn out? HA is the diagonal matrix we just saw. HB is this more complicated looking thing, but if I throw it all together, I get this terrible monstrosity. Okay, that is the total Hamiltonian in terms of gamma in matrix form expressed in the A basis. If I want to find the eigenvalues and eigenvectors of this matrix, all I have to do is take the normal strategy of solving the eigenvalue problem. The eigenvalue problem is, of course, H acting on some arbitrary ket is equal to a number times the same ket. That immediately gives us this characteristic equation, which says the determinant of this matrix, notice the minus lambda is on the diagonal, has to be 0. You plug that equation into your favorite computer algebra system, at least that's what I did because I'm lazy, and it came out with this result. And
that tells us that there are two eigenvalues, and of course I can plug those eigenvalues back into the original eigenvalue problem and compute the eigenvectors. In the end, we get some eigenvectors that depend on gamma. As you can imagine, when gamma is equal to 0, the eigenvectors are just a plus and a minus, but as you dial gamma up, the eigenvectors approach b plus and b minus. So let's do a little demo now, and you can see how that goes. So here we have the eigenvectors. Let's scoot back a little bit. A plus and b, a plus and a minus. And I'm going to turn on gamma, and you'll watch gamma go. Gamma is going to be just proportional to time. And once gamma gets going, you'll notice that the eigenvalues, which are going to graph in this window, separate, and that the eigenvectors, which will display here, are going to rotate toward b plus and b minus. So let's do that. You can see that effect happening. As time goes on, the eigenvalues now become proportional to time, essentially, and the eigenvectors now are approaching asymptotically the eigenvectors b plus and b minus. And that's the way it works. Good. Now let's get back to business. We're going to go back to the Zeeman effect. Now we talked about the weak field Zeeman effect last time. Today I want to deal with the weak field and the strong field and everything in between. It gets a little complicated. First, let's start with the fine structure correction. Remember, the fine structure correction to the hydrogen atom only depends on J. So it makes sense that the fine structure Hamiltonian, that is the Hamiltonian that includes the fine structure corrections and the original Coulomb potential of the hydrogen atom, would be most simply expressed in a basis where J is well defined. In other words, in the J m sub J basis. And that's right. The Zeeman Hamiltonian, on the other hand, is more complicated. It's proportional to Lz plus 2 times Sz. Now remember, the 2 in the Sc comes in from the fact that the spin angular momentum is related to the magnetic moment of the electron in the similar way as the orbital angular momentum is related to the orbital magnetic moment, but there's an extra factor of 2, and that comes from the Dirac equation and relativity and all that stuff. But it is well known that the electron's magnetic moment is twice what you would expect, assuming that the electron was just a ball of charge spinning with some angular momentum. And that is a purely relativistic effect. But let's, as Griffiths does in the text, let's go ahead and consider the n equal 2 levels of hydrogen. And when n equals 2, we have a couple of different possibilities. We can either have L equals 0, and S is a half. We can have L equals 1, S can be a half, and J could be a half. Or you could have L equals 1, S equals a half, and J is 3 halves. So the J is 3 halves case is the so-called extended, and the J is 1/2 case is the so-called jackknife configuration. Let's consider these three ways of having the system organized. Of course, if L equals 0, the only contribution to J is the spin. So that's quite easy. The states of well-defined J also happen to be states of well-defined L and states of well-defined S. So it makes it quite simple. In the extended case, there are 4 possibilities because J is 3 halves. So M sub J could be 3 halves, a half, minus a half, and minus 3 halves. Of course, in the jackknife configuration, J is only a half, so there's only 2 possibilities. M sub J is plus a half, or M sub J is minus a half. But in order to compute the Zeeman Hamiltonian in the J basis, we need to know what the values of M sub L and M sub S are, because those are the things, those are the LZ and SZ quantum numbers that tell us what the Zeeman effect is going to be. What is the energy associated with the Zeeman effect? So let's begin with the S states. Of course, they're the easiest because L is equal to 0, M sub L is equal to 0. The only thing we don't know is what's going on with S. Of course, if if m sub j is plus a half, then m sub s has to be plus a half. And if m sub j is minus a half, m sub s has to be minus a half. So it's not very complicated. This is quite easy. Where it gets more interesting is when we go into the extended configuration, where now we have to express 3/2 in terms of L and S. Of course, the only way to get an m sub j of 3/2 is if m sub L and m sub S are both positive. So m sub L has to be plus 1, m sub S has to be plus a half, so they can add up to 3/2. And there's no other combination of m sub L and m sub S that does that. So that's sometimes referred to as the top of the ladder. Okay, we're all the way at the top. But the question is, how do I form an m sub j is 1/2 out of various L and S states? The answer to that question, or in order to answer that question, you really have only two options. You can either go and grab the dreaded Clebsch-Gordon coefficient table, or you can remember last semester we did this once before and I kind of walked you through it. But basically the idea is you pull out the j minus operator. If you apply the j minus operator to a state j is 3/2, m sub j is 3/2, you're going to get something proportional to j is 3/2, m sub j is 1/2. In other words, it's going to bump the m sub j down by 1. And there's going to be a factor out in front. You remember that crazy square root thing that's out in front? But the basic idea is that j minus takes m sub j down by 1. But remember that j minus can be expressed as L minus plus S minus, because j is L plus S. And that means that I can operate on the state 3/2 with L minus plus S minus to figure out what I get. And the answer is, of course, when L minus acts on that state, you get 1, 0, but it doesn't touch the spin part. And when S minus acts on that state, you get 1/2 minus a half, but it doesn't touch the L part. So when you add those two together, you get two pieces. One piece has 1, 0, a half plus a half. The other piece has 1, 1, left the L alone, but 1/2 minus a half. So you end up with a superposition of two different states of L and S. That's why the JM states don't always have well-defined contributions. They don't have well-defined values of L, m sub L, and m sub S. If you measured m sub S in this state, you'd have a 67% chance, roughly, a 2/3 chance of getting plus a half and a 1/3 chance of getting minus a half. And similarly, if you measured m sub L, you'd have a 2/3 chance of getting 0. You'd have a 1/3 chance of getting 1. And the crazy square roots in the front arise from those crazy square roots that show up in the front of the results of the L minus, S minus, and J minus operators that you remember, I'm sure, from Chapter 4. If you don't, you might go back and remind yourself how that goes. But that's the idea. So we can replace, or we can express 3/2 a half as a superposition of states of different m sub L and m sub S. We can play the same game with 3/2 minus a half and the same game with 3/2 minus 3/2. It should be no shock that the 3/2 minus 3/2 is simple again, just like the 3/2 plus 3/2, because there's only one combination of m sub L and m sub S that give rise to that m sub j. Okay, I know this is technical and it's complicated, but what can I do? It's the way nature works. And in the jackknife configuration, it's a similar idea. It's just that now we need a different combination of m sub L and m sub S that adds up to a half, but it has to be orthogonal to the combination that had j is 3/2. And if you think about it for a little bit, you'll see that the only combination that does that has to have different signs on the two terms, and the square root of 1/3 and the square root of 2/3 have to swap places, so that when you dot those guys into each other, you get 0. And then you can use j minus to get the 1/2 minus 1/2 version, the j equals 1/2, m sub j is minus a half version of the same ket, and you end up with this. And so let's summarize what we've got here. we'll write down every single one of these guys. This is the order that Griffiths puts them in, for a reason that we'll get to in a second. Basically, the first 4 kets are top of the ladder, bottom of the ladder kets. So they are interesting in that they are simultaneously eigenvectors of J, L, and S. And they have well-defined values of J, M sub J, L, M sub L, and S, M sub S. So these guys are simultaneous eigenvectors of both the fine structure Hamiltonian and the Zeeman Hamiltonian. So there's no ambiguity about these 4 states. We don't need to do, in fact, we're done. We can basically write down the answer for all 4 of them. The trouble comes in 5 and 6 and 7 and 8. And the way these are grouped, I want you to look at them for a second and notice that the grouping has to do with the fact that they interact with one another. They have the same values of M sub J, and so these guys, through the action of the Zeeman Hamiltonian, they connect to one another. In other words, the Zeeman Hamiltonian has a non-zero inner product between 5 and, or matrix element between 5 and 6, and a non-zero matrix element between 7 and 8. But they're the only ones that connect. In other words, 5 doesn't connect with 7 or 8 or 1 or 2 or 3 or 4. 6 doesn't connect with 7 or 8 or 1 or 2 or 3 or 4, but it does connect to 5. So, and we'll see why that's important here in a moment. Let's review for a second what's going on. Now, the fine structure Hamiltonian is diagonal in the J basis. We've already figured that out. And we know that the energy that we need to use in our expressions for energy is the 2 state. We're dealing with the n equal 2 state. And so I know that. And let's see what else I know. I can go ahead and compute the fine structure Hamiltonian by putting in the fact that E2 is E1 over 4, square it. That gives us a 32 downstairs because it's 2 times 16. And I know n is equal to 2, so I can replace the n in this generic expression with 2 and get 8 over j plus 1. Now, since it only depends on j, and we only have 2 values of j, we have j as a half and j as 3 halves, we can compute these guys directly. Putting in what the actual energy is, we can see that the fine structure Hamiltonian has basically 2 values. When j is a half, it works out to be minus 5 times the fine structure constant divided by h squared times 13.6 electron volts. We're going to call that gamma, so I don't have to say that so many times. And when j is 3 halves, it's minus gamma. So j is 1 half is minus 5 gamma, j is 3 halves is minus 1 gamma. So that's the plan. This is important because we're going to be making this nasty matrix, and we want to simplify it as much as we can. So by taking all those constants and just calling them gamma, it'll look a little less formidable. Okay, now let's remind ourselves about the Zeeman Hamiltonian. It's diagonal in the LS basis, and the point is, if we apply, for example, the Zeeman Hamiltonian to some particular state, let's say the 0, 0, 1 half, 1 half state, the L comes in with the 0, the S comes in with the half, and so we get a half times 2 times the junk on the left, and then there's an h bar. The h bar comes from the SZ, because SZ is h bar times m sub s. And so you end up with this junk out in front, but to simplify the thing, we're going to call that junk out in front beta. So beta is going to be h bar E over 2m times the external magnetic field strength. And so it's proportional to the magnetic field strength, but and it's got units of energy, essentially. Okay, so since we know that the first 4 states are eigenstates of both the Zeeman and the fine structure Hamiltonian, we can immediately compute the matrix elements of Hz on those states. They're on the diagonal, and they're all proportional to beta. Now, what happens when you apply Hz to one of these other superposition states? Well, it gets complicated. Well, take psi 5, for example. Psi 5, the first component has m sub L of 0 and m sub S of a half. So that gives you m sub L plus 2 m sub S is 1. But the second component has m sub L of 1 and m sub S of minus a half. So that gives you m sub L plus 2m sub S of 0. So these guys are not, neither of these are, let me say it this way. This ket, psi 5, is not an eigenvector of the Zeeman Hamiltonian. The first component is an eigenvector. It's got an eigenvalue of 1 times some junk, and the second term has an eigenvalue of 0, but neither of them directly are, or I should say the superposition is definitely not an eigenvalue, because the second term gets wiped out, the first term survives, and so what you see is that Hz acting on psi 5 only has the first term in the answer. That means that if I take psi 6, remember psi 6 was a superposition of the same two kets with different, no, I'm lying. No, I'm not lying. It's a superposition of the same two kets with different coefficients, and that means that psi 6 has a matrix element on Hz acting on psi 5. This is what I meant by the fact that psi 5 and psi 6 are connected together by the Zeeman Hamiltonian. They have a non-zero matrix element, and if you calculate the complex conjugate, of course it's a real matrix element, so the complex conjugate is equal, and so if you plug all that in, you'll notice that psi 5 and psi 6 have off-diagonal matrix elements. Psi 7 and psi 8 have off-diagonal matrix elements, and those arise from the Zeeman Hamiltonian and in more or less the same way. Now, the good news is, because these are just little 2 by 2 off-diagonal elements, you can pull that submatrix out and treat it as a little system, the psi 5, 6. And so what we know are so you could think of psi 5 and psi 6 as sort of like a plus and a minus in our toy problem. And you could think of the components of psi 5 and psi 6, the components that have definite values of m sub L and m sub S. Those are a little bit like the B eigenvectors in our toy problem, and the beta is a little bit like the gamma from the toy problem. I picked unfortunate Greek letters, but the point is beta is just a parameter. It's proportional to the magnetic field strength. It has units of energy, but it basically tells you how strong the magnetic field is. So as you adjust the magnetic field strength, the eigenvectors are going to transform from eigenvectors of HFS to eigenvectors of Hz. That's the idea. But the strategy is the same. You basically treat this as a little eigenvalue problem. You put in the lambdas just like we did in our toy problem. You get out energies, which are eigenenergies of the total Hamiltonian, the original and the new, and then you can go back and compute eigenvectors at the same time by putting these lambdas back into the original eigenvalue equation. Let's take a look at this result and see if we see anything interesting. I'm going to rearrange things just a little bit, and then let's look at the case when beta is much, much less than gamma. If beta is much, much less than gamma, being careful with the square root. If you factor the 4 gamma squared out of the square root, you get the 1 plus something small inside the square root. You can treat that as 1 plus something small over 2 if you use the expansion formula, the small parameter expansion formula for square roots, and you get this result that the energy of the 5, 6 states, there are 2 of them. One of them has negative 3 gamma plus 2 gamma. Notice that's minus 1 gamma. So that means this must be a J is 3/2 state. And what is the beta going to be for that one? I got plus beta over 2, then I get plus beta over 6. so that's going to be 2/3 of beta. And so this one must be one that depends on beta, like plus 2/3. Now if you go back and look at the lesson last time, you'll notice that the low field energy for the Zeeman effect it was proportional to m sub j. It had this Landé factor g sub j in it, and it had the magnetic field and the Bohr magneton and all that stuff. But the main point is that you ended up with something proportional to beta as the energy. And if you go back and check it, you'll see that in this case, if j is 3/2 and L is equal to 1, then the factor in front of the beta turns out to be 2/3. So that it's useful to go back and check that this thing actually works out, and you should feel confident, or at least you should go check it, and then you'll feel confident that it does. And what about if beta is very large? Again, being careful with the square roots. You see that in this case, there are two possibilities. The plus sign gives you a plus beta. Excuse me. The minus sign gives you 0. So the two states, 5 and 6, one of them goes like plus beta for large b for large beta, and one goes like 0. And I think we already saw that when we were going through the states originally. So you can do a similar thing with 7 and 8. You can look at the low field behavior. You can look at the high field behavior. But and again, you can go back and check that they have reasonable properties. But that's the idea. Just to remind you how it goes, there's the expression from the last set of slides, and there is the Landé factor. And if you go and put in the L and J's for the different cases that we're studying, we have 3 Landé factors to worry about. There's the S states, L equals 0, have G sub j equals 2. Then we've got the jackknife configuration has G sub j as 2/3, and the extended configuration has G sub j as 4/3. If you put all that in, you end up with, so for example, states 1 and 2, you end up with minus 5 gamma plus or minus beta. The j equals 1/2 states, remember, have a low field energy of minus 5 gamma, and putting in the Landé factor, you get plus or minus beta. If you're looking at the extended configuration, in the case where j is 3/2 and m sub j is 3/2, then you get minus gamma. That's the 3/2 j has a higher low field energy, minus gamma, and then the magnetic field part goes like plus or minus twice beta. The trickier ones are the 5/7 and the 6/8, and those guys also go like 2/3 and 1/3 beta, and that comes out of the Landé factor and all that stuff. So this is just to help you if you want to sit down and work it all out. You can check to see that the low field results of the eigenvalue problem produce the same results we got when we treated it as a weak field perturbation of the fine structure. And just to kind of show how that works, I'm going to do a little demo now so you can see it for yourself. Okay, so here I've actually put into Grapher the 4 energy eigenvalues that we got out of the math, and I've in order to make it easier to zoom in and out, I've added basically something like 2.5. Actually, what have I added? I've added 3, I think. I've added 3 gamma to the energies, so that the high energy state becomes +2 on this scale, and the low energy state becomes -2. Remember, originally they were -1 and -5, but if I zoom in, the origin's going to be way up there somewhere, and it's not as pretty. So, but these are the high energy states. Remember, the high energy states where the J is 3/2, and the lower energy states where J is 1/2. And so these are the high energy and the low energy. Now, there's only one source of J is 3/2. That was when L is 1, S is 1 in the extended configuration. but there's two ways to make J is J is a half. You can either have L equals 0, or you could have L equals 1 and S equals a half in the jackknife configuration. So both of those are in here. And we just worked through the math to see how that turns out. What I want to show you, and this is the magnetic field direction to the right. You increase the magnetic field strength and the energies separate, and notice the energies even cross down here. What happens if I zoom out? So let's zoom out, and you'll notice something interesting. These guys kind of pair up in a way. So now we're starting to look at the high field. Notice the J is 3/2 and J is 1/2 states sort of come together, and what we end up with, if you look out here a little ways, is 5 states. I'll zoom out again. It looks like there's only 5 states out here. Now they're actually combinations of states of different J. States of different J are coming together to make states of definite L and S. So this is the high field limit. I can even zoom out some more. This is the high field limit, and in the high field limit, all that matters is M sub S and M sub L. The J doesn't make any difference anymore. We're looking at a different basis. It's sort of like in the toy problem, now we're in the B basis. The B basis is the LS basis instead of the J basis. And in this case, remember the energy went like, it was proportional to L sub Z plus twice S sub Z. So, you know, S sub Z is only plus and minus a half h bar. L sub Z is plus or minus minus 1, 0, or plus 1. But when you multiply the S sub Z by 2, then it contributes either plus 1 or minus 1. And so you end up with 5 states. You could have L and S both positive, in which case you get essentially 2 1s. You get a 1 from the S and a 1 from the L. You could have L equals 0 and S is plus 1. You could have L equals plus 1, S equals minus 1. Not S equals minus 1, but S contributes minus 1 because of the factor of 2, and so on. So it turns out there's 5 states, and those are the 5 states in the strong field Zeeman limit. But in the weak field limit, you end up with 2 groups of 4. The J is 3/2 and the J is 1/2, and it's a more or less completely different behavior. But the theory that we just worked through handles both the weak field and the high field limit, and that's how it works. Well, welcome back. It's lesson 15. So this is going to be a very short set of slides, which I guess is probably good news if you are pressed for time. But I did want to just touch a couple of things. The first is there's a new homework assignment. What I thought I'd have you guys do is to look at the Zeeman effect and notice that Griffith's states 7 and 8, the one he calls psi 7 and psi 8, go from 2 specific low field states to 2 different high field states. What I want you to do is to look at the eigenvalues listed on page 283 as a function of beta, and the information from page 281 that describes what states 7 and 8 actually are and how they're defined in the J basis. And I'd like you to identify what are the low field states, what do they correspond to, definite values of what observables, and then in the high field limit, what do these 2 particular states correspond to in terms of their quantum numbers and their observable values. So that's the idea. Just write out in words, I guess, with any justification you can based on the equations. Then the second part of the homework is to begin our study of the polarizability of the infinite square well. Now this is kind of a toy problem. It's not something anybody probably actually does, although with nano technology and quantum dots and so on, I guess this might be not too far off from something you might actually do. But the notion is this. You get an infinite square well, you apply a potential that produces a constant force to the left in the infinite square well, and I'm going to represent that as a potential that's balanced. It has no net potential. The average potential over the entire well is 0. So the reason for that is simply that it doesn't affect the energy of the states to first order,
And all I care about at this point is the ground state. So I'm just going to have you guys study the ground state perturbations. What happens to the ground state wave function? What happens to the ground state energy under the influence of this perturbation? And the answer is, to first order, not much goes on. The expectation value of the potential in the ground state is 0. So, but what we can do is look at the second order non-degenerate perturbation theory in energy, and the first order non-degenerate perturbation theory, what is the effect on the wave function? And that's what I want you to do this week. So ultimately, once you get the wave function, you can also estimate the electric dipole moment after the perturbation is applied, and see that there's an induced dipole moment that isn't there in the ground state before the perturbation is applied, but after the perturbation is applied, then you get a dipole moment. And so that's the idea. All right, so let's talk about the hyperfine structure. The idea of hyperfine structure is that the electron, in addition to seeing the magnetic field due to the fact that the electrostatic field of the proton produces a magnetic field in the electron's frame, the proton also has a magnetic dipole moment. Now, it's a very it's a very tiny dipole moment, but it's there nonetheless. And so we can compute it. I'm not going to go through the details. Griffiths explains all that, and it's fascinating. But basically what you wind up with when you're dealing with the ground state of the hydrogen atom, the only thing that really matters is the spin of the electron and the spin of the proton. You get a perturbation that's proportional to the spin of the proton dotted into the spin of the electron. Now, the total spin is the sum of those two guys, and it turns out neither the spin of the electron nor the spin of the proton is a good quantum number in the sense that it's conserved in this system. But the total spin is. In other words, the total spin commutes with sp.se, but neither SE nor SP individually commutes with sp.se. So that's the idea. And using the same tricks we worked out last time, you can show that there's a relationship between S squared, SE squared, SP squared, and since these guys are all spins, the SE squared and the SP squared, they're both spin of a half. Those are just definite numbers. And when you plug everything in, you see that the dot product of SE and SP depends only on the total spin quantum number, the magnitude of the total spin quantum number. Of course, what choices do we have for the total spin? Well, there's only two. Either you can have the total spin as 0, that would be the singlet configuration, and if you plug in S equals 0 into that expression, you get minus 3/4 h bar squared for the dot product. Of course, the other option is that it's the S equals 1 case, the two spins add to make a total spin of 1, and if you plug that into the expression for SE.SP, you get h bar squared over 4. And since the perturbation energy is proportional to SE.SP, that means the triplet and the singlet states, while they're degenerate, if you don't include this interaction, if you do include it, you get a difference in energy. And that is the energy associated with the spin. It's called the so-called spin-spin coupling. You guys have already encountered this energy if you've done any reading about radio astronomy, because the famous 21 centimeter line of hydrogen is exactly this transition. It's the transition from spins aligned to spins anti-aligned. The aligned spins has a lower energy. The anti-aligned spins has a somewhat higher energy. So there we have it. And then I just want to point out, we haven't really officially started this section yet, but the idea behind this section is so easy that I just wanted to go ahead and say it and kind of get you started on that. It's called the variational principle. And the notion is this: the energy of the ground state of any system is less than or equal to the expectation value of the Hamiltonian for any wave function. You pick any random wave function you like, use that wave function to compute the expectation value of the Hamiltonian, and the number you get is always going to be greater than or equal to the ground state. Of course, if you happen to pick the wave function that is exactly equal to the ground state wave function, you'll get the equality. But any other wave function, you're going to get something bigger. So the idea is you can use this to get as close as you like to the exact ground state wave function. You simply randomly pick a wave function, you calculate the energy, then you make a random change. If the energy goes down, you take it. If it doesn't, you don't take it. Or you use the some kind of a strategy, like, for example, the Metropolis algorithm or something, to figure out how to make the change, when to accept it, when not to accept it, and so on. And eventually, you will find a wave function that is arbitrarily close to the exact ground state wave function. That's the idea. All right, we'll see you guys next time.
Okay, guys, it's lesson 16. It's time for some diffusion Monte Carlo, and we're going to touch again on the variational method. I'll basically just recap what we said last time. It's such a simple idea. It doesn't really require much, but I want to just reinforce what we already talked about. Let's go back to this guy. Do you remember this equation? I guess you probably do. It's nothing other than the Schrödinger equation. The the left-hand term just says the time evolution of the wave function is proportional to the total energy operator, the Hamiltonian operator, acting on the wave function. Now, of course, the Hamiltonian is made up of kinetic energy part and a potential energy part. So nothing new here, but interestingly, if I replace the time variable with a minus I times tau, so we make a variable substitution, essentially, and then clear out the i's, divide the i's out, and multiply through by minus 1, we get the following result. That is, the time derivative of this wave function thing goes like the second spatial derivative minus the potential energy function times the wave function again. I want you to notice that that's looking an awful lot like the diffusion equation. If we imagine adding an offset to the energy, call it ER, and more about that in a minute, but if we add an offset to the energy, notice that what we have here, it's sort of like when you have a diffusing gas or a diffusing material embedded in some other material, for example. You know that the time rate of change of the concentration of the stuff that you're following depends on something like a diffusion constant times the second spatial derivative of the concentration. And then if there is a source of this stuff, it would appear as a source term. And this equation, even though it's the Schrödinger equation with the time replaced with a minus I times tau, it looks exactly like the diffusion equation. And so the notion is that if you understand the diffusion equation and you understand how to solve it, you can use that understanding to solve the Schrödinger equation. That's the underlying sort of insight to diffusion Monte Carlo. So I'm going to skip now to look at the Computing Project 4 handout, and I'll just sort of touch on the highlights of that. Of course, you can read it and see how it goes and ask questions if you have trouble. But I thought it would be worthwhile to just sort of go through it bit by bit in the slides so you could see how that goes. Okay, so this is Computing Project 4. And it's about diffusion Monte Carlo, and you'll recognize these equations. These are right out of the slides, the Schrödinger equation, what you get when you replace the time with the complex time, what happens when you clear some signs, and finally what you end up with. Now, one thing I want to point out is that if you have an eigenstate of the Hamiltonian, of course you get the eigenvalue that goes with it. If I were to add an offset to the Hamiltonian, just a constant offset, what it would do, your eigenstates would still be solutions to the original equation, but now the eigenvalues would simply get that offset. So the eigenvalues would change, but the eigenvectors would be the same. That's an important point. Now, the thing is, if I rewrite that a little bit, let's see, and I write an arbitrary ket as a superposition of eigenkets, with the original Schrödinger equation, of course, if I if I add a constant offset to the Hamiltonian, that just adds a constant offset to the omegas. And that doesn't actually have any physical impact, because we all know that if you multiply a wave function by a constant phase, even if it's a superposition state with multiple different eigenvalues, that constant phase just hits all the eigenvalues, or hits all the components of the wave function, and when you compute anything physical, it doesn't really make any difference. But if we change this from a complex exponential to a real exponential, like this, with the diffusion equation, then notice that adding or subtracting a constant to the Hamiltonian adds or subtracts a constant to all these real exponential terms. Now the thing is, I want you to focus on the ground state for a second. If we were to add the ground state energy in such a way that let me say that again. If we were to add an energy to the Hamiltonian such that the ground state energy became 0, then as the time progressed, notice that the factor multiplying the ground state wave function would just be 1, e to the minus 0 times tau. But all the higher energy states would have a positive constant here, because they would all have energies greater than the ground state energy, and so they would naturally decay out in time, because when you change the time to an imaginary time, then these guys all become real exponentials that decay. The only one that wouldn't decay would be the ground state, because if you could set the offset energy equal to the ground state energy. So here's the idea. We fiddle with the offset such that the number of walkers so here's the plan. You make a bunch of walkers. They're just random representations of positions in the state space of the eigenfunction. They're basically, you think of them as little guys that wander around in quantum state space, and they get born in those regions where the source term is large. Let's go back and look at the diffusion equation again. Where this term is large, you create walkers. Where this term is small, you destroy walkers. And you adjust this energy, E sub r, so that the number of walkers remains relatively constant. When you do that, it turns out the wave function that survives after you run this thing for a long time is the ground state wave function, because all the higher order eigenstates decay away as a consequence of that real exponential effect. So we can rescale the equation. We rescale the distance with a length scale, rescale the time with a time scale, rescale the energy with an energy scale, and the equation under those circumstances looks like this. And basically we get to choose the length scale and the time scale, for example, and then the energy scale gets dictated, or we could do it the other way around. And we can talk about that in class. The technical details of scaling the equation are a little bit tricky, but the main idea is we adopt position, time, and energy units to make the equation simple, and then we run this algorithm, the Walker algorithm, in time so that it correctly represents a diffusion process. And what we end up with is the diffusion of walkers around in such a way that their average position, that their average concentration, is proportional to the ground state wave function. That's the idea. Now there are a couple of Python tricks I want to point out to you guys. Here's the basic code, which of course you can read. I'm not going to explain every single line, but the main point is this flat non-zero function is probably the most different, most distinct function to one you've used before. And what it does is it computes the indices of an array that satisfy a certain condition. So flat non-zero returns a set of indices where this number is greater than 0. This number is described in the paper that I'll hand out in class today. But basically it's a measure of whether or not we want to keep the walkers around in a certain location, or we want to kill them, or we want to create more. So if the condition is satisfied, we want to keep these walkers. if this condition is satisfied, we want to actually make more walkers, and if neither of these conditions is satisfied, then the walkers, we want to let them go. So basically, in regions where the potential is low, we want to make walkers. In regions where the potential is high, we want to destroy walkers. And the flat non-zero is an easy way to go find the indices of walkers that satisfy a certain criteria, goes and pulls those walkers out, and the nice thing about these functions is that they're very efficient, and we can use them without having to write a bunch of loops. So we don't have to iterate through all the walkers to discover which ones satisfy a condition. We simply call flat non-zero. It very efficiently finds all the indices where this condition is satisfied. Very efficiently goes and pulls those guys out. And that's the way the thing works. And now let's look at a demonstration of that code to see what it actually does, and we'll be right back. To get really good results, and we're only running 1,000 walkers, so we're going to find out that the biggest limitation to this algorithm is time. It takes time for the thing to converge, and that's where the parallel computing comes in. Later in the semester, we'll be invoking multiple computers working in tandem to compute Monte Carlo quantum ground state wave functions. All right, very good. Finally, let's just quickly review the variational principle. The notion of the variational principle is that if you compute the expectation value of the Hamiltonian using any old wave function at all, the number you're going to get is always going to be greater than or equal to the ground state energy. So that suggests a way to discover what the ground state wave function is and what the ground state energy is. You just parameterize a wave function any old way you like, superpositions of Fourier terms or exponentials or Gaussians or whatever you think is going to give you a good answer, and then you simply adjust the parameters of that wave function to minimize the expectation value of the Hamiltonian. Assuming you know the Hamiltonian, you can always calculate an approximate wave function and compute the expectation value of the Hamiltonian, and by fiddling with the parameters of the wave function, you can make the expectation value as small as you like. So that's basically the idea of the variational principle. We're going to get some experience with that in the next couple lessons to see how that works, but that's the notion, and that's really all there is to it. All right, we'll see you guys next time. Hey guys, welcome back. It's time for lesson 17. We're going to apply the variational method in a couple of contexts, and we're going to talk about some homework problems. This is the last lesson before the next exam, which will be lesson 19. Lesson 18, of course, is just going to be our wrap-up and review, so there's no formal new material that day. It's all about getting you guys ready to take an exam about this stuff. So let's march ahead. I want to mention Computing Project 5, which won't be due till after the exam, is the application of the variational method to some problem of your choice. Now, the handout is written up about the helium atom, but in the spirit of broadening the scope of these things and giving you guys more choice about what you do, I was going to suggest that you could also study the hydrogen the negative hydrogen ion. That's a hydrogen atom, a proton basically, with one extra electron. There's a homework problem about that. In fact, there are a couple that relate to that. Then there's the lithium plus ion. Notice that all three of these, the helium atom, the negative hydrogen ion, and the positively charged lithium ion, are all systems with a nucleus and 2 electrons. So they have a lot in common, but they are different systems. And another one that might be interesting is the hydrogen molecular ion. So that would be 2 protons, not in the same nucleus, but separated by some distance, that share only 1 electron. So we have 2 protons sharing a single electron. That's another case that we can handle with the variational method. We're going to look at the neutral hydrogen molecule for project 8. At least that's my proposed context, but we'll get to that later. Anyway, in this time, and look, if there's another system that you're interested in that you can attack with the variational method, then go right ahead and do it, and I will accept that as your competing project 5. So as long as you're applying the variational method in some way, you're good. Okay, let's talk about a homework problem. This is extending the problem we did for the last homework. Now, for the last homework, what you did was you took the infinite square well, which is our old buddy, and you added a potential, which was anti-symmetric about the midpoint of the infinite square well, and you computed the perturbed wave function and the perturbed energy of that system using non-degenerate perturbation theory. That was the idea. What I want to have you guys do now is to attack the same problem as a variational method problem. So the idea is you think of the wave function as a little bit of the ground state plus, or mostly the ground state, it's almost all the ground state, plus a little tiny bit of the first excited state. And how can you think of that as a variational method? Well, you can think of it as a variational method by imagining computing the expectation value of the Hamiltonian, minimizing it with respect to variation in the parameter beta. Now, one thing about the variational method, it's extremely important that you normalize the wave function. When we worked out the wave function for the degenerate perturbation theory, we didn't worry too much about normalizing in the end. We just said it was the ground state plus some dimensionless parameter times the first excited state. It turns out the normalization is 1 over the square root of 1 plus beta squared. But we didn't worry about working that out. We could get the energy without worrying about the normalization. We got a correct value for the first order correction to the energy without worrying about the normalization constant. And the reason is that the normalization constant is second order in beta. As you can see, it's got a beta squared in it. But when we're using the variational method, the fact that the parameter shows up in the normalization constant turns out to be important. You need to compute the expectation value of the Hamiltonian to second order in beta so that when you minimize it by taking the derivative, you'll have something useful left over. You can't minimize a linear function of beta. It's got to be at least quadratic in order to get a minimum. So you have to keep beta up to second order, and it does make a difference. So that's the idea. You keep terms in the expectation value of the Hamiltonian up to second order in beta. If you keep all orders of beta, it's kind of a hideous expression, and you don't really learn a whole lot. Excuse me, you don't learn a whole lot more anyway. If you wanted to go to higher order in beta, you'd have to include the n equals 3 state and other things that make it more complicated. So I want to keep it simple, but you can't keep it that simple. You have to go up at least to second order in beta. What I want you to do is to show that beta turns out to be alpha divided by 3 times the energy of the ground state. That's the same result we got with degenerate perturbation theory, so that's comforting. You can also show that the energy that you wind up with turns out to be the ground state energy minus alpha squared over 3 times the ground state energy. In other words, by adding this potential and having this perturbation take effect, the energy is actually lowered from the ground state energy. Now, I want to think about this a little bit. What is it that's exactly happening? You could think of it as a trade-off of kinetic energy to potential energy. If you turn up beta, what are we actually doing? We're incorporating some of the first excited state. Notice that the first excited state is the sine function that has 2 antinodes. It's got one on the left of the center and one on the right of the center. And if you turn that up, it's going to shift the probability distribution to the left. By shifting the probability distribution to the left, we go down in potential energy because the potential energy is lower on the left than it is on the right. So by that logic, you'd want beta to be as big as you could get it. The problem is that beta is the amplitude of being in the n equals 2 state. And of course, the n equals 2 state has 4 times the kinetic energy of the n equals 1 state. So by turning beta up, we're going down in potential energy, but we're going up in kinetic energy. And so the
minimum total energy happens when beta has just the right value to minimize the Hamiltonian expectation value. And of course, that is when beta is equal to alpha divided by 3 times the ground state energy, as we showed. But we didn't treat it in the perturbation theory. We didn't treat it as a minimization problem. But you can see that using the variational principle, you get the same result, but you can think of it as minimizing the expectation value of the total energy. In other words, we got a new ground state with a lower energy than the original ground state. But that ain't all, because there's another way we can attack this problem. We can treat it as an eigenvalue problem. So I'd like you to do that as the second part of the homework. I want you to show, using the unperturbed states as a basis, in other words, the ground state and the first excited state, n equals 1 and n equals 2, show that you can write the Hamiltonian this way, where alpha is the same definition we used before. It's minus the matrix element between n equals 2 and n equals 1 with the perturbation. And what you have to do is find the eigenvalues and eigenvectors. What you can show is that the eigenvector is the ground state plus beta times the first excited state. And if you want to normalize it, you can, but you don't have to. I mean, the eigenvectors, of course, are eigenvectors regardless of normalization. And what you can show is that the eigenvector has the property that beta is alpha divided by 3e1, again, same result, and that the energy of the low, now when you get eigenvectors, you're going to get 2 eigenvectors and 2 eigenvalues. We're really only interested in the ground state, the new ground state, so we want to look at the low energy eigenvector and the low energy eigenvalue. You can also learn by studying this that the first excited state also gets shifted, but it gets shifted up by the perturbation. And that also kind of makes sense if you think about it, but we don't have to think about it right now. Right now, I just want you to focus on what happens to the ground state, what happens to the energy of the ground state, and what happens to the composition of the ground state in terms of the unperturbed states. And so for board work today, we'll get started on these 2 problems. Hopefully we can make some decent progress, and we can also talk about the computing project. We can talk about what's bothering you guys and stuff like that. But that is the job for today. See you next time. A really quick note before we start the actual lesson. I just wanted to point out a couple of things. It's come to my attention that there is a population in the class that is feeling like we're doing too much theory, and this last couple of chapters has been a lot of theory. I'll acknowledge that. This one next chapter, the WKB approximation, is also fairly theoretical, but it's just one lesson. I'm going to just move on, and we'll get directly to some applications, including lasers, laser cooling, time-dependent problems, and hopefully that will be more palatable for those of you who are eager to actually see some real numbers and work with actual applications. I hope that helps, and we'll see you soon. Hey guys, I've got a quick set of slides here for lesson 20. It's actually not that complicated, so maybe this will be easy. All right, so let's talk about what is the WKB approximation. What are we going to do with it? Basically, there's 2 primary applications. You can do approximate bound state energies of various systems, and you can handle tunneling. So most of the time you're working in one dimension, although there are ways to make it work in higher dimensions. But let's talk about the basic idea. The notion is, if I've got a potential that's fairly slowly changing, and in such a way that the wavelength is short, say, compared to the distance over which the potential changes a lot, then I can approximate a sort of local phase, or local spatial frequency, local wave number k, using the kinetic energy plus potential energy is equal to a constant. And that gives me a way to estimate what k is, and then I can integrate k dx in order to get the local phase. So the notion is that the wave function goes something like e to the I integral k of x dx, instead of just k times x, where k is a constant. K is now a function of x, and so to get the phase we need to integrate it. And then there's the notion that it goes like 1 over the square root of the wave number, and that's a simple consequence of the fact that remember, wave numbers like momentum, so as the momentum gets larger, the probability of finding the particle at a place with high momentum is less than the probability of finding the particle at a place with low momentum. But this is a very weak dependence, because notice that the amplitude goes like 1 over the square root of k, but k goes like the square root of the energy, or the kinetic energy. So if the kinetic energy doubles, the amplitude is only going to change due to this factor out in front by about 20%, because it's the square root of 2 and the square root of that. So it's not a very big effect. In order for the amplitude to change by a factor of 2, then the kinetic energy has to change according to that factor out in front, the amplitude factor, by something like a factor of 16. So a lot of times we can just ignore that factor out in front and just worry about the phase. In fact, the phase is all you really need to get the bound state energy. The idea is, if I've got some kind of a potential, let's say, that varies in space, and at any given energy, the notion is that there will be some turning points. And so the idea is that the total phase between the turning points has to be something like an integer number of pi. If you think about a round trip, if it traverses the space between the turning points twice, and you want a total phase change of 2 pi, then between the turning points you'd want a phase change of pi. Now, the nature of the turning points turns out to affect the details of exactly what you get. It turns out that if you have a hard boundary, like an infinite square well boundary, the wave function goes to 0, and the phase starts then at a definite place. But if you've got a soft boundary, like this depicted here, then the wave function doesn't go to 0 at the boundary, and there's a little bit of sloppiness in the phase, and that's we'll talk about that. And also, of course, the point is that inside, where the potential is less than the energy, you get a sinusoidal behavior. But if you look at the integral up there, if you go back and look at the definition of k, when v is greater than e, then the k becomes imaginary, and of course this turns from a complex exponential to a real exponential. And we expect to see decaying exponentials outside where the energy is less than the potential. So here's a typical example how it might turn out. Notice that there are turning points, and at the turning points the general behavior of the wave function goes from sinusoidal to exponential. And you also notice that the wave function does go up a little bit as a result of the kinetic energy dropping, but not a lot. Now here's the thing. You see that the wave function spills over the turning point. I guess I can't exactly point here, but anyway, if you look at the right turning point, the wave function, it behaves as if it could continue sinusoidally and go to 0 a little bit past the turning point, and the same way on the left. We're going to find out that represents basically an eighth of a wavelength. In other words, there's an eighth of a wavelength shift when the boundary is soft, as is depicted here. But if the boundary is hard, like an infinite square well, or a point where the wave function goes to 0, then there is no spillover. The wave function goes to 0 right at the boundary. And we'll work some examples in class and see how that turns out. The other thing is, if you look in phase space, if you look at k as a function of x, what you get are these sort of phase space trajectories. You can think of these classically. This could be like an oscillator that's oscillating back and forth. It's got turning points. Each of the lines here represents a line of constant energy. But the bound states occur when the area enclosed by one of these curves is 2 pi greater than the area enclosed by the previous curve. In other words, if you know one bound state energy and you can draw the curve of constant energy for that bound state, the next bound state happens when you get an additional 2 pi of phase. And so the the area in these ellipsoids, I guess that this is a simple harmonic oscillator potential, but the area between these neighboring bound state energies happens to be 2 pi. the area of the central one depends on the boundary conditions. So if the boundary conditions are hard on both sides, the area of the central one is 2 pi. If you got one soft boundary, then you take away basically pi over 2. If you have another soft boundary, you take away another pi over 2. And that's how you get the energy of the simple harmonic oscillator ends up being n plus a half. That half comes from the area of that central guy. And the last application that we're going to deal with is tunneling. You guys remember tunneling from last semester. It wasn't really in the book, but I talked about it anyway. What we talked about last semester was actually the WKB approximation. So you take this expression that we cook up by assuming that the potential changes slowly compared to the wavelength, and then you see what happens when V is greater than E. When that happens, the K becomes imaginary, so we think of this as a kappa. You define kappa to be, it's the same definition as K, except the V and the E are swapped. So now kappa is real, and you plug that in to the WKB approximation, and you get an expression for the relative amplitude on the right side of the barrier compared to the left side of the barrier. So, and we've done this before, so you guys don't really have anything new to learn here, but I just wanted to point out that that this is the WKB approximation that allowed us to make this claim, and it really isn't that hard to use. All right, well, that's enough rambling for today. I think we'll see you guys in class. Okay, here we are with lesson 21, and it's the time-dependent perturbation theory. I'm going to focus on an application, since I want to try to consider applications more frequently. So I've tailored this whole conversation around the issue of what happens when an electromagnetic wave interacts with an atom. Now, many of the interesting situations occur when the frequency of the electromagnetic wave matches an energy difference between two particular states. And in that case, you can pretty much ignore all the other states because their effect on the situation is negligible, and just focus on the two states that are involved in the interaction with the electromagnetic wave. And I'm only going to consider today a monochromatic or a exact single frequency electromagnetic wave. And next time we'll see what happens if the electromagnetic field has more frequencies in it. But today we'll just focus on a single frequency. So let's get started. The idea is to imagine you have an unperturbed system, an atom just sitting there, and then a time-dependent perturbation comes along and affects it in some way. The notion is that we can describe the atomic quantum state as a superposition of a little bit of state A and a little bit of state B. And we're going to further assume that we start out in state A and we make a transition to state B. Now normally, if there's no perturbation, the Fourier coefficients, the amplitude to be in state A and the amplitude to be in state B, are constant. They don't change in time. But what we're going to do is to incorporate, we're going to solve the Schrödinger equation by permitting the CA and CB now to become functions of time that evolve according to the effect of the perturbation. So that's the idea. So here's the Schrödinger equation. We plug in the Schrödinger equation as a little bit of the original unperturbed Hamiltonian plus the perturbation. And when you take out the terms that cancel, of course, you know that the unperturbed Hamiltonian acting on state A just gives you the energy EA and so on. And I'm going to define omega A to be EA over h bar and omega B to be EB over h bar in the normal way. Anyway, when the smoke clears, you end up with this expression. So notice that there are derivatives of the coefficients in there. They come from the derivative of the wave function, which of course is got products of these coefficients and e to the minus I omega t and so on. What I want to do now is to hit with A or B from the left, and we get these expressions. I'm using the shorthand H prime AA, excuse me, is the matrix element between state A and state A of the perturbation and so on. We get these two expressions, and they are expressions for the time derivatives of CA and CB in terms of the current values of CA and CB and the matrix elements of the perturbation. So notice if the perturbation is 0, CA dot and CB dot would be 0, which just means they're constant, which would be the case if there's no perturbation. So I also want to focus on a case that's generally true, a situation that's generally true, and that is that the diagonal matrix elements are 0. So let's assume that those guys are 0. There's a nice problem in Griffiths that encourages you to investigate what happens if they're not 0, and the answer is not very much interesting happens. You just add or subtract a constant to the energy, essentially. But it doesn't have any real effect on transitions, which is what we're interested in today. So let's just focus on the case where their diagonal elements are 0, and that simplifies the equation somewhat because it gets rid of those CA terms in the CA dot equation and the CB term in the CB dot equation, and you just get that CA dot is proportional to CB and the matrix element between the AB state in the perturbation, and CB dot is proportional to CA and the matrix element between the B and A states of the perturbation. So notice what that says is CB dot, the perturbation basically connects CB with CA. If CA is not 0, then it gives CB dot a value. And if CB is not 0, it gives CA dot a value. So the amplitude to be in state B is going to change if there's a large amplitude to be in state A and there's a connecting matrix element through the perturbation. So here's the idea. Let's say we started out in state A at t equals 0. How do we express that? Well, you just say CA is equal to 1 and CB is equal to 0 at t equals 0. So that means the system is definitely in state A. And let's further assume that H prime is in some sense weak. So that means that the rate of change of B is going to be slow, say compared to omega naught or omega B and omega A. Oh, by the way, I snuck in here a definition. I'm defining omega naught to be the difference in frequency between state B and state A. I don't know if you caught that. I should have said something back in those equations, but if you look at the top of the screen, you'll see that I've substituted omega naught for the difference omega B minus omega A. So what I can do then, if H prime is weak and CB is 0, then I can forget about CA dot. It's not significant because CB is 0 and H prime is weak. But CB dot, because CA is 1, CB dot is not going to be negligible. And so I can simply integrate that equation, substituting for CA. I'll just put in 1. It's a constant value. And I get an integral that I can evaluate. And I'm interested in particular in electromagnetic oscillation. So electromagnetic fields. But we're talking about optical fields where the wavelength is many, many times the size of an atom. So I can just assume that I can calculate the matrix element H prime AB and H prime BA. It's going to turn out, we'll talk about this a little more next time, but as we've seen before when we talked about the effect of a constant field on various things, harmonic oscillators and square wells and so on, it's proportional to the matrix element of the position. And that's simply because the wavelength is so long that the field near the atom is essentially a constant in space, but variable in time. So it's just a constant field multiplied by a cosine. That's the idea. And I'll go ahead and put that perturbation in, and you can see that what we get is the integral of a cosine. That's an easy integral to do. We break the cosine into e to the I e to the plus I omega t and e to the minus I omega t, and we simply crank it out. Now, it's not a very enlightening result, unfortunately, so I'm going to make what people often make in this business. I'm going to say, let's imagine that omega is very nearly equal to omega naught. So that means if you look at these two expressions, the omega plus omega naught is going to be much, much, much greater than omega naught minus omega, or omega minus omega naught. And for that reason, that first term in this expression is so small, I can basically neglect it compared to the second. That's the idea. This is the so-called rotating wave approximation. And if I make that approximation, this expression simplifies. I can kind of factor some things out. I can convert that numerator into a sine function by factoring out an e to the I omega naught minus omega t over 2. And we get the following somewhat simplified result. And I can use that to compute the probability. Now, the first thing you'll notice about the probability is it's not a constant in time. In fact, it oscillates in time. So, and it oscillates with the frequency that goes like the difference between the electromagnetic wave frequency and the difference in frequency between the two states in question. So the probability ends up looking something like this. Of course, it has a maximum value that depends on the detuning. Detuning is a measure of how far the electromagnetic wave frequency is from the resonant frequency, omega b minus omega a. And of course, it's proportional to the matrix element of the perturbation, VAB, the amplitude of that matrix element between the two states. That's the idea. And also the period of that oscillation depends on the detuning as well. So if the detuning goes to 0, the period becomes very large. So you can think of it's almost like beats. There's almost a beat between the electromagnetic field frequency and the resonant frequency. Also notice that the probability blows up, the maximum probability blows up if the detuning goes to 0. This is a consequence of the fact that we only did the one term in the perturbation series. This is the first non-zero term in the perturbation series, which generally you'd have to do an infinite number of them to get the exact answer. So our result is only valid as long as the probability remains small. So that means we either have to look at very short times if omega naught is very close to omega, or we have to look at very large detunings, stuff like that. In a little bit we'll do the exact analysis, and we'll see that it comes out sort of similar, but it has no such restriction. So we'll see exactly what happens even if the detuning goes to 0. Let's look at the probability as a function of frequency at a given time. So at a given time, if you look at the probability as a function of omega, you'll notice it looks something like this. It looks like a sinc function, sinc squared actually. It's sine x over x, or sine something times omega divided by omega squared. And it has a definite peak. That peak occurs at 0 detuning, and the width of the peak is quite interesting. It depends on time. So the longer you run the field, the narrower this peak becomes. Now this goes back to the time-energy uncertainty relationship. Remember that the longer you run, the longer an experiment takes, the more precise the energy has to be. This is basically what this is saying. If you run the field for many cycles, then in order to get any appreciable probability of being in the excited state, then the detuning has to be very small. If the detuning is very large, you end up outside of this range, omega naught plus or minus 2 pi over t, and you don't get any appreciable probability. So that's a fascinating result, and we'll probably talk about that more when we talk about what happens when you introduce collisions. and what happens when you have more states that the thing can go to, for example, in an ionization or something like that. But let's go back and start over again. You know, I made that rotating wave approximation where we said omega naught plus omega is much, much greater than omega naught minus omega. I made it after we had already done the first term in the perturbation series, and I had done the integral solution for CB dot, or for CB. Let's see what happens if we put it in at the beginning. In other words, we make the rotating wave approximation now, before we do any integrals or anything. We say that, well, let's let HAB prime, essentially what I'm going to do is to take out instead of putting in cosine, which is e to the I omega t plus e to the minus I omega t, I'll get rid of the minus I omega part and only leave in the plus I omega part. This has the same effect as that rotating wave approximation, and but it turns out if you do it at the beginning, you can actually solve this thing exactly. So let's do it. We'll make that substitution, put in the perturbation, and I'll actually combine that in the exponential as a single exponential. What we're going to do is to differentiate the right-hand equation and substitute that into the left-hand equation, essentially. Let's go ahead and do it. If we take, I'm going to define delta to be the difference between the resonant frequency, which remember is the difference between the B and the A frequency for the system, and the electromagnetic field frequency. So we're going to call that delta. And I'm going to put delta in parentheses a lot of times so we don't think it's an operator that takes the difference between two values of a variable, but it's actually a value. So I'll take the derivative of the right-hand expression, CB. I'll get CB double dot, and let's see what I'm going to get. I'm going to get a CA dot, and I'm going to get a CA with a delta coming downstairs, and I'll solve the right equation for CA and plug back in to get something in terms of CB dot. I'll solve the left equation for CA dot. It's already solved for CA dot. I'll plug that in, and after a lot of algebra, which I'm not going to reproduce, you end up with this expression, which is a simple second-order differential equation for CB. Notice it's you got a CB double dot, a CB dot, and a CB. This is screaming for a characteristic equation. If I assume CB has the form e to the lambda t, CB double dot, I get a lambda squared, CB dot, I get a lambda, and CB, I get nothing, I just get a 1. And I can produce a characteristic equation that looks something like this. It's just a quadratic that I can solve for lambda, and I get 2 roots for lambda. So we get these 2 roots, and the idea is to sort of factor things out. Notice that everything in the radical is negative, so that means it's going to be imaginary. We can factor that I out. I want to make a substitution. I want to define omega r, the Rabi frequency, to be what I get in the radical when I move the 2, the 1/2 in fact, multiply that through, and notice that it's the square root of the sum of the squares of the detuning, half of the detuning squared, plus half of VAB over h bar squared. And so the detuning and the size of the matrix element together determine the Rabi frequency. In the case when the detuning is 0, of course, you're just going to get the matrix element. But if I put all that in, I get a nice simple expression for lambda with the 2 different roots. I can put that back into my expression for CB. And notice that because there are 2 different roots, that means the general solution is going to be a superposition of e to the plus I omega RT and e to the minus I omega RT. But we also have to remember that the initial condition was that CB was 0, which means that A and B can't just be anything, but in fact B has to be negative A, because when you plug in t equals 0, the whole thing has to add up to nothing. And the only way you can do that is if B is equal to negative A, so I can rewrite the
e to the plus I omega RT minus e to the minus I omega RT as a sine function, and get rid of the b since it's only minus a, and I get a simple expression which I can plug back in and figure out what CB dot is. Remember that CB dot was also related to CA, so I can use this to find CA. If I solve for CA, I get this hideous looking expression, but remember that at t equals 0, CA was supposed to be 1. So I can demand that when I put t equals 0 in here, CA is 1, and that tells me that all that junk has to be 1, which gives me an expression for A. So now I've got the boundary condition satisfied, or the initial condition satisfied, excuse me, that CA is 1, CB is 0, and that demands that A have a particular value. I can put that back in and finally have an expression for CA that's completely in terms of known things. And then that also determines CB, because once I have A, I can plug that back into the expression for CB, and I get general expressions for CA and CB as a function of time in terms of the detuning and the Rabi frequency. Now there's a special case I want to talk about, and that's when the detuning is equal to 0. If the detuning is equal to 0, then capital delta is 0, and the Rabi frequency reduces to VAB over 2H bar. If I plug that back in, I get a very simple result. I get that the A coefficient just looks like cosine, the B coefficient just looks like minus I times sine, and that means that the probability of being in the A state and the probability of being in the B state simply oscillate between 0 and 1 with a frequency equal to the Rabi frequency. Now I want to point out a couple of things. Both of these results, the first order perturbation theory result and the Rabi result, this so-called rotating wave approximation, are only valid if there are no other influences. So that means that, for example, no collisions, no other stuff going on. And in addition to that, they're only valid for a single well-defined frequency. And next time we'll generalize that a little bit. I'll even get into the field theory and how you can use field theory to treat the electromagnetic field not as a external classical electric field, but as an actual quantum mechanical beast in and of itself. All right, we'll see you guys next time.
Okay, welcome to Lesson 22. We're going to talk about quantized electric and magnetic fields today, and spontaneous transitions. So let's start by discussing what happens if I have a box with only one mode of radiation. And let's just remind ourselves about Maxwell's equations that relate to the electric and magnetic fields. There are basically two of them we're going to be dealing with today, and we're going to be talking about regions where there is very little charge. So we're going to ignore. So we're going to talk about the effects of putting charges in here as a perturbation. So we're going to quantize the fields, assuming that there are no other charges. So that means in the curl of B Maxwell equation, there is a term that has to do with the current, but there's not going to be any free charge. And also the divergence of E and the divergence of B we're going to assume are both 0, since there's no free charges anywhere. Under those circumstances, if you wrap these guys around each other, you'll find that you get a wave equation, and the wave equation has solutions which, in the spatial part at least, go like the sine and the cosine of kz, where k is a number that is set up to satisfy the boundary conditions, and in this case the boundary conditions are going to be that the electric field goes to 0 at the ends of the cavity. So we can assume the cavity has conducting walls or something. And let's remind ourselves how the curl works. Curl is a vector operator that acts on a vector field, and in this case, if you apply it to a field that only has an x component and it only depends on z, so the only thing that's going to matter is the ddz part of Ex, and if you work that out, it turns out to be Dex dz j hat. So that's the part that matters. Remember that the middle column, and you do a determinant, the middle column gets a minus sign, but then the ddz Ex also gets a minus sign, and those two minus signs cancel out, and you end up with positive Dex dz. And the thing points in the j hat direction. But of course, if you evaluate that, you notice that you go from sine to cosine. So at least the spatial part of B, because the curl of E has to equal minus the rate of change of B, the spatial part of B has to go like cosine. So that's something worth remembering. And then let's also go ahead and evaluate dE dt. I'm going to assume that the time dependence of the field is proportional to this thing I'm going to call Q. Q is just some function of time, classically. Well, I don't know what it is yet. I'm going to work it out. But I want it to have units of length. So what I've done is to divide Q sub n, which would be the nth mode. That n is the nth mode. So Q sub n is going to be divided by some length parameter. Now, it's not necessarily the length of the cavity. It's just something that has dimensions of unit of length. That makes the dimensions of this thing work out. E0 is some base electric field amplitude. Q is some like a Fourier coefficient, but it depends on time, and it has units of length. And then the L is just some parameter that has units of length, which will work out later. Okay, it's going to end up going away, but we'll see how that happens. So let's go ahead and look at the second of Maxwell's equations. The curl of B is related to the time rate of change of E. Now we know that the spatial dependence of B has to go like cosine, so that the curl of E equation works out to be minus dB dt. But I've come up with a new time-dependent function for B, which I'm going to call P. The reason I'm calling them Q and P will become clear momentarily. But P is going to have units of momentum. So to make it have units of momentum, in order for the units of this whole expression to work out, I need to divide by something with units of momentum. And so I'm going to divide by a mass times a frequency times the same length parameter that I had in the other equation. And at this moment, I'm not going to explore what those actually mean, but they're just letters, basically, that scale the magnetic field. Again, the curl of B is expressed in this way, and it works out to be minus dB dz times I hat. Of course, dB dz is related to the cosine. If I take the derivative of cosine, I get minus sign, and the minus dB dz and the minus sign cancel, and I end up with a plus sign function. And I get out, of course, a factor of k sub n because I've taken the derivative with respect to z. Also, taking the time derivative of B, you notice I get a p dot. That's basically it. And now let's rewrite those two Maxwell's equations in terms of the results we just cooked up, and I get these monstrosities. But you'll notice a bunch of stuff is going to cancel out. So for example, you notice that the L's go away, and the cosines and the sines go away, and what I'm left with is a couple of equations that relate the Q's and the P's. Now, we know from studying electricity and magnetism that if I've got an electromagnetic wave in a cavity, that the electric and magnetic fields are connected to one another, and they're proportional to one another in a sense. And so I'm going to put in that proportionality. I'm going to put in that B naught is equal to E naught divided by C. And I'm going to put in that C is omega divided by K. These are just the definitions of C and K and omega. And if I do that, an interesting thing happens. These two equations, which look so hideous, the E naughts end up canceling because of this substitution. And some of the other things go away, and I get two equations. I get that P is mq dot, and P dot is minus m omega squared q.
Well, the first equation is just the definition of momentum, mass times the rate of change of position. If I think of Q as kind of like a position thing, and P is like a momentum thing, then P equals mq dot is just the relationship between the derivative of position and the momentum. And the next equation is basically Newton's second law for a simple harmonic oscillator. P dot is minus kq. K is m omega squared. So, and don't confuse the spring constant k with the wave number k sub n. Those are not the same thing. M omega squared is the same as like a spring constant. It's a restoring force. So what we find is that the equations of Maxwell, which are electromagnetic field equations, can be mapped onto the simple harmonic oscillator through this sort of bizarre parameterization. But that's useful. So SHO, simple harmonic oscillator, that's useful because we know how to quantize the simple harmonic oscillator, and the procedure is exactly the same. We know that Q and P are non-compatible observables that have a non-zero commutator. We know that the Hamiltonian can be expressed in terms of the fields. Let's go ahead and do that. Let's plug in our definitions of the fields. We stick those guys in there. We make our substitutions. We integrate over the size of the cavity. We get the volume of the cavity now appears here, and if I make the substitution that E naught looks like this, in other words, I've just defined E naught to be this. Again, I want you to suspend your disbelief for a moment to see where this is going. But if I define E naught to just be a magnitude of electric field that's expressed in this way, then this equation for the Hamiltonian reduces to this. But that's just the Hamiltonian for the simple harmonic oscillator. And we know the simple harmonic oscillator already has a length parameter. It's the oscillator length. And we can express Q and P operators for the simple harmonic oscillator in terms of raising and lowering operators. A plus and A minus is what Griffiths uses. The rest of the world uses A and A dagger. So I'm going to switch to the notation of the rest of the world, since most of this, none of this material is basically in Griffiths. So A dagger is the same thing as A plus, and A, without any notation, is the same thing as Griffiths A minus. If I plug those two definitions for Q and P into the Hamiltonian, I get the following result, which is that the Hamiltonian is h bar omega times A dagger times A plus a half. And you know A dagger times A is nothing other than the number operator. It measures the number of a pure quantum state, an eigenstate of the Hamiltonian. And so this just says that h bar omega times the quantity n plus a half. Okay, now let's take that. In order to make this all work out, I had to assume E naught was equal to this bizarre expression. Let's plug that back in. Plug that back into our field, and then put all this stuff together. We'll put in the operator for Q. We'll put in this square root goober thing for E naught, and we'll go ahead and plug that into the formula for the field. And let's see what all comes out. Notice some stuff cancels. The L squared in the numerator of the E naught expression and the L in the denominator of the electric field expression cancel. So this length parameter that I introduced just to keep the unit straight ends up canceling in the end. And when the smoke clears, what I get is an expression for the electric field that depends on the raising and lowering operators. The quantum mechanical version of the electric field, once I've quantized the simple harmonic oscillator version of Maxwell's equations, turns out to look like a displacement. It looks a lot like the displacement operator for the one-dimensional simple harmonic oscillator, except that it's got this square root of h bar omega over epsilon 0 v. Notice that when you square the real electric field, the classical electric field, you get an energy density if you multiply by E naught. And notice if you square this and multiply by E naught, you get h bar omega, which is an energy, divided by volume, so you get an energy density. And it's the right thing to put in front if you want to think of one photon being confined, one photon of energy h bar omega being confined to the volume V. So it's kind of a rough concept, but at least it gives you some intuition as to why that factor needs to be what it is. And let's talk about the consequences of this. Of course, you could also make up a similar expression for the magnetic field, but because the transitions we're interested in are primarily related to the electric field, the dipole transitions, I'm not going to worry about that. You could, of course, do it. Just do exactly the same thing I did with the electric field, but for the magnetic field, using the P operator. So let's talk about stimulated transitions. If I have an initial state where an atom is in an excited state, E, and the we're talking about a single mode, that it's in a cavity with a single mode that has n photons in it. That'll be n. So this expression, the first thing is the atom's quantum state, and the second thing is the electromagnetic field's quantum state. And the final state is going to be the atom is in the ground state, and the electromagnetic field now has n plus 1 photons in it. Can I use perturbation theory to look at this? And the answer is yeah, I can. Let's imagine the interaction is the same interaction we've talked about in the past, where the electric field gets dotted into the dipole moment. The energy is really minus the electric field dotted into the dipole moment, but remember the charge on the electron is negative, and so it works out to be equal to the magnitude of the charge on the electron times the x. Now remember, our electric field only has an x component, so when we take the vector electric field and dot it into the position vector, we just get the x component of the field, which is just E, and the x component of r, which is just x. So that's why we have a scalar here of the interaction energy. And I want to write, just like we did last time, I want to write the quantum state as a superposition of the initial state and the final state with a time-dependent coefficient out in front. And now basically the math is identical to what we did last time. We can write out the time derivative of the ground state amplitude. It's proportional to the amplitude of the excited state, and then it's the matrix element between the initial and the final state, and then it's this time exponential with the difference in frequency between the initial and final situation. Notice there's no classical field here. The only field is the quantized field of the cavity with n photons in it, and the perturbation is actually a constant perturbation. So kind of interesting. If we use the same trick we used last time, we can put in what the interaction Hamiltonian is. We get one term that looks like GXE, that's the dipole moment evaluated between the two states, the ground state and the excited state. And we get the electric field operator acting on the n photon state and taking the n plus 1 photon state inner product with that. And notice that A is not going to contribute, but A dagger does, because A dagger takes n photons, bumps it up to n plus 1 photons, and gives us a square root of n plus 1. The other thing is, I'm assuming the atom is in the center, where the sign of KNX is 1, or it's the sign of KNZ is 1. I'm putting the atom at a maximum location of the electric field. If you move the atom around, depending on where it is, you might not be in such a place. In a very large cavity with walls that are very far away, many, many wavelengths away, this isn't going to be a big factor. What you can do then is, instead of dealing with standing waves, you can switch to traveling wave representation. But it doesn't make any difference in the end, so we'll just assume the atom is at the center. Let's go ahead and evaluate those matrix elements.
GXE, I'm going to call that DEG. That's the dipole moment taken between the states E and G, or the expectation value of position taken between the states E and G. And then, of course, the electric field matrix element turned out to be the square root of n plus 1, just like it is for the simple harmonic oscillator. Now we can integrate that, assuming that the excited state n amplitude at t equals 0 is 1, just like we did before. And we go ahead and perform the integral, and what we get is that we have a sine delta t over 2 divided by delta. Notice that there's a square root of n plus 1 there. What if the field contains 0 photons initially? Well, classically, nothing would happen because there's no field there. But because that's a square root of n plus 1, you'd still get something, and that square root of n plus 1 is the reason why spontaneous transitions occur, because the field has some non-zero n equals 0 value, or n equals 0 fluctuation, and that causes stimulated emission with no photons. So that's what we wind up with. We can replace the square root of n plus 1 with 1 if n equals 0, and we still get something. Let's go ahead and talk about what happens if I have more modes. All this has been done assuming a single mode, but of course in a real big box there's going to be many, many modes, and this is one of the reasons why the exact location of the atom doesn't really matter very much, because when you add up all those different modes, you're going to get some. And so let's go ahead and talk about it. Now we have a wave function which is no longer just two components, but now it's got many, many components. It's got, for every mode in the box, there'll be a number of photons in mode 1, a number of photons in mode 2, a number of photons in mode 3, and the atom can be in different states, call those states J. So we'll need a coefficient that depends on time for every possible state that's interesting of the atom, plus every possible number of photons that could exist in each of the very many different modes. So n1 could be 0, 1, 2, 3, 4, n2 could be 0, 1, 2, 3, 4, and so on. So this is a very large space of states, and the question is, what happens when we repeat the same procedure? We can basically go through the same process, but what we need to do is to calculate the probability of each of these different modes for being populated, and that's going to depend on the number of photons in the modes to begin with and the number of photons we're interested in being in the modes at the end. And it's a generally fairly challenging problem. But if we assume that the system starts out with the atom in the excited state and no photons in any of the modes, then the final state is going to be the atom in the ground state and one photon in one of the modes, and then another state will be a photon in another mode and a photon in another mode. So what we end up having to do is to calculate the probability of a photon being in any one of those modes, but we have to add the probabilities up for all the different modes. So basically we take the expression at the top of the screen and add it up, square it first to calculate a probability, and then add it up for all the different modes. That's not that bad. One of the things we have to do is to go back into the mode counting business, which is exactly the same as it was when we dealt with electrons, fermions, and solids, or if you've ever talked about black body radiation, it's the same business. We can switch from k space to omega space. There's not that big a difference between the two. For every k, there's an omega, and omega is just about the energy and k is just about the momentum, but they're still directly related to one another. And then we can convert this sum over modes into an integral. Now here's the thing. The integral is very sharply peaked around omega 0 because of the way the sinc function gets so narrow so quickly. We don't have to worry about the fact that there's an omega squared in the density of states, because omega squared varies very slowly, and the sine function is very sharply peaked. It's a sinc function, really. And if we make the substitution that delta omega, or delta t over 2 is equal to x, and integrate, we find that that integral in a very short period of time reduces to pi times t over 2. So it's just an integral proportional to time. And if I plug that back in, I get an expression for the probability of the thing jumping to the ground state. I've added up all the probabilities of going into all these different electromagnetic modes of the box. One thing I didn't do was to be careful with the polarization. It turns out if you are careful with the polarization, there's a factor that comes in and you end up with a 3 pi downstairs here. But and you can see Griffiths actually deals with this when he talks about stimulated emission, and you can look at his equations to deal with that. Basically, you average the dipole moment over all the different directions that the thing can go, and you get this factor of 1/3 is what it boils down to. And what I want to focus on is the fact that this probability is proportional to time. So that means that as time goes on, the probability of being in the ground state grows. But of course, that means the probability of being in the excited state has to diminish. So we can actually improve our situation by taking that into account. We're going to define the rate of transition from the excited state to the ground state as this expression divided by, it's the probability per unit time. Now, the probability expression is only valid for short periods of time. But what we can do is say, look, if the probability of getting into the ground state has a certain rate, that means it's going to bleed the excited state of probability at the same rate. And what we end up with is it's almost like discharging a capacitor. As you discharge the capacitor, the current drops because the voltage drops, and then the rate at which it discharges drops, and it's basically the same math. You can approximate the rate of change of the amplitude to be in the excited state as half. Remember, it's got to be a half because the amplitude goes, the probability goes like amplitude squared, and so that gives you a differential equation to get the amplitude to be in the excited state. You can then plug that amplitude back in to the perturbation expansion and use it to correct for the time-varying amplitude of the excited state, and you get a differential equation that looks like this. But notice now there's an imaginary part and a real part in the exponential. And the short story is that when you grind through all of that and work out the answer, you end up with an extra factor in front of the probability, and it has to do with the rate at which the thing is losing probability in the excited state. In other words, the distribution of energies in these modes in the box gets spread out, and it gets spread out by an amount that's proportional to the rate at which the excited state is being drained. And that's the idea. We're going to need this because this is critical to understand laser cooling, and that's going to be our next subject. Talk to you soon. Hey guys, welcome back. It's time for lesson 23 on laser cooling. So, can lasers actually cool things? You normally think of lasers as making things hot, like cutting through pieces of metal or firing rockets out of the sky or something. But very clever people have come up with multiple schemes of cooling things down with lasers. I'm going to describe one of them that's used to cool ions in various electromagnetic traps, and see how that works. It relates to the quantum computing because in order to use ions in a quantum computer, you need to cool them down enough that they're in a well-known quantum state. So, first of all, let me point out that if you immerse an ion in a strong laser field, it will periodically produce a spontaneous photon. It'll continuously be excited and then re-emit and excited and re-emit. Some of those emissions will be stimulated emissions, and those don't have any net effect because you absorb a photon and you emit a photon in the same direction, and the net change in momentum is going to be zero. But the spontaneous emissions do produce a net momentum effect, and that's what we're after. So this is a function that describes the number of spontaneous transitions per second
as a function of the frequency of the laser. So omega 0 is the resonant frequency. That's the energy difference between the two states in the ion that the electron is transitioning between, divided by h bar. And gamma, we learned about that last time. Gamma is essentially a damping factor. It relates to the lifetime of the excited state. It's basically 1 over the lifetime, or the rate at which the excited state is depopulated. And just to give you rough numbers, omega 0 tends to be on the order of 10 to the 15 cycles a second. Gamma is more like 10 to the 9, or many times 10 to the 8 cycles a second. And so omega 0 is much, much larger than gamma. Now, if you make a graph of this function, and here I've exaggerated gamma in order to see what the function looks like, but in fact, gamma is going to be a very tiny thing, and it will be an extremely sharp spike. N0 is the number of spontaneous transitions per second if omega is equal to omega 0. And of course, if omega is not equal to omega 0, you get a smaller number than that, depending on how far away you are from omega 0. So that's the idea. Now, the point of laser cooling is you've got this ion that's moving, and you immerse that in a laser beam, and you set the laser frequency to be just a little bit less than the resonant frequency. So omega L is somewhat less than omega 0 by about gamma over 2. The key is you want the laser frequency to be at a point in the curve where the slope is very large. So the notion is a photon comes in, hits the ion, and the ion absorbs that momentum. If a spontaneous transition occurs, a photon is emitted, and there's a recoil momentum that the ion experiences as a result. And the sum of those two is the net change in momentum of the ion. The interesting thing is the absorbed momentum is always in the direction of the laser beam. The emitted momentum is in a random direction. So if you average this over many, many interactions, the spontaneous emission produces no net momentum change. But the laser, always producing a momentum in the same direction, does produce a net momentum change, or a net rate of change of momentum. And so it produces a kind of radiation force, or radiation pressure. And you'd say, well, that's interesting. It kind of pushes on the ion, but how does it cool? The thing is, the average force of this radiation pressure is a function of omega. So it's the momentum of a single photon times the rate at which these spontaneous transitions occur. And if you think about that, the issue is, what is the value of the frequency that you need to put into the function n of omega? And the answer is, you need to put in the Doppler shifted frequency. In other words, the frequency is going to be Doppler shifted by the motion of the ion. If the ion's moving fast, you put in a lower frequency. But what that does is it reduces n of omega because of where the laser frequency sits. It's on this highly sloped region of the function n of omega. If the ion is moving fast, it shifts omega to the left. That drops the force. If it's moving very slowly, or if it moves in the other direction, it'll shift omega up, excuse me, and that will increase the force. So we have a force that varies as a function of velocity. And that turns out to be the important idea. So n of omega has a large slope, and if you think about it, if you put that omega into the function n of omega and expand that as a kind of a Taylor series, what we have is n of omega L plus delta omega, but that's n minus n prime times delta omega. And if you put all that together, notice that n prime is positive, all those other factors are positive, and the minus sign comes from the Doppler shift, and you can see that what we get is a damping effect. So what you see is that you get a velocity-dependent force, or you get a average force minus a velocity-dependent damping factor. Very interesting. Now let's go back for a second and remember that this is an ion not in empty space, but in an ion trap. So there is a restoring force from the ion trap that we worked out several lessons ago, and I have to add this new laser force to that force, and I get a net force that has the restoring force, the constant force from the laser beam, and then the damping force. If I put all that together and take the component of R in the direction of the laser beam, I get an equation that you probably will recognize. It's the simple harmonic oscillator, the damped simple harmonic oscillator equation. You guys have all solved this probably 100 times before, and you know that as long as gamma is less than 2m omega, that the thing is underdamped, and that means there's an underdamped frequency, omega sub d, and if you solve this thing, cook up a characteristic equation and solve it for the frequencies, the two roots, you get a solution that looks something like this. If I make a graph of this thing, it's a damped sort of sinusoid, but the effect of the laser is to shift the equilibrium position by a little bit. That depends on the average laser force, but it does ultimately damp out the motion. Okay, so here is a little demo. I modified the ion trap code. Remember, in the original version that we worked with before, I had put in some artificial damping just to kind of slowly slow down the ion. But what I've done to this in this case is I've introduced this n factor function, which is the basically the broadening factor. I've got the line width squared the line width over 2 squared divided by the line width over 2 squared plus the difference between the omega prime, the Doppler shifted frequency, and the resonant frequency squared. So this is the factor that determines, depending on the Doppler shifted frequency, what the number of photons spontaneously emitted per second is going to be. And then in the loop that computes the new position of the ion, the force responsible for the trapping, the trap forces are computed in a Runge-Kutta, fourth order Runge-Kutta update. And then on each time step, I go through and create a number of photons, generate that number of random numbers to get the distribution of cosines. Now remember, to generate a uniform distribution of solid angles, or a uniform distribution of thetas and phis, you can set the cosine of theta to be a uniformly distributed random number between -1 and +1, and the sine of theta is, of course, just the square root of 1 minus cosine theta squared. Phi is a uniformly distributed random number between 0 and 2 pi. And then sine theta cosine phi, sine theta sine phi, I can compute directly. And then the idea is I give I add up those kicks produced by each of those spontaneous events and add those to the velocity of the ion. So basically, I'm giving the ion an extra little kick in each time step that's determined by the rate at which spontaneous events are occurring, and they're occurring in random directions, in all directions of space. In addition to, of course, the laser beam, which produces steady state, what you call kicks, that's taken care of here. Notice that the kick in the z direction is 1 minus cosine theta. The 1 is from the laser beam. The minus cosine theta is from the spontaneously emitted photon, or the spontaneous transition. Okay, so let's see what happens. I'll go ahead and run it, and you notice we've got the it's the old Paul trap there in view, and there's added here a little cylinder that represents the laser beam, and I'm going to go ahead and start the ion going. I want you to notice at first it takes off in this direction. The laser beam is pushing the ion to the left in this view,
And so the ion never even makes it back to the origin because of the radiation pressure from the ion beam. But another dramatic thing is you can see that the motion in the z direction is seriously damped out. In fact, after only a couple of cycles, it's almost completely damped out. But if you look in the x and y direction, you can see that the motion is still going pretty strong. It looks like a Lissajous figure or something. But in the z direction, all the motion along that laser beam trajectory is damped out. So the thing really does damp. And I want to emphasize that this is actually solving the equations of motion, not making the fast-slow approximation, so you can still see the fast motion in there. Let's see if I can zoom in here to take a look at it. There's the fast motion. And it's simulating the spontaneous photon emissions and the laser absorptions in each time step. So it seems like it's kind of holding water, that this seems to work. All right. Now there is a limit. As the thing cools down, every photon that's emitted produces a little bit of momentum, and that means that the thing gets down to some low temperature, but it never gets below a temperature where Kb is about equal to p squared over 2m, where p is the recoil momentum of a single photon. If you need a lower temperature than that in order to do quantum computing, and unfortunately it turns out many times you do need a lower temperature than this recoil limit, you need to pull some other tricks. And we'll talk about some of those tricks. And in fact, I found a lovely article out of Los Alamos that describes some of the tricks people are doing, and we can talk about those in class. Also, I'll have some board work for you guys to do today relating to this material, but that's the basic idea. See you then. Hey guys, welcome back. It's time to talk about how do you actually make a computer out of these things, and so I want to describe the basic idea known as the Cirac Zollar scheme, and let's talk about what happens if I get several of these ions in an ion trap, and I cool them way down. There are modes of vibration of the system that can happen. You can get different collective modes, and the one that we're going to use is the center of mass mode, where all the ions oscillate in the same direction. Of course, you can imagine other ones where the ions on the left go to the right and the ions on the right go to the left, and so on. But those are higher order excitations, and we want to look at the lowest possible mode we can, and that is the collective center of mass mode. That's all we're going to need for today. And the idea is, because the whole system, that mode is quantized, just like we quantize the electromagnetic modes in a cavity, this mode is quantum mechanical, and so it has a ground state and it has a first excited state. The interesting thing about those two states is that all the ions in the chain are collectively in the ground state or the first excited state, and so you can use that as a mechanism to communicate between the ions. That's kind of the idea. So, for example, the quantum state at any given moment could be that ion A is in its ground state, ion B is in its ground state, ion C is in its electronic excited state, ion D is in its electronic ground state, and then the whole system is in the ground vibrational state. So to specify what's going on with the system of 4 ions, you have to know the electronic state of the 4 ions in the chain individually, and you need to know the vibrational state of the whole system. That's the idea. Okay, now let's look at what the energy levels are going to look like for a single atom or single ion in this chain. Notice that the energy difference between the ground vibrational state and the n equals 1 vibrational state is quite small, whereas the energy difference between the ground state and the excited state, the electronic excited state of a single ion, is fairly large. So the trick is that we can tune a laser to the energy difference between or the difference in energy between the excitation energy of the electronic state and the vibrational state. What this means is if you shine a laser in, h bar omega 0 is the energy difference between the ground state and the excited state. Omega c is the energy difference between the ground state and the first vibrational state of the whole system. And if I have a laser whose frequency is h bar omega naught minus omega c, then if a particular ion is in the excited state, that could stimulate a transition to the ground state in the first vibrational state. In other words, it would force the system into the n equals 1 vibrational state and at the same time stimulate an emission from the excited state to the ground state of a particular ion. That turns out to be the trick to make this thing work. Let's see how it happens. And then I just put the words there that are exactly what I just said, so that when you have a laser detuned to omega naught minus omega c, you'll stimulate a transition into the first vibrational state. But if the atom is in the ground, or the ion is in the ground state, in the 0 vibrational state, there's not enough energy there to get it into the excited state. So you can, by tuning a laser to a particular transition, you can force that transition to happen, and that can get you between n equals 0 and n equals 1 of the vibrational states of the system. Okay, so how are we going to make a gate? A controlled knot. You remember that from last semester? We talked about different quantum gates. A controlled knot happens to be universal. That means if I can make a controlled knot, I can make anything, because by putting controlled knots together, I can build any quantum gate I like. Let's imagine that we have 4 basis states that are going to be our computational basis, with all in the n equals 0 state of the ion chain. So this would correspond to 0, 0, 1, 0, 0, 1, and 1, 1, if in a binary arithmetic kind of sense. I want to introduce 2 operators that are going to enable us to make a C knot. The first operator is U, and if we apply U to the atom A, it's basically a laser pulse that's detuned to the omega naught minus omega c frequency. So if both ions, and we're only going to apply it to ion A, so ion A is the target of this operator, ion B just goes along for the ride. But if ion A is in the ground state, nothing happens, because the laser's detuned and it can't affect ion A if it's in the ground state. But if it's in the excited state, what it does is it forces a transition to the ground state, but it bumps the vibrational mode up by 1. It also happens to have the effect of multiplying the phase by minus I. This is just a question of how long do you apply the laser pulse. Remember that there's going to be some kind of Rabi oscillation, and there's an e to the I omega t, and if you have t be just the right amount of time, you can change the phase as well by minus I, and it doesn't matter what state atom B is in. So if ion B is in the ground state or the excited state, again, it just goes along for the ride, because the laser pulse is hitting only ion A. Okay, now let's imagine another laser pulse, and all this thing does is it changes the sign of ion B. So the idea is this is a laser pulse that acts only on ion B, and let's see what it does. If and it only works if the vibrational state is n equals 1. So by picking the wavelength and the timing of the laser pulse exactly right, and we'll get into this a little bit more next time, but the idea is you can set up a situation where if the vibrational state is 0, nothing happens, but if the vibrational state is 1, then you get a phase change, but only if atom B is in the ground state. If it's in the excited state, nothing happens. If it's in the ground state, you get a minus 1. That's the idea. Then you apply U again to ion A. It does exactly the same thing it did last time. That is, if ion A, if
n is equal to 1, it's the detuned laser. If n is equal to 1 and ion A now is in the ground state, it'll bump it back up to the excited state with the change of phase of -I. And it doesn't matter if what ion B is doing, it just goes along for the ride. And if you apply all three of these together, if you take UA, VB, UA, if you go back and look at all those transitions, you'll see that the net effect is that if ion A starts out in the ground state, nothing happens. If ion A starts out in the excited state, then you either get a nothing or you get a -1 factor, depending on the state of ion B. So if ion B is in the ground state, nothing happens. If ion B is in the excited state, you end up with a net phase change of -1. And that's a consequence of the phases that get added for the various operators. But that's it. Once we have this, we can make a C0. And the trick is you form plus and minus states of ion B using a Hadamard operator. We talked about Hadamard last semester, but you may remember that Hadamard takes the ground state and puts it into a superposition of ground and excited with the plus sign. It takes the excited state and puts it into a superposition of ground state and excited state with a minus sign. And if you apply the W operator that we've just worked out to the system when it's in the ground state of ion A and in plus or minus, it comes out plus or minus again for ion B. But if you're in the excited state of atom A and you apply W, then plus or minus of ion B goes to minus plus. It changes sign. And that turns out to mean that we can make a C0. If you remember, Hadamard is the thing that takes it E to minus and G to plus. And if you form an operator that's Hadamard, W, and Hadamard, you'll see that what happens is that operator, if they're both in the ground state, you get the same thing back. If atom A is in the ground state and atom B is in the excited state, you get the same thing back. But if atom A is in the excited state, it flips atom B from the ground state to the excited state. If atom A is in the excited state, it'll flip atom B from the excited state to the ground state. So basically, depending on whether atom A or ion A is in the ground state or the excited state, ion B either stays the same if ion A is in the ground state, or it flips if ion A is in the excited state. So that is the definition of a controlled knot. So what we have here, I know it's a little complicated, but basically it's a scheme whereby you can take a string of ions and by carefully addressing them with focused laser beams that act for definite periods of time, you can construct a controlled knot gate. And with controlled knot gates, as I said, it's theoretically possible to build anything. All right.
Hey guys, welcome back. We got a quick lesson today. It's some of the technical details of actually analyzing how a calcium ion computer might work, a calcium ion quantum computer. And the first thing we need to look at is the energy levels available, the relevant, I guess, energy levels available in the calcium ion. And the main levels that we're going to be using to actually do calculations are the S1/2 ground state and the D5/2 excited state. Now, one of the things we're going to learn about, actually we already sort of know about it, is that strong transitions between levels only occur if there is a finite matrix element of the perturbation between the two levels. Now, it turns out the dipole perturbation is such that it only produces finite matrix elements between states of opposite angular momentum, opposite orbital angular momentum. So that means that
basically L, capital L, has to change by 1. That's called a selection rule. It just means that in order for the thing to be strongly active, the particular transition has to have a difference in L of 1 between the two states. So, for example, going from an S to a P or from a P to a D is relatively strong, but going from an S to a D is quite weak. And that has it's a double-edged sword. It means you need a strong laser in order to produce that transition, but it also means that once the electron is in the excited state, the D state, for example, it can only decay to the ground state very, very slowly. It turns out it's an electric quadrupole transition, not a dipole transition, and it's very, very weak. The D5 state takes about a second to decay to the ground state on the average, and that's very long compared to the time frame of the calculation that's going on. And so that's good because it means that the calculation won't be spoiled by spontaneous emissions from the 5/2 state to the D5 to the S1/2. So the calculation basis, as far as a single ion is concerned, is between the G ket and the E ket. But there's a lot of other stuff that has to go on, and all these other states play a role. So let's talk about it and see how it works. The first thing we have to worry about is how do we cool these guys down. For that, we need a strong transition. And in the case of calcium, typically what folks do is use the S1/2 to P1/2 transition. It turns out there's another selection rule that says that the transitions are strongest if J changes by plus or minus 1 or 0. And so S1/2 to P1/2 is a strong transition, as is P1/2 to D3/2. And that presents a little bit of a problem, because if you're using the S1/2 P1/2 transition to cool the ion, that means that the population in the P1/2 level is going to be something on the order of 50% on the average. And if there's a spontaneous decay into the D3/2 level, then that's going to be problematic, because the atoms or the ions that fall into that level, it's also a very long-lived level. It takes a long time to decay to the S1/2 state, but it doesn't participate in the cooling, because the cooling happens with the 397 nanometer laser. So because the cooling is happening at 397, it turns out the spontaneous decay of 866 nanometers down to the D3/2 state causes atoms to be lost from the cooling action. And so in order to and also there's a small chance that they can get caught in the D5/2. It's not as strong because that's a delta J of 2, but it is possible. And so what folks do is they put in diode lasers at 866 and 854 nanometers to bump those guys out of the metastable states, the D5/2 and the D3/2, and back up into states that can transition to the ground state. So and through that mechanism, they flush those states out so that ions don't get stuck in the metastable states for seconds at a time. Now, of course, that has a side effect. The D5/2 is strongly coupled to the P3/2, not as much to the P1/2 because delta J is too big. And so that means that the P3/2 state is going to get populated. But it's very strongly coupled to the S1/2. And what that means is that it quickly decays, within nanoseconds or something. And so that's basically how the thing works. So in order to cool the guys down, it doesn't just take the cooling laser, it takes 3 lasers. 2 lasers, the 854 and the 866, need to be there to keep ions from getting stuck in these metastable states during the cooling process. Of course, if you're going to do any calculation, you have to turn those guys off because they would completely spoil the calculation. If the 854 laser were on, it would be stealing population from the 5/2 state and throwing it into the P3/2, and that would, of course, then immediately decay to the ground state. So that would be an artificial route of transition, and so you'd have to turn those 2 guys off. What about actual calculation? So to actually do any calculations, we use the S1 half and D5 half state and the 729 nanometer laser line. To make a measurement, you use the 397 nanometer laser line to stimulate fluorescence between the S1 half and the P1 half state. If the system is in the ground state, if the ion is in the ground state, then that transition will produce a strong fluorescence, and you can actually see the laser light. On the other hand, if the ion is in the D5 half state, then you'll get no fluorescence, and what that means is the thing was in the excited state. So you can measure a 0 or a 1 by shining a 397 nanometer laser at the ion. If it fluoresces, it's in the ground state. If it doesn't fluoresce, it's in the excited state. And that's a form of quantum measurement. The idea is that by varying the polarization, the duration, and the phase of the laser, different computational operators can be realized, such as the U and the V and the Hadamard and so on. And as we talked about in class last time, each of those can be thought of as a rotation of the state in the block sphere. So we're basically using the laser to move the state vector around on the block sphere, and those are equivalent to rotations and reflections and things like that. All right, for the board work for today, I'm going to have you guys compare the level diagram for calcium, magnesium, and barium ions, and we'll talk about the different pluses and minuses, and I'm going to try to get you guys to discover what the issues are with the other ions and why calcium might be preferable. And also I'd like to have you guys attempt to design an electron trap computer. In other words, what if you could trap electrons in an ion trap somehow and use magnetic fields to produce transitions between spin up and spin down. So you use the spin up and spin down states of an electron in a magnetic field to produce computation, C0 gates and stuff like that, and we'll see what the various issues are with that. And that's really all I have for today. We'll see you guys in class. Hey guys, it's lesson 26. I'm not feeling super great today, so this is going to be quick, and excuse me if I don't sound super enthusiastic. I'm just struggling with some health things, so what are you going to do? Anyway, let's move ahead. What I want to do this week is have you guys work through some board work where we actually calculate real values using an ion trap computer, a hypothetical ion trap computer. So let's say there are two calcium ions confined to the z-axis of an ion trap. I want you to presume that the confinement is very strong so that the oscillations transverse to the z-axis in the x and y directions are going to be in the ground state. And so we've cooled the thing down. Just imagine that. Obviously that's a technical issue. You have to actually cool the thing down. But the guys are cooled down, and then just classically, I'd like you to work out, given that the potential along the z direction is a quadratic potential, I'd like you to try to figure out what the equilibrium spacing between the two ions is going to be. These are calcium ions, singly ionized. And then work out, any way you can, what the frequency of the center of mass mode of oscillation is. This is when both ions always move in the same direction. So they're both moving to the right or they're both moving to the left. That's the center of mass mode. And then while you're at that, you might as well go ahead and work out the frequency of the breathing mode. That's the mode where one ion moves to the right, but the other ion moves to the left. That's another mode of a two-ion chain. And see what the frequency difference is between those two modes. That's going to turn out to be important later. But interestingly, the frequency difference between the two lowest modes, or the frequency of the two lowest modes, is related by the same basic relationship independent of the number of ions. So it's kind of an interesting result. And we may have time to work that out. But anyway, it's easiest to work out for two ions. Of course, if you add more ions, it gets more complicated. It's not terrible, but that's what we're going to do. So let's talk about cooling. Imagine that we're using the S1 half P3 halves transition for cooling. That's a dipole allowed transition. I'd like you to work out the recoil limit of the temperature. What is the lowest temperature you can reach using that transition? That'll be enlightening, I think. And then also, assuming that the number of spontaneous photon emissions per second at the laser frequency is 10 to the 6th. I'd like you to work out what the equilibrium displacement of the ion is from its from the z-axis. Remember that the radiation pressure from the laser beam is going to displace the ion from its equilibrium position when the laser's off, and I'd like to have you estimate how far that is. And finally, for the same system, I'd like you to calculate how long it takes for the ion's motion to cool down in the direction perpendicular, parallel to the laser beam. And that'll give you some order of magnitude sense of how long these things actually take to occur. Finally, let's look at computing itself. Remember that the level structure for calcium ions looks something like this, the levels that we're interested in. And remember that the U transition, or the U operator, has the following effect on the various states. We've got ion A, ion B, and then the bus, or harmonic oscillator motion, center of mass motion of the two ions together, the so-called quantum bus. I'd like you to compute the wavelength that would be needed to achieve the U transition. Looking at what you have to accomplish, what wavelength would you need to use to actually do that? And given that we know that the quadrupole transition from D to S, the D5 halves to the S1 half, has a lifetime of something on the order of a second. So that turns out to relate to the width of the transition, the width of that resonance. Is there very much danger of exciting the n equals 2 mode or the breathing mode of the oscillator, of the translational motion of the ions in the cavity? And so that's enough questions. I don't think we'll probably even get through all of them tomorrow, but that gives you a sense of the kinds of questions I want you to think about and the things I want you to be able to do, both on the homework and on the exam. Finally, I'd like to talk a little bit about how to write code that runs on the cluster, because we're getting around the time when we need to start doing that. How do we take advantage of more compute nodes, and how do we just think about calculating things on a cluster of computers? So I've got a little demo here we can watch, and then that'll be all for today. See you next time. Okay guys, so this is a calculation we did back in Computing Project 2. If you remember, we're calculating the integral of e to the minus lambda times dx, and I went ahead and worked out the exact integral here. This is from 0 to infinity, and the exact result is 1 over lambda squared. But the strategy was to use a Monte Carlo approach, where we generated a bunch of random numbers in an exponential distribution, and then computed the expectation value of x using that using x's that are distributed exponentially. So that was kind of a trick to calculate an integral. The reason I'm interested in that kind of calculation is because it turns out to be fairly easy to use a cluster computing system in order to calculate things using that basic approach. So here's the idea. Here's the calculation. You generate n random numbers. You convert those uniformly distributed random numbers into an exponential distribution with the logarithm function, as we discussed before. And then you calculate the expectation value of x divided by lambda. So x dot sum over n is the expectation value of x. And you divide by lambda in order to convert this into a, what you call, normalized distribution. That's kind of the idea. And what you get back is the answer. So let's go ahead and run this. I'll just choose run here, and we'll see what we get. And there's the answer. The Monte Carlo result was 0.2506 and change. The exact result is 0.25. Of course, we know I only took like 50,000 samples, I think 50,000 samples, and so we didn't get a very precise result, but it was pretty close. Now the idea is, how do I run this on a cluster computer? So I've cooked up this module called Handy MPI. So I'm going to bring a new window into the frame, and Handy MPI is a Python module that I'll give you guys to use. It has really several important functions, but today we're only interested in this one called for each. So I'm importing two things from MPI. I'm importing the for each function, and I'm importing the myRank constant. myRank basically is a way to check each processor can check to see what its name is or what its index is in the list of cluster computer nodes. The node that's in charge of everybody else, by default, we're going to use is the 0 node. So down here you'll notice I'm checking. If my rank is 0, then I'm going to print something out. It turns out the 0 node is special. It's called the master node, and it's in charge of coordinating the calculation with the other nodes. But notice everything is the same here, with the exception that we don't call the doCalc method directly. Actually, what I want to do is make n equal to 10,000. 10 is going to be n is going to be equal to 10,000, and then I'm going to multiply here the list that contains only one thing, n, by nodes. And here I have, let's make it 5 nodes. I'm making changes here. Let me just show you what that does. If you're not familiar with list multiplication in Python, if I make a list with a 3 in it, so let's call x equal to 3, and if I say print x, I have a list with a 3 in it, then what happens when I multiply that by a number like 5? It makes a new list, but now it's a list with 5 elements, where each element is the same value, essentially. So that's kind of a neat trick, and it's useful because what I want to do here, I'll tell you the way for each works. You pass in a function, and you pass in a list of arguments. And what it does is to compute the function using each one of the values in the argument. So in other words, if I pass in a list with 5 10,000s in it, it's going to call doCalc with 10,000 once and put the result in a list. Then it's going to call doCalc with 10,000 again and put the result of that calculation in the same list. And it'll do that until it runs out of list. And when it runs out of list, it'll have nodes results. Each result will have come from one of these arguments. So it computes the doCalc function n times, however, well, I should say in this case nodes times, and puts the results in a list. Now notice down here when I get to the bottom, I check to see if I'm the master node, and if I am, I make an array out of the results, I add them up, and I divide by the length of the results array. So I'm taking the average of these different results that came back from the different invocations of doCalc. And I'm also going to print out the exact here. I'll make this. Tell you what, let's do it this way. So the point is, it calls doCalc, in this case, 5 times. But on a cluster computer, it's smart enough to know, it goes out and sort of sniffs around and says, hey, I'm running on a cluster computer. And what it does is to distribute the calculation, the calling of doCalc, on the different nodes. So each node is going to get one invocation of doCalc, and the results are going to accumulate in an array that gets passed back in results. But for each takes care of all the coordination with the different nodes and making sure everybody's doing the right thing and so on. So let's go ahead. Now, here's the thing. If you run this on a system that doesn't have a cluster environment, what it does is it just calls doCalc nodes times, one after the other, and accumulates the results in a list. The beauty of that is that I can write my code on my laptop or any other computer, that whether it has a cluster environment or not, and test it to make sure that it's working correctly. And then when I take the same program and move it to a real cluster with real nodes, it'll do the right thing and pass the computation out. And my homework for this section is for you guys to write any kind of program you like to calculate just about anything you like, but I want you to use this for each method and demonstrate that your code runs faster on a cluster than it does on a single processor or in a single process on a conventional computer. So let's go ahead and run it. If I just run it in this window, it doesn't find an MPI environment, and it comes back with the result. But it's nothing very dramatic. If I were to run the same code on a cluster, it would be faster. Of course, it doesn't always mean it's faster. It depends on the nature of the calculation and how much overhead there is in getting the thing going. And it is quite easy to write programs that run more slowly on a cluster than they do on a conventional computer. And that's part of the business of learning how these things work and figuring out what works and what doesn't and so on. All right.
Hi guys, welcome back. It's lesson 28. It's time to figure out where that scattering amplitude comes from. So remember last time we talked about the solutions to the scattering problem, and that everything boiled down to finding this so-called scattering amplitude. Today's plan is to use the Rayleigh superposition of spherical Bessel functions and Legendre polynomials to expand the incoming wave in spherical wavelets, basically, and then analyze it in those terms. After the GR, we're going to use a different approach, which is the so-called Born approximation, which is basically an integral form of the Schrödinger equation. And it's appropriate in a certain domain, typically short wavelengths and so on. The partial wave analysis is good for low energies, and we'll investigate it right now. So if you remember the situation, we have a target, we have an incoming wave, and we can think of this incoming wave as having sort of plane wave fronts that strike the target and produce scattered wavelets that then expand out into space. That's kind of a schematic picture. The incoming wave has the form e to the ikz. The scattered wave has the form e to the ikr over r. Remember that the 1 over r is needed to preserve probability, and the function of theta tells you how different amplitudes scatter in different directions, basically. So forward scattering would be theta equals 0, back scattering would be theta equals pi, and everything in between. So what does the solution look like? Remember, the basic format of the solution is the sum of these two pieces, the incoming wave and the scattered wave. But this solution is only really valid for large values of r. I guess I should say it's only exactly correct for large values of r. But how do we figure out what f of theta is? We do it by matching everything up in the region where the potential is non-zero. So let's see how that works. Remember what the Schrödinger equation looks like if you express it in spherical polar coordinates. It's this monstrosity. So we need something that satisfies this. It's well known that the e to the ikz part satisfies that. Less clear that the other part satisfies that. So let's see what we have to do. The idea is to first factor the wave function into parts that depend only on r, theta, and phi. And we're going to do this because the potential is spherically symmetric. So for the moment, let's imagine we have a potential that only depends on r, and that means that the phi part is simple. We did this all last semester, so I don't have to repeat the details, but basically you find an eigenvalue formula for the phi part, you plug that back in, you get an eigenvalue formula for the theta part, and this produces solutions which are product functions of theta and phi, the so-called spherical harmonics. And then you finally take all that information and put it back into the r form of the equation, and you get something that looks like this. Now u is called the radial function. It's not the radial factor in the wave function. It's basically r times that, and you end up with this differential equation. Now, there are three important regions we have to worry about. There's the region when r is small, where v of r is definitely not 0. There's a region where r is very large, and in that domain, that's the region in which our solution is valid. In that domain, neither the potential nor the centrifugal term of this differential equation are significant. And then we get a simple second order equation with in u, but there is an intermediate region where v of r is 0, but the centrifugal term is not negligible,
And that's the region I want to talk about right now. That's the so-called intermediate region. In that region, we throw out the potential, but we keep around the centrifugal term. And it turns out solutions to this equation are the so-called spherical Bessel functions, the first and second kind, J sub L and N sub L. The first kind sort of behave like sine functions, and the second kind sort of behave like cosine functions, except that they're sine x divided by x and cosine x divided by x. Well, you know sine x divided by x, it's the so-called sinc function. I say it's not exactly that, but it sort of behaves like that. It has a finite value at the origin, but then it wiggles. But the cosine one, it blows up at the origin. And so, and also, I should point out that in the same way that e to the I kx is equal to cosine kx plus I times sine kx, we can make something that behaves like e to the I kr over r by taking a cosine plus I times a cosine plus I times a sine term, or a combination like that, to make what's called a Hankel function. This is a Hankel function of the first kind. It looks like e to the I kx over x. The Hankel function of the second kind looks like e to the minus I kx over x. Of course, our x is really r, and so the first kind looks like a wavelet leaving the target. The second kind looks like a wavelet coming into the target, and since we're doing scattering, we're really only interested in the outgoing guy, and so that's the first kind. That's the kind I have here, J sub L plus I times N sub L. That's going to be the outgoing form of the Hankel function. And so what I want to do is to rewrite the solution now in terms of functions that satisfy the Schrödinger wave equation in the intermediate region. It's a region where V of r is 0, but the centrifugal term is not 0. And as long as V of r is 0, the e to the I kz definitely works, and the Hankel function gives us an outgoing wave that also satisfies the Schrödinger wave equation. That's the idea. Now remember that the spherical harmonics are related to the Legendre polynomials, but since the incoming wave has no z component of angular momentum, and because the potential is spherically symmetric, that means it can't produce any torque. That means it can't change the angular momentum, which means that the outgoing wave can't have any z component of angular momentum either. And that means that the only spherical harmonics we have to worry about are the spherical harmonics that have m equal to 0. And those are the ones that are strictly proportional to the plain old Legendre polynomials, not the associated Legendre polynomials that have non-zero m. Only the zero m's, which are just the plain old Legendre polynomials, which simplifies our life a little bit. So I can rewrite the whole thing in terms of two pieces. The first piece is the incoming wave. The second piece is it's the outgoing wave, but it's written in terms of these, it's a decomposition of the outgoing wave into components of different angular momentum, is what it boils down to. The original form looks like this, and so if you think about it, you can rewrite this as, you can rewrite the scattering amplitude as a sum of pieces that have to do with the Legendre polynomials, and the Hankel functions take over the business of the r dependence, the e to the I kr over r. When kr is big, the Hankel function looks like an e to the I kr over kr. And so we can factor all that out and write the scattering amplitude as this sum of Legendre polynomials, 2l plus 1, and then these things called the a sub l's. Notice the a sub l's are just the expansion coefficients for this superposition, and they have a name. They're called the partial scattering amplitude, or partial wave amplitude. Now I want to talk a little bit about these Bessel functions. The Bessel functions, the spherical Bessel functions of the first kind look like this. Notice they're finite at the origin. Also notice that as z gets small, they go like z to the L. So z to the 0 is 1, and j0 is 1 at the origin. Z to the 1 is a linear function, and as you can see near the origin, j1 is a linear function. Z to the 2 is a quadratic, and if you look at the thing, you'll see that j2 appears to be approximately quadratic, and so on. So what that says is, if you need a function that's finite or not too small near the origin, then you have to have a fairly small L. As L gets bigger, the function gets suppressed near the origin. But what that means is that the incoming wave is made up only of j sub L's, and it's only going to interact strongly near the origin with its small L components, so that the large L components don't interact very much with the potential that's confined to the origin. That's an important idea. Also, the second kind of Bessel function, there's the expansion up there. Notice it only depends on the j sub L's. The n sub L's blow up at the origin, and they blow up pretty badly at the origin. And they blow up, the larger the L, the more they blow up. So they blow up faster if L is big. And that's going to have a consequence here in a minute when we get to plugging in the solution for the incoming plane wave in terms of its angular momentum components. So here, let's go back to the drawing board for a second. There's our current solution as we've written it. What I want to do is to replace the incoming wave with its angular momentum components. Now, the incoming wave is finite at the origin, therefore it has no n sub L parts. It has both incoming and outgoing waves, but it has no components proportional to n sub L, so it doesn't look like a pure incoming or pure outgoing wave. But the point is, if I put that back in, I can get a single expression that's entirely written in terms of angular momentum components. Let me show you a little demo here now, so you get a sense of how this decomposition into angular momentum components works. Okay, so here we have the Rayleigh expansion. This is a plane wave propagating to the right. I've turned on the time here so that you can see how the thing evolves in time, expressed in terms of well-defined angular momentum components, L equals 0, L equals 1, and so on. What I have showing here, using the cylinder representation from Project 8 of last semester, I just doctored up that program to visualize what this superposition looks like. And what I have right now is the sum. In principle, it should be L equals 0 to L equals infinity, but this one goes from L equals 0 to L equals 0, so it's only the L equals 0 term. But L equals 0 corresponds to J0. You may remember that that's the one that is big at the origin and then drops off gradually. And P0, but P0 is just a constant. It's a 0th order polynomial in cosine theta. Of course, 0th order polynomials are constant, so it doesn't depend on theta at all. And you can see that in the way the thing appears. But I want to imagine you're sitting at the origin. What would a plane wave look like as it went by? You just see a phasor going up and down with the frequency omega, and that's exactly what you see. So for someone who is precisely at the origin, they can't tell the difference between a plane wave coming by and this particular function. So that means that this does well if you're right on the origin. But if you go far from the origin, or any distance from the origin at all, basically, you can start to tell the difference between this and a real plane wave. So I'm going to bump up L max. Okay, well, let me make the window active here so it sees my key presses. I'll bump up L max and leave L min 0. This is the superposition of the L equals 0 and L equals 1. And I want you to notice that near the origin, this looks like a plane wave going by. But far from the origin, it clearly isn't. It doesn't look planar at all. But because the higher order components contribute mostly far from the origin, it only takes a few of the low order components to produce something that is plane wave-like near the origin. And that's important when looking at scattering, because in scattering the potential is only non-zero near the origin, and you only have to have a high fidelity reproduction of a plane wave in the places where the potential is non-zero. Okay, let's go ahead and let me bump up L min so you can see this is what the L equals 1 only term looks like. Notice it goes to 0 exactly at the origin. If we look at the L equals 2 term, it goes to 0 at the origin as well, but it's the zeroness of it extends farther out. Notice that also the theta variation, the number of nodes in the theta direction, is equal to the angular momentum value. So L equals 2, L equals 3, L equals 4, and so on. So, and also as I go up in L, if I look at higher and higher L components, notice that the degree to which they avoid the origin increases. This is because of the art of the, essentially the spherical Bessel function goes like r to the L, as we talked about before, and that becomes flatter and flatter as you go farther out. There's L equals 8. Okay, so L equals 8 only really affects the thing at the edges. Doesn't really do anything in the middle. Now let me bump L min down, and you can see what happens when I add all these components together. There's L equals 0 through L equals 8. And in this picture at least, that's very nearly a plane wave. You can see a little bit of wiggling just at the edges, but in the middle it looks very, very much like a plane wave. And that's the basic idea. Okay, now back to the plan. Notice that we have written the incoming wave as a superposition of angular momentum components with the spherical Bessel functions and the Legendre polynomials. If I plug that in and plug in the outgoing wave with the in terms of its angular momentum components, I can rewrite the whole thing as a sum of different angular momentum components. And then we see that that is the full solution to the Schrödinger equation in the intermediate region. Now the trick is to go back and then solve the Schrödinger equation in the internal domain of the potential and match up the solution in the intermediate domain to figure out what the A sub L's are. Okay, and I've actually worked it all out. There's an example in Griffiths that shows how he does this for a hard sphere case, and I went ahead and cooked that up, modifying the demo you just saw to show you what happens when you include the hard sphere scattering. Okay, so here we are looking at the plane wave again, but I've now doctored the program up one more time. Oh, this, by the way, is going from L equals 0 to L equals 13, but it's a plane wave. What I've done is to take Griffith's example on the hard sphere. So if you work through the example on the hard sphere, you'll notice that the trick is to calculate the partial scattering amplitude, the A sub L's, by demanding that the wave function go to 0 at the perimeter of the sphere. And if you do that, I can go ahead and show you what the result looks like. It basically modifies the plane wave, and you end up with a wave function that looks like this. But what I want to talk about is which partial waves are actually involved in this. If I dial down L max and we just look at the L equals 0 part, you can see that there's a huge change in L equals 0. I'll switch back and forth between the plane wave, that's the plane wave superposition, and there's with the hard sphere. So we've had to add in a bunch of N sub L. And remember that we only add in N sub L in conjunction with a little bit of J sub L to make an outgoing wave. But we had to add in some N sub L in order to cancel out the part of the plane wave that was non-zero at the surface of the sphere. But that shifts the phase of the whole wave function, and it obviously cuts a big hole in the middle of it. Okay? So there's a big effect in L equals 0. But let's look at L equal 1. So there's the L equal 1, there's the plane wave, there's the hard sphere. It's not nearly as dramatic a change. It just takes a little piece out of it, but it isn't dramatically changed. What about L equals 2? L equals 2, you know, you can see there's a change, but it's very minor. Okay, there's the hard sphere, there's the plane wave. Hard sphere, plane wave. What about L equals 3? L equals 3 is 0 near the origin. You can barely see any difference at all. You can just see a very tiny change. And with L equals 4, I don't detect any difference at all between hard sphere, plane wave, hard sphere, plane wave. So the L equals 4 part of the plane wave superposition doesn't interact with the hard sphere at all in this case, at least at this wavelength. And that means that that we can stop. We don't have to worry about any effects for any L greater than or equal to 4. So that takes our infinite series and reduces it to only 4 terms. L equals 0, 1, 2, and 3 are the only ones we could realistically have to worry about. So anyway, that's the way this thing works. We'll talk about this more in class, of course, but I think it's kind of fun to see how the pieces fit together a little bit more visually. Talk to you in class. Hey guys, welcome back. It's time for lesson 31. We're going to continue our investigation of scattering because we're moving our way toward nuclear reactions, and in order to understand those, we need to understand how we get data about nuclear phenomena, and mostly that data comes in the form of scattering experiments. Okay, so let's see what you remember from last time. You know that we were talking about incoming waves that we treated as plane waves, and then the outgoing waves were basically the consequence of scattering of the plane waves, and they went like e to the ikr over r with a theta dependence. But we broke the incoming wave down into angular momentum components, and thereby also broke the outgoing wave into angular momentum components, and we ended up with an expression for the scattering amplitude in terms of its angular momentum pieces, and it's basically a kind of a series expansion with the expansion coefficients called the partial wave amplitudes, or the A sub L's. Now these are complex numbers in general that tell how much you've got of each angular momentum component in the outgoing scattered part of the wave function. It turns out, because of the fact that in many contexts the potential is spherically symmetric, we know that the probability doesn't split from one angular momentum component to another. In other words, because the potential energy is spherically symmetric, it can't produce a torque. So we'll see how that goes in a minute. Right now I want to remind you of a few things. You guys remember, of course, the Euler relation between e to the ix and cosine and sine, e to the minus ix and cosine and sine. I want to point out that there's a very similar relationship between the spherical Bessel functions of the first and second kind, the j's and the n's, and the Hankel functions of the first and second kind, the h1 and h2 functions. They have a very similar relationship. You know that if you believe in the Euler relation, you can reverse it and write cosine as a superposition of e to the ix and e to the minus ix, and you can write sine similarly as a superposition of those two guys. Somewhat analogously, you can write the Bessel function of the first kind, the j, as a superposition of the first and second type of Hankel function, and also the n's you can write as a superposition of Hankel functions. And so I just want you to kind of, when you're looking at these crazy looking expressions and so on and trying to figure out what it all means, you might bear in mind this sort of relationship to something more familiar, and that might help you to understand kind of what's going on. Okay, so back to the monstrosity. Here we have the full solution of the Schrödinger equation expressed in terms of these Hankel functions. Then the Hankel functions of the first kind in the asymptotic limit turn out to look like e to the ikr over r. So if we're trying to think of the wave function as a superposition of an incoming plane wave and an outgoing scattered wave, it helps to remember that the Hankel function looks like the outgoing scattered wave. But you know that
the amplitude, the partial wave amplitude, fits in the same place as the Hankel function. So it's the part of the expression there on the right that has the Hankel function with it. And as I was saying, if the potential is spherically symmetric, then it turns out you can't move probability from one component to another component. The probability has to be the same. What that means is really all that can happen is a change of phase. So how do we see that? So we can write the incoming plane wave as a superposition of Bessel functions, and remember that the Bessel function is a superposition of the two Hankel functions. So if you put that in and look at what the Hankel functions look like, asymptotically at large values of r, the Hankel function looks like an incoming wave and an outgoing wave. The incoming wave is the e to the minus ikr, and the outgoing wave is e to the plus ikr. And what happens as a result of the scattering is, because we can't shift probability from one angular momentum component to another, it means the only thing that you can do that doesn't change the probability is to change the phase. So if you flip that around and you add a phase shift, that has to be the net effect of the scattering. So notice the incoming wave doesn't change, but the outgoing wave gets a additional phase. That's kind of the idea. And it gets a 2 delta because it gets a delta on the way in and a delta on the way out, basically. So it traverses the potential twice, and so we give it effectively a 2 delta. So the idea is we're going to attack the finite square well with this mathematics, this terrible mathematics, and I just want to remind you about the finite square well. First of all, the radial function is r times the wave function. If you make that substitution into the Schrödinger equation, and you look at the L equals 0 term, only consider L equals 0, then the Schrödinger wave equation reduces to what looks like a simple one-dimensional problem, with the minor caveat that because of the definition of U has to go to 0 at the origin. So a finite spherical square well basically looks like a square well that has an infinite potential at the origin and a finite potential everywhere else. And because it's square, it means we're going to have a minus V naught inside the well and 0 outside the well for a potential. And so you know this differential equation pretty well by now, so you know that in order to satisfy the boundary condition at the origin, the inside wave function has to go like sine, and the outside wave function has no such boundary condition, so it's free to be a little bit of cosine and a little bit of sine. But the wave number inside and outside are different. The wave number inside corresponds to an additional kinetic energy of V naught, and outside it's just the free energy, the kinetic energy, h bar, whatever, h bar squared k squared over 2m. So what does this look like? The point is, inside the well, the kinetic energy is a little higher, which means the wavelength's a little shorter. So when you go to match up the amplitude and the slope of the wave function at the boundary, what you find is that the wave function outside looks like it's just a sine plus a cosine, but it's been shifted in phase relative to what it would have been had the potential not been there. If the potential hadn't been there, then the wave function would have to go to 0 at the origin with a fixed wavelength all the way, the same wavelength all the way to the origin. But because of the potential barrier, or the potential well, rather, the wavelength got a little shorter inside the well, and so the phase of the wave function shifted. So we call that phase shift delta, and in space, of course, it's delta divided by k. That's the difference in position, where the wave function would have gone to 0, and where it does actually go to 0. And I want to show you a couple demos about how to think about this. So let's break for a demo. Okay, so this is a square well. This is the wave function that you see here. The blue line is the actual wave function inside and outside the well. The green dots are what the wave function would be if it weren't for the well being there, and it will illustrate the phase shift. So the idea is right now the well is got 0
potential, but if I turn on the well a little bit, you can see that what happens is the wavelength inside the well gets less, and we get this phase shift. So notice this is considered a positive phase shift, okay, because the thing is attractive and it's advancing the phase. The phase here is more than it would be if the well weren't there. The phase would be less at a given r than it is with the well there. And notice that let's see, if the phase shift gets to be big enough, as the well gets deeper, the phase shift just continues to get larger, greater and greater phase shift, till we get to something like that. Okay, and it would just keep going. So one thing I want to point out is that the phase shift is a monotonically increasing function of the well depth for an attractive well. As the well gets deeper, you get greater and greater amounts of phase shift for a given wave function. And this is, of course, this is all L equals 0. Notice we got L equals 0 here, and that's why we're getting away with sines and cosines. If we want to go to L equals 1 or L equals 2, then these have to change, and they're going to be something like, Bessel functions times r or some crazy thing. But it's easy to see what's going on in the L equals 0 case. As the well gets deeper, you get a greater and greater phase shift. Okay, this is the same idea. The difference is now the energy of the wave function outside the well, the energy of the particle outside the well, is very low. So you'll notice that the curvature of the wave function is very tiny. If anything, it looks like a straight line practically. So this is the low energy version of the same thing. And in the low energy case, because this is basically a straight line, the distance here is called the distance from the origin to the point where the wave function would cross the axis, or at least it asymptotically appears. The asymptote appears to cross the axis here. This is called the scattering length. And it turns out the scattering length is related to the cross-section, which, how's the short story go? If we have this is a positive scattering length, and that's a negative scattering length. But in the positive scattering length case, you can see the scattering length is the radius of a hard sphere potential, an infinite potential that would give the same cross-section. In other words, if instead of having a soft potential here with a finite well depth, if I had an infinite barrier right here at the scattering length, then the wave function would go to 0 there, and it would appear to be just like a hard sphere of radius equal to the scattering length, the distance between the origin and the place where this wave function crosses. So you can see the scattering length is related to the effective cross-section of the potential for low energy incoming particles. So that's what the scattering length is about. And we're going to find out that when we talk about the deuteron, we'll find out that the scattering length is a very useful idea for estimating the cross-section of the deuteron, for example, of neutrons scattering off of protons. Okay, so here's the thing. If I increase the well depth, this thing goes through various changes. And notice the scattering length changes a lot depending on exactly how deep the well is. So as a function of well depth, the scattering length varies a lot. We're going to find out. In fact, the cross-section, the total cross-section, turns out to be 4 pi times the scattering length squared. If you remember from Griffiths, the total cross-section of a hard sphere at low energy turned out to be nothing other than 4 pi times the radius of the hard sphere squared. The scattering length plays the same role as the radius of that hard sphere, and so the hard sphere model is actually useful. It tells us the low energy cross-section of basically any potential, because any potential is going to have a scattering length at low energies, because when you get outside the potential, the wave function's a straight line, and you can identify a distance that's the scattering length. So that's the way that works. Next, when you guys are in class today, I'm just going to let you have a peek at the board work. What I want you to do is to basically use this solution inside and outside the well
notice that you can rewrite the solution outside the well as a phase-shifted sine function, and you can see that the phase angle is related to the sine and cosine coefficients from the original expression. So if you can figure out what B and C are, or you can figure out their ratio, then you can work out the phase shift. So what I'm going to give you some real numbers and see if we can't work out the phase shift for low energy neutrons colliding with protons using a spherical square well model potential. And so we'll do that in class. But let's work backwards now. Let's relate that to the scattering amplitude. Obviously, somehow this must relate back to the scattering amplitude, since that's what you can physically measure. And so I want to remind you about the scattering amplitude and how it looks, and the wave function and how it looks. What I'd like to do is just focus on L equals 0 for the moment. It turns out, for neutrons on protons, a lot of the interesting data that you can actually interpret is for low energy, less than 10 MeV, say, and in that domain, only L equals 0 is really important. So let's go ahead and just look at what happens, and also it's simpler. And L equals 0, the U function just turns out to be the sine, and that's just e to the plus ikr plus e to the minus ikr. It's equal parts of incoming and outgoing spherical wave fronts. But if you turn on the potential, then this gets shifted to an e to the ikr plus 2 delta. But I want to monkey with that a little bit. Let's look at that expression. That's the full wave function, but I can add and subtract e to the ikr to the numerator, and then notice that if I rearrange things, I've got a sine of kr, and then I can factor out the e to the ikr from the other part, and I end up with this e to the ikr, and then I have an e to the I 2 delta minus 1 over 2I, but I can factor an e to the I delta out of that, and notice I've got a sine of delta times e to the I delta times e to the ikr. Well, e to the ikr was the original outgoing wavefront. E to the I delta times sine delta, that's starting to look like my scattering amplitude. And if you go back and look at the original expression for scattering amplitude, you'll see that what it actually turns out to be, the partial amplitude, is e to the I delta sine delta over k. And now I've only worked it out for L equals 0. It turns out, shockingly, that you get the same exact result for all values of L, although if you're interested, you can pursue that. There's places on the internet that show how that works, but it's basically the same manipulation I just did, except using the generic Bessel functions instead of the sine and cosine. But anyway, that's the answer. So it turns out that these partial scattering amplitudes are really due to a simple single number, a real number, the phase shift. And the phase shift is useful in situations where probability is being conserved. It's just getting shifted. The amplitude of the wave function is just shifting in phase. And if I put that back into the expression I had for the scattering amplitude, you can see how to, once you know the phase shifts, you can calculate the scattering amplitude. And if you integrate over all angles, you can even calculate the total scattering cross-section. If you let's go ahead and work this out. I went ahead and worked it out for the square well for a couple of different potentials. Here's for one potential that's fairly weak. In this case, it turns out you can see the strongest cross-section is L equals 0. But if you go up, now that's k in the denominator, and you know energy goes like k squared. So if you square this, the functions that start at 0 are going to flatten out a little bit, but you can see that the dominant term is the L equals 0 term. If I bump up the size of the potential a little bit and graph that as a function of k, an interesting thing happens. You notice that the L equals 0 phase shift
starts out, instead of at 0, it starts out at pi. And that turns out to be significant. We're going to see in a little bit that, and in fact you may have noticed from the earlier demo, that when the phase shift starts out at pi, even though the energy is going to 0, it means that you already had a bound state. In other words, there's enough, the potential well is deep enough and wide enough to have at least one bound state for L equals 0. In fact, it has exactly one bound state. If I make the potential even deeper, here's 12.1 potential, you'll notice that the L equals 0 phase starts at 2 pi now. L equals 1 and L equal 2 start at pi, and all the higher ones start at 0. So the interpretation there is that even if you go down to 0 energy, you get a phase shift. That means that you have 2 bound states in the L equals 0 case, and 1 bound state in the L equal 1 and L equal 2 state. So I guess the important insight to get from this is that you can discover things about the ability of the potential to hold particles in bound states based on the phase shift that you see from a scattering experiment. Notice no binding has actually occurred here. This is scattering we're looking at, but it's scattering that shows us something about the internal structure capabilities, I guess, of the well. So let's go ahead and look at some more demos and discuss the low energy phase shifts and this idea of the scattering length. Okay, so here's a similar setup. I have the wave function up here. I'm going to vary the well depth, but I'm graphing here the phase shift and the cross section at the same time as a function of the well depth. Basically, this is a scaled version of well depth here. It's the square root of the well depth times the size of the well. This actually works out to be the phase of the wave function inside the well as it meets the boundary. So let's see what happens. If I start increasing the well depth, notice I start to get a scattering length, and the phase difference starts out pretty much 0. So I'm going to go ahead and crank up the well depth here, but notice that the scattering length goes through a maximum right about there. In fact, it goes to infinity very briefly. At the same time, the phase shifts by pi. The phase goes from 0 to pi very quickly, and if you remember, basically the scattering length goes like the tangent of the phase difference, and so the phase difference in going from 0 to pi, it very quickly passes through pi over 2, which is a singularity in the scattering length, which puts a singularity in the cross section. So the cross section goes through a maximum, and it happens again when the scattering length goes through a maximum here, when the phase goes through another half integer multiple of pi over 2, and the cross section again blows up. So you'll see that you get a series of regions where the phase difference jumps from an integer multiple of pi to the next integer multiple of pi, and in passing through the odd integer multiple of pi over 2, the scattering cross section blows up. These things are called resonances. Okay, they're called resonances, and they're very important, but that's how they come about. And here's a similar situation, but this time, instead of varying the well depth, we're going to vary the energy of the particle coming in, and you can see that that changes the phase shift, and changing the phase shift changes the cross section. So again, the main point is that if you can theoretically predict the phase shift by matching boundary conditions at the well, for example, if you want to model it as a finite square well, then you can compute the cross section and you can compare with the experimental results. And here's one last thing. Here is the phase shift as a function of k, which is like energy. It's the square root of energy for a moderate depth well, where you've got one bound state at low energy, but notice that as you increase the energy, the scattering cross-section varies, and almost all the cross-section here is in the L equals 0. So there's basically no cross-section for L equals 1, L equals 2, L equals 3. So this would be S-wave scattering only. But if you bump up the well depth a little bit, you get a more interesting situation. Here we have a well depth of 32.4 on this scale, and notice that here we have 1 pi, 2 pi, 3 pi. So there's 3 bound states for the S wave, 2 bound states for L equals 1 and L equals 2, and 1 bound state for these guys. It looks like we have here L equals 5, L equals 4, and L equals 3, each of which has 1 bound state. So it's a much richer situation when the well is a lot deeper. But the other thing I want to point out is here's an example of a resonance. Here is the L equals 6 state is going from 0 phase difference, and very quickly it jumps up to pi, or pretty nearly pi. And when it jumps up, there's a big spike in the cross-section for that partial wave. And you can see the total cross-section is the sum of all these cross-sections. It also gets a bump. And that bump is due to the L equals 6 partial wave cross-section at that particular energy. So that's another way to look at a resonance, and we're going to see some more of that in the near future. Okay, and real quick, I just wanted to point out that we can use this math, all this crazy math, to actually build pictures of what the scattering process looks like. This is sort of similar to the things I did in VPython in 3 dimensions, but it turned out you can get a little more detail if you just do it in 2 dimensions with contour plots. So that's what I've got here. And also I've calculated, if you remember at the beginning of Griffiths, there was an expression for the probability current, which is, it's something like psi star grad psi minus psi grad psi star, something like that. Anyway, if you calculate that thing, you can actually make pretty pictures which show the probability current vectors so this is a plane wave. So and this is I'm actually graphing the real part here, just so you can see the wave structure, and it looks like you'd expect all the probabilities going to the right. But if I hang on a second, if I switch this to soft sphere and run it, you should see here, okay, now we're in a soft sphere situation, and we got probability going to the right. But what's fun is you can see that in the soft sphere case, the shift in the wavelength, it gets shorter wavelength inside in the well, and that produces an increase in current flow. Probability current gets transferred from this region out here into the center, and it looks almost like optics. This looks like a lens of some kind, and we've got waves coming in and being focused. So this is sort of like probability focusing. And you can also do the hard sphere. Let me go ahead and switch this. You can see what the hard sphere looks like. It looks quite different. You got a big shadow region here, and the probability is getting shifted to the outside. So it's kind of fun what you can do with math, and you can see the probability currents getting pushed around like that. Pretty cool. Anyway, the other thing you can do, of course, is make movies. So I went ahead and made some movies. This turned out to be quite easy because all you have to do is turn on the e to the minus I omega t. All the wave functions have the same energy. They have the same omega. They all happen in phase. But I think it turned out quite nice. That you can see the probability piling up in the middle there. Let's go ahead and look at the hard sphere case. There's the hard sphere. You'll notice a lot more reflection interfering with the incoming wave in the hard sphere case, but and then there's that shadow. But I thought you might find that entertaining. I know I did, and we'll be looking at this some more when we talk about neutron, proton, nuclear reactions. We basically have already done the scattering part. We've done the math, but we haven't actually compared it to experiment to see what it all means. We'll be doing that next time. I'll talk to you soon. Hey guys, welcome back. It's lesson 32. We're going to
continue our discussion of scattering with the Born approximation, and we're going to get into some nuclear physics today with the empirical mass formula. So let's begin with the Born approximation. The idea is it's a different way to attack the scattering problem from the partial wave analysis we've been doing. It doesn't in any way rely on the spherical symmetry of the potential, so you can easily, or more straightforwardly, I guess, handle non-symmetric potentials. And the other thing is it works best if the potential is weak. So compared to, say, the kinetic energy of the scattering particles. And I'll just go ahead and put the answer down there. This is what the answer turns out to be. And we'll spend a handful of slides trying to show where that answer comes from, what the basic idea is. So let's get started. First of all, I want to introduce the concept of a Green's function, and I want to give you the mathematician's definition for a Hermitian linear differential operator L with the boundary conditions on L2. Basically, it's a vector space of functions that are square integrable. Okay. If lambda is a real constant that is not in the spectrum of eigenvalues of L in the inhomogeneous equation, and the inhomogeneous equation is L minus lambda times the solution is equal to some source term f of x, then the solution is given by the integral of the Green's function. And I want you to look at the Green's function. It's an integral over y. But the Green's function is a function of two variables, x and y. And the way you think about it, it's that the Green's function is a solution to the problem of a delta source. So the idea is if you have a delta source at y, what's the response of what will be the solution at x for a delta source located at y? That's kind of how you think of it. So that if you want to ask what happens if I have a distributed source, you could basically think of it as a superposition of delta sources. Now, we already do this. You guys are familiar with this in the context of electrostatic fields and the resulting potential from point charges. So a point charge is basically a delta source of charge, and once you know the solution to a point charge, you can calculate the potential to any distribution of charges by adding them up. That's basically what this is saying, except that the solution for a point charge, the static field of a point charge, is different than the solution of the Schrödinger equation for a point wave source, but it's the same idea. So first of all, let's figure out what the solution to a delta source is. Well, let's say we could get the solution to a delta source, then we can get the solution for any source by adding up the solutions of a bunch of delta sources. So the idea is if we have some distributed source f of x, we could think of it as f evaluated at x1 times the delta function at x1 plus f evaluated at x2 times the delta function at x2, something like that. So you could think of the source as sort of an integral over point sources. And then if you want to know the solution, you simply find the solution to a point source. That would be the Green's function, is the solution to the point source. And then to get the overall solution, you simply superpose all those point sources and add them up to get the solution for the distributed source. That's the idea. Okay, so we could write out the solution as the Green's function for the point source at x1 times the Green's function for the point plus the Green's function for the point source at x2 times the size of the point source at x2, and so on, and then add all those guys up to get the total solution. Okay, so how do we apply this to the scattering problem? Well, we need to find a way to think about the scattering problem as a bunch of point sources whose solutions we can add up. So the idea is the operator L is going to become del squared. That's the kinetic energy operator from the Schrödinger equation. And then the idea, this is in the part of space where the Schrödinger equation is del squared. Then the eigenvalue, or the lambda, the thing that plays the role of lambda, is going to be the essentially k squared, the wave number squared. And
And the source term is going to be the potential times the wave function. So we sort of flip the Schrodinger equation around, move the potential energy to the right-hand side, and the kinetic energy and the total energy, k squared is basically going to be the total energy, over to the left-hand side, and then it looks like this. So this is the way the thing turns out. And notice that you can identify f as the right-hand side. It's the source term, and so you can simply write down the answer once you know the Green's function. There are a couple of things I want to add to that. You can add a solution to the homogeneous equation, and it doesn't affect the solution, but it does change things at the boundary, so you have to be careful with the boundary conditions. And in the scattering problem, the incoming wave is a solution to the homogeneous equation, so you can add it outside the Green's function integral, and it doesn't have any effect on the correctness of the answer. Remember that you can always add a homogeneous solution, and it doesn't, because the operator acting on that is 0, it doesn't affect the right-hand side. Okay, so we can just write down the answer. What I want to point out is that it is the answer, but we have a trouble, and that is that the same solution shows up inside the integral and outside the integral. So unlike the case of the point charges in the electrostatic field, we can't simply integrate this because the thing we're after is inside the integral. So we have to come up with some kind of a strategy to deal with that. But first, we've got to figure out what g is. So let's find out what g is. It's a solution to this equation. It's a solution to the equation del squared plus k squared on the Green's function is equal to a delta function source. So how do we solve an equation like that? The easiest way is to take the Fourier transform. So we Fourier transform both sides. In the Fourier transform, basically you're converting from a sort of real space to sort of a momentum space, and we'll let the momentum be s. And then del squared on e to the I s dot r is just minus s squared, right? And so this formula, and the right-hand side, we just have a delta function. We take the Fourier transform of that, and we just get e to the ISR. And you can see, looking at that thing, that you can write down the Fourier transform of the Green's function right away. It's quite straightforward. Now the question is, what's the Green's function? We're going to have to take the inverse Fourier transform of the Fourier transform of the Green's function, and that's a little more challenging. It's a three-dimensional integral, so first we'll break it up into s, theta, and phi. The phi is easy. There's no phi dependence anywhere, so you just multiply by 2 pi. That gives you the phi part. Then the theta integral isn't too bad. You can use a u substitution there, and you end up with the result that looks like this: s times the sine of sr over k squared minus s squared. Now you'll notice k squared minus s squared is a difference of squares, so I can break it into k plus s times k minus s. And also notice that because s is odd and sine is odd, that the product of the numerator, that numerator is even, so I could actually change the integral to an integral over all s from minus infinity to plus infinity and divide by 2, which is what I did. And I want you to notice that that integral has problems. First of all, it blows up at k equals plus s and k equals minus s. So there are 2 poles on the real axis. It turns out the easiest way to do this is through a technique called complex contour integration. Now, this is, if some of you guys have had some complex analysis, you're probably already familiar with this. But the idea is there's a thing called Cauchy's theorem, which says that if you integrate around a closed loop in the complex plane, that you can deform the integral any way you like, and the result is the sum of the residues, the so-called residues, which are due to the poles that are inside the curve on the complex plane. So basically the way we handle this is to carefully wrap the integral around to make it a loop. But we wrap it around at r equals infinity, and there, the infinity part doesn't contribute because we've got a 1 over r, notice, in the thing. Let's see, am I saying that right? Actually, it's s that we're going to let go to infinity, but we're going to break it into the two terms, the e to the plus ISR and e to the minus ISR. The idea is we break this thing up into, break the sign into the e to the plus ISR and e to the minus ISR. And for the part of the integral where we wrap the thing around the positive imaginary infinity, then the first term goes to 0 because of the e to the plus ISR, and the second term will wrap the curve around the minus infinity part, and that will let that term go to 0. Anyway, I don't really want to too much get into the details of that. The most important part is the answer. The answer turns out to be easy. It looks like the scattered wave from our scattering wave function. Basically, if I have a delta source, I get a response that looks like a scattered wave, e to the ikr over r, and I can simply put that in, and you can see that the answer turns out to look like this. Now we're going to make some approximations here. Notice we still have the unknown wave function inside the integral and in the answer on the left, and we need to figure out how to handle that. And the easiest way to handle it is to make what's known as the firstborn approximation, which is one, we say, look, we're interested in r much greater than the area where the potential is non-zero, so we'll let r become much greater than r0. And the second is, to the first approximation, scattering doesn't change much. So inside the integral, let's just put in the incoming wave and see what happens. It works pretty well as long as v is fairly weak. So we'll go ahead and do that. Making r much greater than r0 means we can bring the 1 over r outside the integral, and then we're left with this monstrosity. But if you actually evaluate what psi 0 is, it's e to the ikz. You can put that in, and you get the following result. Notice I've got the incoming wave, e to the ikz. I've got my e to the ikr over r. And then on the inside, what have I got? This must be nothing other than the scattering amplitude. So we identify all the rest of the junk there with the scattering amplitude. And that is just an integral that we can do. I mean, it's not a terribly easy one, but it's something you can do. And how do we get better answers if we don't like the firstborn approximation? Well, we can take the answer for the firstborn approximation and stick it back into the integral again, and that'll give us the secondborn approximation, right? And then we can take that result and stick it back in the integral again and get the next one, and so on. So you can actually you can build up a series of approximations that involves doing the integral multiple times using the incoming wave as the starting point. And that becomes the so-called Born series. What is it? It's a series of complicated high-dimensional integrals. How do we do those complicated high-dimensional integrals? Well, one approach that we've already talked about is the Monte Carlo strategy. And just to illustrate that people actually do this, I tracked down a paper on using the Monte Carlo method without using partial wave decomposition to get the nth Born series. And so that's exactly what we're talking about. So anyway, moving right ahead, that's the Born approximation. Basically, it's a nasty integral that you can do to calculate the scattering amplitude, and probably it won't make a lot of sense to you until we actually sit down and try and do it. So we'll try and do a couple of those before we're finished. In the meantime, let's get into some nuclear physics. I want to talk about something called the semi-empirical mass formula. It's not in your book, but I'll put some papers on the shared drive so you guys can see how it kind of works, but I want to give you a feel for it. Basically, it's a formula that you can use to estimate the energy, the binding energy of any nucleus, given its number of protons and number of neutrons. And it's not exact. It's that's why, and it's semi-empirical, but it has some theoretical inputs, and it gets you in the ballpark. It gives you a sense of whether something's going to be stable or not, and if it's not, why isn't it? And that's a useful insight to have. So let's talk about it. The first effect I want to discuss is the pairing effect, and it has to do with the fact that any given nucleus has so many protons and so many neutrons, and they tend to like to pair up, spin up to spin down. And we've already seen that. You guys remember when we did atomic physics and we talked about electrons and how they fill the orbital shells of an atom. It's a similar idea here, except instead of electrons filling electronic energy states, these are nucleons filling nuclear energy states. But it's energetically favorable for them to be paired up, spin up and spin down. You could have two different isotopes, or two different nucleons with the same number of nucleons, two different nuclei with the same number of nucleons, but you see one of them here has 8 protons and one has 7 protons. The fact that it has 8 protons makes it oxygen, and the fact that the other one has 7 makes it nitrogen. But notice that even though they have the same number of nucleons, because of the fact that the nitrogen is odd, it means that one of the nucleons is up at a little bit higher energy. So these guys like to pair up, and you can also see that there's an advantage to having an equal number of neutrons and protons, because that keeps the energy levels about the same. If the number of neutrons and protons were very different, you could lower the energy by converting some neutrons to protons, and that's essentially what happens. So there's also the Pauli exclusion principle, which brings in some other ideas. Remember that exchange forces are attractive for symmetric and repulsive for antisymmetric wave functions. So you remember that from when we discussed the Pauli exclusion principle with electrons and atoms, but it's still true today, still true with nucleons and nuclei. And also remember that the kinetic energy of a wave function is lower for a symmetric and higher for antisymmetric wave functions. And finally, particles in symmetric wave functions can get close together. Particles in antisymmetric wave functions are forced to remain far apart because there's a node in the middle. And when we're talking about nuclear force, close together means lower energy, far apart means higher energy. So there are multiple reasons here why identical nucleons like to be in symmetric states. And of course, to be in a symmetric wave function, spatial symmetric wave function, you've got to be an antisymmetric spin wave function. So that's another reason why they like to be paired up, spin up and spin down. Now, there's also the charge effect. So we know that protons have charge, neutrons don't. So, and because they all have positive charge, it means they repel each other. So that means that as the nucleus gets larger and larger, protons, there get to be more and more protons, and that the fact that they repel one another starts to have an impact on the energy of the nucleus, the overall energy of the nucleus. And so you don't see that the number of neutrons and protons stays equal as the size of the nucleus increases, and that has to do with the charge effect, the fact that the protons repel one another. So let's actually look at the darn formula. It's the semi-empirical mass formula. First of all, a dominant effect is that the more nucleons you have, the lower the energy, and that's the so-called volume term. It just means that as you increase the number of nucleons, there are more of them, and each nucleon in the nucleus has a bunch of folks around it, and that adds to the energy. And so there's a first term that's just proportional to the number of nucleons. Then there's this pairing term, the T sub c, and it's proportional to the difference between the number of neutrons and the number of protons. And we've already talked about that. That's due to the fact that they like to come in pairs. Then there's the electrostatic repulsion term, and this is simply the electrostatic energy of the protons. So notice it only has protons in it. Z is the number of protons. And finally, there is the surface term, which means that if there are nucleons at the surface, unlike the ones that are deep in the volume of the nucleus, they don't have neighboring nuclei on every side, and so there tends to be an increase in energy. Notice it's a positive term. There's an increase in energy associated with the surface area of the nucleus. And since A goes like the volume, it goes like r cubed, then this term goes like r squared. Notice it's the cube root of A, which is proportional to r squared, which is going to give you an r squared term. So this is proportional to the surface area of the nucleus. So what are the terms? The volume term, the pairing term, the charge term, and the surface term. And we define T sub c to be half of the difference between the number of neutrons and the number of protons. So basically it's 0 if there are equal number of protons and neutrons, and it gets bigger as there is a difference between number of neutrons and number of protons. So that's the so-called pairing term. There's one other symmetry term I want to discuss. Oh, and in at least different people have used this formula to fit measured binding energies, and they've discovered that the coefficients that give the best fit over the largest range are these ones. Of course, there are competing fits that different people use for different reasons, but this is one popular set of fits, or set of coefficients. And I cooked up a little spreadsheet that I'm going to show you now that allows you to see what the consequences of this formula are, and we'll take a little break here to just peek at that. Hi guys, so let's see, here we are. Here's a little spreadsheet I cooked up that uses the Weizsäcker empirical mass formula. You can see it's a hideous expression in Excel, but basically what we've got here is A going down the left side and Z going across the top. Here are the expansion coefficients in basically an MEV, more or less. And first thing I want you to notice is even with the numbers here, I can see that there's a region of negative energy, and then it goes out to a region of positive energy. And so it follows along a line of Z equals N, where for low values of Z, and as Z gets larger, of course, it tends to favor neutrons as opposed to protons because of the charge effect, so it'll kind of shift. But the point is that the formula gives you qualitatively correct behavior and quantitatively reasonable but not exact. And the example that I showed earlier, or what we're going to talk about here in a minute, I guess, is A equals 46. Z is going to go in the 20s, kind of. That's the sort of calcium, scandium, titanium in that region. And I went ahead and selected a few energies here just to show you how that works. So I can make a little scatter plot. And you'll notice that there is some bumpiness here, and that has to do with the symmetry effect. This is the odd, or these guys are even, and these guys are odd, and so you get a bump in energy. But what that means is this guy's not stable, and I'll talk some more about that in a minute. But anyway, that's the idea. The point is you can make a little spreadsheet to look at this formula and see how it works, and get an idea of what's going on. And moving ahead, there is one other symmetry effect I want to mention, and that has to do with the evenness and oddness. Obviously, the lowest energy is if both the number of neutrons and the number of protons can be even. Independent of whether the number of protons and number of neutrons are equal, there's also a benefit to having them be even. That means they're all paired up and everybody's happy. If there are even number of protons and an odd number of neutrons, or an even number of neutrons and an odd number of protons, that's an even-odd situation. That has a little bit higher energy, and the worst case is if they're both odd. If they're both odd, then nobody's paired up and nobody's happy. And so you can add a term to the semi-empirical mass formula that takes that into account, where the even-even case you take off a little bit, the even-odd case you leave it the same, and the odd-odd case you add a little bit. And based on one popular strategy for fitting, the value of delta here works out to be 270 MeV. So if you put that in, you can explain a kind of beta instability that happens. Here's an example, and I just used the mass formula to calculate these numbers, so they're not really exact. They're in the ballpark. But there's one case where if you let the A be 46, we have potassium, calcium, scandium, titanium, and vanadium. Okay, and now some of these are not found in nature because they're so unstable. But for example, if you look at scandium or whatever, it's A equals 46, Z equals 21. Notice that if Z is odd and A is even, it means N must also be odd. So potassium, scandium, and vanadium, they're all odd-odd. But calcium and titanium are both even-even. So even-even is more stable than odd-odd. And if you look at an even A, every other nuclide, I guess, on the list is going to be odd-odd, even-even, odd-odd, even-even, because the only way to get an even A is either for both Z and N to be odd or both Z and N to be even. And so that gives you a big energy difference. And notice that by emitting a beta minus, one of the neutrons in scandium can change to a proton. And that will bump up its Z by 1. And so scandium is unstable to beta decay to titanium. It's also unstable by electron capture to calcium. So there's two ways to go down in Z. You can either emit a beta plus, or you can capture an electron from the atoms that are orbiting one of the s electrons in the atomic electronic structure, and convert a basically you're going to convert a proton to a neutron. And so you're going to go up in N and down in Z. And also potassium and vanadium are also unstable. It turns out a lot of the times only one of electron capture or beta plus emission occur because one is much more likely than the other. And so it isn't that the other is impossible, but it's just not measurably significant. So anyway, that's the idea. The point is, using the empirical mass formula, you get a good idea. These numbers, by the way, were calculated from the empirical mass formula, so they're ballpark, but not exact. The point is that you can get a sense of what's going on in terms of stability using that formula. And that's it for today. Hey guys, welcome back. Time for lesson 34. It's time for inelastic scattering of neutrons on protons. In other words, this is how you make deuterons. So let's talk about what neutron capture means. It means I have an incoming neutron and an incoming proton. This is in the center of mass frame of reference. And these guys scatter, but in particular, sometimes they scatter in such a way that they form a deuteron after the emission of a gamma ray. Now remember, the deuteron has only a triplet bound state, and for that reason we're going to discover that the incoming state of the neutron and the proton, in order to do this, has to be a singlet configuration. We'll get around to talking about why that is, but it turns out to be true. The energy of the gamma is about 2 MeV. I should say the energy of the system after the capture is about 2 MeV. That's the binding energy of the deuteron. But we're going to assume that the incoming energy of the neutron and the proton is much less than that. We're particularly interested in thermal energy, so we're talking about something like a 40th of an electron volt at room temperature. And so we're well within the range of L equals 0 consideration. So we don't have to worry about p states. And that also is important in order to make this thing tractable.
I want to point out that the magnetic moments of the neutron and the proton are well known and measured. The proton has a positive magnetic moment, which means that its magnetic moment points in the same direction as its spin. The neutron, on the other hand, has a negative magnetic moment, which means when the neutron is spin up, the magnetic moment is pointing down. And that has consequences that we'll see here in a minute. The deuteron, on the other hand, has a magnetic moment that's roughly the sum of those two, which sort of is consistent with the fact that we know that it's in a triplet state where the spins are aligned. And so we'll talk some more about that. But I want to first show you a little demo which describes the nature of the capture process. It turns out the fact that the magnetic moments have opposite sign is significant in the physics of how this capture process happens. All right, so what I have here is a model of a proton. The spin of the proton is up, and it's participating in this case, I'm imagining these guys are part of a triplet state so that their spins add. The total spin I can show here is a constant of the motion. It's a good quantum number, but the individual spins are superposing to create that triplet, and in this case this is both spins are up. So this is the triplet with both spins up situation. But notice that because the magnetic moment of the proton points along the spin direction, but the magnetic moment of the neutron points in the opposite direction, when you add their magnetic moments together, you get something that's not a constant of the motion, but rather it revolves, I guess, about the constant angular momentum. So if you think about that for a little bit, you'll see that there's a chance that this thing could radiate. So that's kind of the idea. And this, you could do a similar picture for the jackknife configuration. The total spin is 0, or the z component is 0, and so on and so forth. But I just wanted to give you a visual picture of the fact that the magnetic moment and the spin don't line up. And that's why it turns out the magnetic interaction is important in this capture process. The other thing is, of course, in order to do an electric dipole transition, you need to change angular momentum L, and that means it involves a p state. But at this very low energy, the probability of a p state interacting is very tiny because the amplitude is so small in the domain where the nuclear forces are significant. So that's the way that one works. Okay, so now we have a rough idea of what's going on. Let's talk about the initial and final states of the system. The final state is obviously the ground state of the deuteron. So it's going to be a triplet, either both spins up, both spins down, or the z component of spin equals 0 version of the triplet. And the initial state, I've claimed, is going to be the singlet. And the singlet, there's only one of those guys. That's the difference between neutron up, proton down, and neutron down, proton up. We're familiar with that singlet idea from last semester. But one thing that's not included is the initial triplet configuration. That one turns out to be no good for reasons that we'll get to. But that's the situation. We have an initial singlet, a final triplet. And let's talk about how to calculate the details of this capture process. We're going to need to extend the perturbation theory from Chapter 9 just a little bit. We wound up with a perturbation formula from Chapter 9 that looks something like this. And the point was that this was the probability per unit, or the probability at a given time of having of finding an amplitude in the B state, the state that started out with no amplitude. This is basically the probability of measuring the energy EB at a later time. I can say it that way. But this was under the influence of a monochromatic exact frequency perturbation. But the point is the gammas that can be emitted in this process, there's a range of very tiny but finite range of gammas, and we need to add up the probabilities of having any of those energies, and not only energies, but that's also the business of which way the gamma goes. It can go in any direction in space. And so there's this whole business of the density of states we have to take into account. So what we have to do is to add up the probabilities of landing in any one of these possible final photon states of the gamma, and that means we end up with a density of states as a function of frequency that we have to multiply by the probability to get the total probability. We're going to integrate over frequency. But what I want to point out is that if you make a graph of what this function looks like, you may remember that as a function of omega, this graph is highly, highly peaked at a particular value of omega, which is the omega of the energy difference between the two states. In this case, it's going to be 2.2 MeV. And the density of states function, on the other hand, is very, very slowly varying relative to the sharply peaked resonance sort of curve that you see in the probability. And so what we're going to do is to say, well, the density of states varies so slowly that we can take it outside the integral and rewrite the integral with just the sine omega over omega business. In fact, what I want to do is to change variables. We're going to change variables to a variable I'll call very cleverly x, and rewrite the integral in that way. The other thing we've done is to take the integral from minus infinity to infinity, where really it only goes from 0 to infinity. But again, the sine function is so sharply peaked that extending the integral to negative infinity doesn't significantly change the answer, and what it does do is it makes the integral one that we know. It turns out to be pi. In principle, if you don't go to minus infinity, it isn't exactly pi, but it's close enough that it doesn't make any difference. So that's the idea. If you put that answer in, you get a probability that depends linearly on time. That is, the probability to be in state B grows linearly in time. And so if you divide by the time, you get the rate at which the probability grows, and that's the transition rate. That's the rate at which this transition is said to occur. And this thing is known as Fermi's golden rule. There are different flavors of it depending on the exact assumptions you make about the perturbation and how you calculate VAB. I've seen other versions from other textbooks that are 4 times bigger than this. It has to do with Griffiths picks VAB to be a cosine, and then it turns out there's a 1/2, and that gets squared, and so you get, this is a 1/4 as big as some other people's, but you get the idea. Now, the point is we want to apply this golden rule thing to the magnetic dipole transition. And so if you put in the magnetic dipole transition and you put in the density of states, this thing comes out like so, with the matrix element mu Fi defined to be the magnetic dipole moment evaluated between the initial and final states. What is the magnetic dipole moment? Well, it's the spin of the proton times the magnetic dipole factor for the proton, plus the spin of the neutron times the magnetic dipole factor for the neutron. And but what is the sum of the two spins? Well, remember that the initial state is definitely a singlet, which means that sigma p plus sigma n is 0. Sigma p and sigma n are, of course, the Pauli spin matrices applied to the proton and the neutron, respectively. You guys, I hope, remember the Pauli spin matrices from last semester. And the thing is, what I want to do is to rewrite this sum in a kind of a funny way, where we factor out the sigma p plus sigma n part and the sigma p minus sigma n part. If you multiply this all out, you'll see that the cross terms cancel, and you end up with the same thing we have on the left. But the beautiful thing about this new expression is that one of these two terms is exactly 0 because we are in a singlet state, and so we can just throw that part away. And notice that the difference between the dipole moments factor out, and I get 2 parts. There's the spatial part of the integral that has to do with the initial and final wave functions, and there's the spin part, which has to do with the spin of the initial and final states. And sandwiched between those is the difference between the Pauli spin matrices for the proton and the neutron.
So let's focus on that part first, and let's focus on only the Z component. So realize that these Pauli spin matrices are what you call vector operators, and there's a Z component, an X component, and a Y component. And so looking at just the Z component, we can apply sigma pz minus sigma nz to the singlet. But sigma p applied to the singlet, it only applies to the proton. So the first term gets a minus because the Z component of the proton spin is negative for the first ket, and it's positive for the second ket. So see what it does is it just flips the sign of the first ket, and overall gives you minus the sum of the two kets. But that's, of course, the Z equals the SZ equals 0 version of the triplet state. That's where the two spins have opposite sign, but they add, so we're in a triplet configuration. So applying the Pauli spin operator to the singlet gives you a triplet. And similarly with the neutron version, it's just with the neutron version, the neutron is positive in the first one and it's negative in the second one, and that gives us plus the triplet, SZ equals 0. And but the original operator was sigma p minus sigma n. So when you put the whole thing back in, you get minus 2 times the triplet, the m or s sub z equals 0 component of the triplet. So that's quite simple, and it's quite nice. That means that when I put the triplet bra on there, as long as I'm using the SZ equals 0 version of the triplet, I get negative 2. The SZ equals plus 1, SZ equals minus 1, those guys give nothing because the whole thing turns out to be only proportional to the SZ equals 0. But I can put that back in, and it also turns out we just did the Z component. If you do the X component or the Y component, you get the same result. And so the squared matrix element, that's the X component squared plus the Y component squared plus the Z component squared, turns out to be 3 times the thing we just found, and so we end up with this. Now everything we know here except this darn integral. So let's look at the integral. Notice that the 4 pi r squared and the 1 over r squared are going to cancel. The 4 pi r squared comes from the volume element of the original integral, and the 1 over r squared comes from the wave function being the radial function divided by r for both the internal, or the bound state, and the free state. And so what we wind up with is the integral of these two functions, the bound state function and the incoming free state function. But notice that we're only talking about the singlet, so only a quarter of the NP pairs are in the singlet condition. And so we get a factor of a quarter that we have to throw in here. The other thing I want to do is to convert from Fermi's transition rate, gamma, to a cross-section. And the way I'm going to do that is to assume that we have a density of 1 collision per unit volume, or 1 incoming particle per unit volume. So that's going to be a density of 1. And of course, what it means is if I have more than that, I just have to multiply by the number I have per unit volume. So the cross-section we come out with is going to be the cross-section for a single target. And also the velocity here is the speed of the incoming particle, and the sigma is the cross-section. So sigma times rho times v is going to be the rate of this reaction. And so I can rewrite, I can take Fermi's golden rule, I can set rho equal to 1, I divide by the velocity, and I come up with an expression, throwing in the 1/4, throwing in the 3, and all this other stuff. I get an expression for the cross-section, and the only thing that's left is this darn integral. Now what I want to point out is that if you remember the bound state wave function, it's sinusoidal inside the well, but it's just a simple exponential outside the well. And most of it is, in fact, outside the well. The probability, the expectation value of the position of the separation, or the separation between the two guys, is greater than the well size. So that means that as a crude approximation, we can just treat that wave function as just the exponential piece.
Of course, numerically, you could go in and do the real wave function, but it turns out we get pretty good results just assuming this. And then the free part of the wave function, outside the well again, is our old friend, the sine kr minus delta 0. That's the phase shift. And it's the phase shift of the singlet. So remember, that's related to the scattering length of the singlet, which worked out to be something like 23 or 24 Fermi. If I put all that in and then do the integral, I get this terrible monstrosity. But the point is, I get an expression that I can evaluate for the cross-section. And if I put in all the numbers, put in the normalization constants, put in the magnetic moment of the proton and the neutron, and so on, and evaluate at 2200 meters a second, which works out to be about a 40th of an MeV, or a 40th of an EV, excuse me, that's sort of room temperature energy, I get a cross-section of 3/10 of a barn. Now, if you remember, the cross-section, the low-energy cross-section for scattering was something like 20-some barns. And so this is a very tiny cross-section, and it represents an unlikely event, but not an impossible event. And if you go to the Berkeley Lab data website for nuclear cross-sections and so on, and calculate and go and look up the neutron-proton cross-section at 2200 meters a second, they give a very precise answer, 7 parts in 10,000 of 0.3326. So you can see that our crude model here actually gives pretty darn good result. And I also want to talk in class today, I'm going to talk a little bit about how you might write a computer program to simulate neutron on proton collisions in the laboratory. So we'll talk about that later today. Talk to you guys soon. Hey guys, welcome back. Time for lesson 35. We're going to talk about 2 different kinds of nuclear reactions. I want to spend a few slides discussing resonant nuclear reactions, so you can kind of see how those come about, and then also astrophysically interesting nuclear reactions, in particular nuclear reactions in stars. So let's get started. I want to remind you a little bit about angular momentum and the role it plays. You know that if you decompose a plane wave into angular momentum components, the different components are important at different distances from the origin. And in particular, the L equals 0 component is dominant near the origin, and an L equals 1 a little farther away, and so on. But I want to quantify that just a little bit. Notice that angular momentum, classically, is momentum times the distance, the impact parameter. And quantum mechanically, momentum is h bar k. So that means you can get a rough estimate of angular momentum as h bar L is h bar k times r, where L is the angular momentum quantum number. And that means that R goes something like lambda bar times L. Now lambda bar is just lambda divided by 2 pi, kind of like h bar is h divided by 2 pi. But what I want to get at is to notice that the area of one of these circles goes roughly like lambda bar L squared times pi. It's just pi r squared. But that means you can compute the area of interest for a particular angular momentum component by simply taking the difference of pi r squared for one angular momentum component minus pi r squared for the next one. And that says that the central L equals 0 circle has an area of pi lambda bar squared. L equals 1 is going to be 3 pi lambda bar squared. L equals 2 is going to be 5 pi lambda bar squared, and so on. And that's going to be important here in just a second, because remember how this works. You've got a component of the scattered wave function. There's an incoming wave that goes like e to the minus ikr, and there's an outgoing wave that is similar, but it's got a phase shift. It's e to the plus ikr plus 2 times delta. So that's the famous phase shift from a couple of lessons ago. But other than that, the incoming and outgoing look pretty much the same. Then the idea is, how do I take into account nuclear reactions? Well, one formal way of doing that is to simply generalize the concept of phase shift. Instead of only allowing a phase shift, we allow the phase shift number, e to the I times 2 delta, to become a complex number. So it's not just a phase shift, but it's also a change in amplitude. And the idea is that in a nuclear reaction, the amplitude of the outgoing wave function is diminished because there's some probability of a reaction which is going to reduce the amplitude of the outgoing wave. And so you let eta sub L be a complex number where the magnitude of the complex number is less than 1. So it can have a real and imaginary part, but not being just a phase, it can have a magnitude that's not equal to 1. In fact, it has to be less than 1 to account for a diminution, a reduction in the amplitude that's moving out from the reaction. And if you put all that in, you end up with now the scattering, the L component of the scattering cross-section is the same here as it was before. It's just the same equation we had before, but I've written it in terms of lambda bar. Notice that it's just the area of the Lth component times 1 minus eta squared. So 1 minus eta is a complex number. We take its magnitude squared, and that gives us the cross-section for that, for scattering. And if you calculate the reaction cross-section, it turns out to be simply 1 minus the magnitude of eta squared. So that means if eta is less than 1, then you'll get a reaction. But if it's equal to 1, if the magnitude of eta is equal to 1, in other words, if you just get a pure phase shift, then there's no reaction at all, and the outgoing amplitude is equal to the incoming amplitude. So that kind of makes qualitative sense. Okay, so what do we do about eta? How do we find eta? Let's take an example where we just focus on the L equals 0 component of the wave. That's the dominant component in most astrophysical situations. In that case, the radial function just becomes a superposition of an incoming and outgoing exponential, e to the minus ikr for the incoming wave, e to the plus ikr for the outgoing wave, with an eta 0 attached to the outgoing component. If I define rho to be the logarithmic derivative of the radial function, that is the derivative divided by the function, times capital R, where I want capital R to be some rough idea of the extent of the nuclear potential. So in typical nuclear potential, that's going to be a few Fermi. If I plug in the radial wave function into that definition, I get a simple result that rho 0 is determined by the extent of the nuclear potential and the wave number k, and eta 0 gets sort of mixed up in there. I can solve that for eta 0 and see that it depends on this logarithmic derivative evaluated at the boundary of the nuclear potential, and it also depends on the wave number and the size of the nuclear potential. But the interesting thing happens if rho is real, if it's pure real, then that implies, if you look at the expression, you can see that the magnitude of eta 0 will be 1, and you'll get no nuclear reaction, only scattering. So if I put all that together and evaluate the scattering cross-section, I see that it looks like the scattering cross-section has two parts. It has a part that's non-resonant, that's simply a phase factor, basically. And then it's got another part that appears to have a resonance. See, the denominator can be 0, depending on the value of rho. In particular, if rho 0 is plus IKR, obviously that thing is going to get big. So we have a resonant part and a non-resonant part. And putting the same thing back into the expression for the reaction cross-section, it also appears to have some kind of resonant behavior. Now notice that the reaction cross-section is biggest when the real part of the logarithmic derivative is 0. So interesting things happen as far as nuclear reactions are concerned when rho 0 is pure imaginary. So let's push on that a little bit. Also, in order to make this thing absorb, you need the imaginary part of rho 0 to be negative. Okay, so let's put all that together and define a few things. Let's assume we're close to a resonance, and let's say rho 0 is going to depend a little bit on energy, but at the resonant energy, the real part of rho 0 has to be 0. So let's let A and B be real numbers, where the real part of rho 0 is proportional to the difference between E and the resonant energy. So that means that near the resonance, we're going to look at the real part as just having a difference between E and the resonant energy. And then the imaginary part of rho 0 is going to be some negative number at that point. And let's see what the consequences of those definitions are. If we put all that back in, the resonant part of the scattering amplitude looks like this. And you can define a width, a gamma, as 2kr over A. If you define the total width, gamma, as twice B plus kr over A, and you define the reaction width, gamma sub r, as the difference between the two, 2b over A, you can basically rewrite these expressions. The scattering amplitude, or the scattering cross-section, looks like a simple resonance ratio, something that you could see in classical mechanics of a simple harmonic oscillator, where there's a resonant frequency, a resonant energy, and the amplitude of the oscillation goes something like this. When E is equal to the resonant energy, of course, you get a maximum. Similarly, you can express the reaction cross-section in a resonant way, and the total cross-section if you add the two together. And you can see that all three of these guys have this resonant behavior. So the main point of all that is you can discover a reason for seeing resonances in nuclear cross-sections, and it has to do with the way that logarithmic derivative goes, and when its real part goes through 0. That's going to tie back, if you think about it, to the phase shift, and when the phase shift goes through pi over 2. It's all sort of very connected together. But I just wanted to bring that up to give you a little flavor of how that theory works and why resonances occur. But we're going to march ahead. That was the main point of all that. And I want to talk a little bit about the proton-proton chain, which is an important part of our own sun's nuclear energy source, the source of life on this planet. So it's an important topic. And it starts with the business of two protons coming together to form a deuteron. Now the problem is that reaction, the way I've drawn it there, it's sort of schematic, but that can't actually happen in a sense, because we just learned last time that two protons are not bound. You can't form a bound state with two protons, so there's no way a bound state of two protons could decay into a deuteron and a positron. So this must be some kind of a fiction, but if we redraw the picture a little bit to look more like this, you get a sense of what's kind of going on. The point is that a proton comes in, it decays into a neutron through a beta decay process. Then the neutron and the proton come together and form a deuteron using the same physics we talked about last lesson. So this is neutron capture by a proton, and we understand that part pretty thoroughly because we just did it last week. But how can a proton decay into a neutron? Well, in empty space, it can't, because the energy is not there to the energy of a neutron is, or the mass of a neutron is greater than the mass of a proton, and so there's no way a proton can decay into a neutron. But if you look at this whole picture of a proton and a neutron converting to a deuteron, that's exothermic. Remember that the deuteron has a binding energy of 2.23 or so MeV, and that's greater than the difference in energy between the proton and the neutron, plus the 500,000 electron volts needed to make the electron, the positron, excuse me. So it turns out there's enough energy in the deuteron creation to supply the difference in energy to let the proton decay to a neutron, plus the energy needed to make the positron. So this process does happen, although it's very, very unlikely. If you expand the proton to neutron conversion, you know that inside there it's actually an up quark getting converted into a down quark with the emission of a W+. And we're going to talk more about how you actually calculate these cross-sections when we get into the field theory and the standard model business. But suffice it to say for now that you can calculate it, and it's very unlikely. And we'll actually make in a few slides here, I'll make a ballpark estimate of how big this thing is. And even when you do the calculation using field theory the best you can, it turns out you don't do a whole lot better numerically than the ballpark estimation I'm about to share with you. So it's actually not that bad. Let's talk about the order of magnitude of things in the Sun. First of all, you know the Boltzmann constant. It's in joules per Kelvin. It's a little tiny number. But if you think of it as electron volts per million Kelvin, it's about 86.1 electron volts per million Kelvin. The Sun's internal temperature is something like 10 million Kelvin. And so that works out to be something like 860 electron volts, or about 1,000, almost 1,000 electron volts, which works out to be a speed of 4 times 10 to the 5 meters per second. So that's 400,000 meters per second. And if you work out lambda bar at that point, it turns out to be 150 Fermi. Now, since the nuclear potential is on the order of a few Fermi, lambda bar is something on like 100 times that, or 50 times that. So it means we're definitely in L equals 0 territory at that energy. One of the difficulties of doing a proton-proton binding, proton-proton making a deuteron, is the fact that both the protons have a charge. And so that's the so-called Coulomb barrier. The electrostatic potential to protons goes like this. And you guys remember from earlier this semester and also last semester that you can estimate the penetration probability, the probability of making it through such a barrier, using the WKB approximation, where kappa of R is related to the difference between the energy and the potential energy. Now, the energy is like 1,000 electron volts, and so you can put all that in. You can rewrite the potential energy as the energy times the turning point radius divided by R. Now, the turning point radius is where the energy is equal to the potential energy. So you can see that's how that works, and if you look at the expression for V of R, you can see it's the same as we had before. So that means I can write kappa of R in terms of the energy and the turning point radius. It turns out to be a simple expression in that way. If you go and do that integral, it turns out technically you only need to do it from the outside edge of the nuclear potential out to the turning point radius. But the turning point radius turns out to be something like 1,500 Fermi, and the nuclear potential only goes out to a couple of Fermi, and so it's no significant error to just do the integral from 0 out to the turning point, and you get basically pi over 2 times the turning point radius times all that junk that was out in front. And so if you plug in numbers and you can define little b to be the square root of 2 mu over h bar times pi r1 or something, and then you put in the turning point radius and you get an expression that goes like 1 over the square root of the energy. And again, putting in numbers, it turns out to work out to be something like 10 to the negative 10 or 10 to the negative 11. So per collision, per incoming proton, there is only one chance in 10 billion or something like that you're going to get close enough to participate in a nuclear reaction. So only a tiny fraction of potential proton collisions actually get close enough to participate in a nuclear process, we're going to define the cross-section to be this transmission probability times a function of energy divided by energy. And the idea is this S of E function is a slowly varying function of energy, and generally cross-sections go like 1 over energy. You might have noticed those cross-sections we dealt with before when it went like 1 over k squared. And so there's a kind of a 1 over energy relationship for cross-section, but this S sub E function we're going to have to estimate in some other way. You can do it completely analytically using field theory, but we're going to skip that for now because we haven't got there yet. And we're going to talk about velocity distributions in stars. I want to define the probability of, or the distribution function for velocity thermodynamically. It's just the kinetic energy divided by kBt, but it's defined for all velocity. So you can see the most likely velocity is 0, but then as velocity gets higher, the likelihood goes down. The reaction rate turns out to be something like the concentration. If you've got a reaction between two constituents, you got the concentration of constituent 1 times the concentration of constituent 2 times their relative velocity times the cross-section for that reaction to occur. So because we have a distribution of velocities, we have to actually calculate the average reaction rate by averaging sigma times v. So sigma is a cross-section that depends on energy, and f is the probability of having a certain relative velocity, and then you have to multiply by the relative velocity. Now here's the thing. You know that f goes like e to the minus energy over kBt. You know that sigma goes like S sub E divided by E times the barrier penetration factor that we just worked out, the T. That also depends on E. The higher the energy, of course, the more likely you're going to penetrate the Coulomb barrier. And we need to cook up some way to estimate what S sub E is. And what I'm going to suggest is the following. If you go into the laboratory and measure the cross-section of 1 MeV protons, that's 1,000 times the energy of the protons in the sun, basically, it works out to be something like 36 barns. Now, the thing is, if you just let a neutron sit in empty space, it'll decay in about 900 seconds through beta decay. But the beta decay process doesn't depend on the charge of the stuff in the neutron. So the beta decay rate of a proton, if it can decay and it's just sitting there, ought to be something like a similar rate. But the problem is, most of the time, it doesn't have the opportunity to beta decay because it's not energetically permitted. But in this case, it is energetically permitted for the time that the two protons are close together. And at 1 MeV, two protons are close together within a nuclear diameter or so for about 10 to the negative 23 seconds. So here's the idea. What's the chance that the proton will just happen to beta decay in the time that it's in the vicinity of the other proton? Well, the answer is it's the time that it's in the vicinity times the rate at which beta decay would occur naturally. And so it's going to be the ratio of 10 to the negative 23 seconds to 900 seconds. And so since S sub V has units of barns MeV, then we can compute the value of S sub V, at least at 1 MeV, by simply multiplying these two factors together. So we're just letting the natural beta decay rate of a free neutron act as an estimate of how long it would take a proton to beta decay. And if you multiply those guys out, you get something like 4 times 10 to the negative 22 in units of keV barns. And we'll see in a minute that there's a tabulated what you call accepted values for various factors here, and that's pretty darn close to the accepted value. I think it's more like 3.78 times 10 to the negative 22, but if you don't mind a 5% variance, then that's pretty good in terms of a ballpark estimate. So the question is, how do I do this integral? And the answer is, I think about it a little bit, and I realize that the f function
says that the probability of having a certain energy goes down with energy at a given temperature. So it's the blue line. But notice that the cross-section goes up with energy, because as the energy rises, of course, the Coulomb barrier is diminished. Even though the cross-section normally drops with energy, that exponential Coulomb barrier goes away as the energy goes up. And so if I multiply those two factors together, I get something like the green curve. And the idea is the green curve has a maximum, which I can compute by taking the derivative and setting it equal to 0. And it has a width, which I can also compute. And I can make a ballpark estimate of the result of the integral by coming up with a function that has the same maximum and has the same width and sort of faking it out. And that's in fact what people do. Or you can do the integral numerically, either way. But if you define eta to be the maximum energy divided by kBt times 3 and compute that, you can show that the average sigma v value depends on eta. It depends on S evaluated at the peak probability, and it depends on that factor B that shows up in the Coulomb barrier. If you then use that to compute the reaction rate, there's three possibilities. If you have distinguishable particles that are reacting, then it's just n1 times n2 times sigma v. Now there's a correction. If they're identical bosons, you've got to divide by 2, because n squared would double count the pairs. And it's even worse if it's identical fermions. You've got to divide by 8, because you have the pair counting problem, which you have with bosons, but also with fermions, the only way they can interact is if they're in a state that's overall antisymmetric. And that means that the spin part has to be antisymmetric and the space part has to be symmetric, and that implies that you got to have spin 0. So they have to be in a singlet configuration to interact significantly, and that cuts you down by a factor of 4, because there's 4 possible spin states. Only one of them works to make this happen. So for identical fermions, it ends up being n squared divided by 8. Anyway, the bottom line is, now that we just talked about the pp interaction, that's protons on hydrogen. That's the first row in this table. But all these numbers are computed here. Notice the S0, which turned out to be 3.78 times 10 to the negative 22 keV barns, where our estimate was 4. That's not too bad. And then the important result that you get from this is that the rate gives you a half-life in years, how long it takes this reaction to occur, of about 8 billion years on the average. And so that means that it's a very slow process. All the other processes in the chain that produce helium in the end, notice there's a bunch of different reactions there. Most of the rest of them are very fast in comparison. There's a few that take, a million. There's one that takes 1 million years, but that's kind of a side chain. It's not really the main event in terms of making helium. So by far and away, the dominant slow piece in the reaction is the proton-proton part. There's another set of reactions called the carbon cycle, and it also is important in producing helium in the sun. But we're not going to talk about that today. I just wanted to give you guys a flavor of it. We'll see you in class. Welcome back, guys. It's lesson 36. We're coming down to the final stretch. Just a few lessons left. This is the first of a 3-part set of lessons about the standard model of particle physics and quantum field theory. Now, you can't do all of the standard model and quantum field theory in 3 lessons, and maybe I'm foolish to try, but I mostly just wanted to give you guys a sense of what it's about. So that's what we're going to talk about. Let's get started. First of all, there are 2 major families in the standard model. There's the sort of matter part, which consists of the fermions, which is, and there are 2 groups of fermions, the quarks, up and down, charm and strange, and top and bottom. They come in pairs. Each
pair has a positive and negative member. The positive is plus 2/3 charge, the negative is minus 1/3 charge. And notice that the positive charges are one elementary charge greater in charge than the negative charges. So the difference in charge between up and down is 1. And that's also true of the leptons. The leptons have a difference in charge of 1, but in this case, the electron has a negative charge. The neutrino, the electron neutrino, has a 0 charge, and so they have a difference in charge of 1 unit. Same with the muon and the muon neutrino, and the tau and the tau neutrino. So the leptons are relatively light particles with nearly massless partner particles. The electron has much, much greater mass than the electron neutrino. But having said that, the up and down quarks are even more massive than the leptons. Then the leptons in the same column, I should say. And then there are the bosons. The bosons generally play the role of the force carriers that act between the leptons. I say generally because there are exceptions to that, but we got the gluons. The gluons, it turns out, carry the color force. In other words, quarks have a color charge, and the gluons are the ones that the quarks exchange with one another in order to interact via the color force. And the anything with charge and weak charge can interact using photons, which are the gammas, and then the W and Z bosons are the carriers of the weak force, and they interact with objects that have weak charge. And finally, I don't want to call the Higgs a force exactly. The Higgs is basically a field that is theoretically permeates all of space, and it enables these particles to have mass to the degree that they interact with the Higgs field. And we're not going to talk about the Higgs field today at all. I'm hoping that on the third day of this we'll have a chance to discuss exactly what the Higgs mechanism is and what the Higgs boson actually does. But let's start with the more straightforward and more direct interactions, and those start with the photons. So photons interact with anything that has electric charge. So that could be any of the leptons, any of the quarks. Those are the only things that have electric charge. And basically the most fundamental interaction is simply an emission or absorption of a photon by an object with charge. So that's all there is to it. Then the weak bosons are the W+, the W-, and the Z, and they interact in a similar fashion to anything with weak charge. So in fact, it turns out the electric and weak forces have been unified theoretically at high energy. They behave the same at high energy, but there is what you call a symmetry breaking that happens, and at the energies that we see on a day-to-day basis or in our laboratories, they appear to be very different. But in fact, the underlying theory is unified at this point. Then there are the gluons, which interact with quarks. So quarks carry color, and the gluons, in the same way that the photon interacts with the electric charge, the gluons interact with the color charge. And the other thing is the gluons actually carry color with them, and so unlike photons, gluons can interact with one another, and that's one of the things that makes dealing with the quarks and the gluons and the color force in general so complicated. Now, where can you go to learn more? There is a free book on the internet. You can go and grab it from the Particle Data Group, and it has all kinds of lovely details about all the wonderful stuff that you can learn about the standard model and how it all goes. I just want to point out a couple things. This is a free download, so it's an amazing resource. One is that we're going to be working with the baryons a lot right away, and I just want to point out also that these guys have a whole chapter set aside for Monte Carlo techniques, so I'm not making this stuff up. People really use this to get work done. And so as I'm encouraging you to use Monte Carlo techniques in your computing projects, understand that it's a skill that may prove useful in the future. Okay, so let's get back to those baryons. Why do we have this quark model? Well, part of the reason is, before the quark model, there were lots and lots and lots of different kinds of particles, and there were some relationships that people understood, but basically it was a zoo of many, many kinds of particles. And we understand today that those complicated particles are actually just superpositions, combinations essentially, of the 6 quarks that have been discovered. And so here's a couple of families you can see made up of up, down, and strange, charm, and so on. This is not a complete set, but it just gives you an idea of the complexity of particle physics, and when you actually go to measure these guys, how complicated it can get to understand what's going on. But anyway, let's start at the beginning. Let's talk about some simple processes that we might want to understand. So, for example, electron-electron scattering. What's the simplest thing that can happen? Well, one electron can emit a photon, another electron can absorb the photon, and that corresponds to a process whereby 2 electrons interact with each other. Of course, you could draw the same diagram for the hydrogen atom, because you've got a proton which has a charge, and the force between the proton and the electron can be thought of, at least at some level, as a scattering event of a photon between the electron and the proton. But that ain't all that can happen, because you could have 2 photons. And you could have 2 photons, and in the middle you could create an electron-positron pair and exchange those between the 2 photons. And so you can see that the thing can get fairly complicated. And part of the trouble with doing calculations in particle physics is that oftentimes you end up having to perform these calculations that include very complicated effects. And so that's what I basically want to introduce you guys to, is how you think about this stuff and how it goes. We're not going to get into too much of the thick of it, but you get an idea. So there's also, in addition to scattering, you can have decay type events. So for example, a Z0 can decay into 2 particles, and I want to point out the arrows here. We're thinking of time advancing to the right, and in this picture you'll notice there's an F advancing to the right. That's a fermion of some kind advancing to the right, but then there's an arrow that looks like it's going backwards, pointing back in time. That's an anti-fermion. So this would be a fermion and an anti-fermion, and they're not necessarily the same fermion, but the point is, when you have an arrow that goes backwards in time, that's a clue that that's an antiparticle. So here's something that does happen. We have a down quark with a charge of -1/3. It's going to emit a W-. Now it turns out when a particle emits a W-, it also changes its flavor, its character, and so in this case the down quark is going to convert to an up quark. Notice the charge is conserved, because on the way in we have a -1/3 charge, and on the way out we have a up quark with a charge of +2/3, and we have a W- with a charge of -1. But then in addition to that, the W- then decays into an electron, but it also has to change flavor, so we have a electron antineutrino. Now, if the neutrino were going forward in time, if this were a weak scattering event where you send in a down quark and an electron neutrino, you could scatter and send out an electron and an up quark. But this is a scattering event turned on its side, in the sense because both the electron and the neutrino are moving forward in time, and so that means that's got to be an antineutrino, because the vertex has to have an incoming and an outgoing particle, but the incoming particle is actually a decay product of the W-. So anyway, I hope that's not too confusing. It's a little strange, I appreciate. And here's another kind of thing that can happen. You can have a positron and an electron scatter two gammas, but notice it would look like a scattering event if the thing were sideways. It would look like an electron scattering two gammas and then going off in the forward direction. But because we have the electron leaving the thing moving backwards in time, it's actually a positron coming in. And what we really have is a positron-electron annihilation producing two gammas. And here's another case. We have an up quark scattering, emitting a W plus and scattering a D. It's a D anti-quark, right? But here's the thing. The D quark is moving backwards in time. That means it's got to be an anti-quark. And so what we really have is an up-down bar, which is a flavor of pion. It's a pi plus, basically. And so we have a pion decaying to a W plus, and then that's further decaying into a anti-muon and a muon neutrino. Notice the muon is moving backwards in time. That makes it an anti-muon, and it's decaying along with its associated neutrino. So that's the idea. Notice that the weak bosons are interesting, the W plus, W minus, because they change flavors of particles. They change electrons into neutrinos. They change up quarks into down quarks. They can even change an up quark, for example, into a strange quark. So, and here's an example of that. Here we have a strange quark changing into an up quark, okay, emitting a W minus, and then the W minus decays into a pi minus, a down quark and an up bar. So there's another example of something crazy that can happen, and you get the idea. I hope you get the idea. Let's talk about the basics of field theory. So the notion is in regular old quantum mechanics, we have T as a parameter, R is an operator, it's an observable, psi is a wave function, it's the state vector. Okay? We're going to change our point of view and switch to field theory. And one of the things that has to happen in field theory is R and T have to get put on the same footing. Now, there are some approaches that make T into an operator, but the approach we're going to take is the more common approach, is that in which we move R to be just a different parameter. So R and T are now going to become parameters, and psi is going to be elevated to an operator, and the state is going to be a ket, which tells you how many particles are in the various single particle wave function states, wave function type states that we can understand. And so it becomes a vector, the state vector. Okay, and what is the vacuum? The vacuum is just nothing. It's there are no particles in any states, and because nobody wants to write a bunch of zeros, we just use the zero ket to mean the vacuum. Notice that's different than the null ket. That is a real ket. It's just a ket with no particles in any of the states. And then you can think of a ket with a single particle in a particular momentum state as what you get when you apply a creation operator associated with that momentum to the vacuum. So applying a creation operator to the vacuum puts a particle in a particular state, and if you put particle I in state k sub I and particle j in state k sub j, you can do that with two creation operators. Now, depending on whether the particles are bosons or fermions, we may have different commutation relations for the creation operators. If they're bosons, then the order doesn't matter. You can put them in any order, but if they're fermions, then switching the order has to switch the sign in order to satisfy the symmetry requirements of fermions. So we'll run into that a little bit later, but I just wanted you to make sure you understood that the commutation relationship for bosonic creation operators is that they commute, For fermionic operators, I'll get there, they anti-commute. So what that means is if you apply them in one order and then you add to that what you get when you apply them in the different order, that gives you 0. Whereas for bosons, if you apply them in one order and subtract what you get when you apply them in the opposite order, that gives you a 0. So bosonic creation operators commute, bosonic annihilation operators commute, and the creation and annihilation operators commute with each other so long as they're talking about different momentum states. If they're the same momentum states, then the commutator is 1, and that's how you get the raising and lowering business. But for fermions, it's exactly the same creation and annihilation commutation relations, except that they're anti-commutators instead of commutators. So they anti-commute. Let's talk about a change of basis. The basis I've been thinking about as we've been talking about these creation and annihilation operators is the sort of the plane wave basis. If you imagine plane waves of fermion particles propagating through a big box of volume V, that would be the e to the ikr sort of version. But I want to imagine that we do a change of basis where we switch from the momentum basis to the space basis. So for example, if you have a state phi and you want to express it in the momentum basis, you simply use the identity, just like we've been using all year. But let's suppose you have a state x and you want to express it in the momentum basis. You would again use the identity, just like this. But x may correspond to a state of well-defined position. And we know what the amplitude is. If I have a state of well-defined position and I ask what's the inner product of the momentum k sub I, we know that that is going to end up looking like e to the minus I k sub I times x. That's just the definition of what I mean by a definite momentum and what it means to have an amplitude to have a definite momentum. I can put that in as k sub I on x, and I can get an expression that tells me how to write down the ket that corresponds to a particle at a definite position in the basis of plane wave momentum eigenstates. So we're going to use that. In fact, how do I get a particle at position x? Well, I apply the creation operator that creates a particle at position x to the vacuum. But you can see here now I can read off exactly how to do that. What I do is I create a bunch of a superposition of different momentum eigenstates and have that act on the vacuum. But if I've got the vacuum on the right of the left-hand side of the expression and I got the vacuum on the right of the right-hand side of the expression, I can just get rid of the vacuum if I don't need to put the vacuum in there, and I have now a definition of what I mean to create a particle at position x. If you need an operator that creates a particle at a particular place in space, this is how you do it. It's a superposition of plane wave momentum eigenstate creation operators. So that creates a particle at position x. So how can I describe an interaction then if I've got this mechanism that allows me to create particles? What I might do is say, well, let's say I've got, I want to describe a scattering process where a particle comes in with some initial momentum, it scatters and ends up in some final momentum. I could do that with an interaction Hamiltonian that destroys a particle with momentum k and creates a particle with momentum k sub L. I'm sorry, it destroys a particle with momentum k sub m, creates a particle with momentum k sub L, and you can see that that's going to describe a process, an interaction that takes particles out of one momentum state and sticks it into a different momentum state. Well, if I have a particle coming in with momentum k sub I can create that by applying a creation operator to the vacuum with momentum k sub I. And if I want to create a particle with momentum k sub f, again, I could do that with a creation operator. What that means is if I want to compute something like the amplitude of being in momentum k sub f after an interaction, starting with momentum k sub I end up with a sum that looks something like this. In other words, this gives me the matrix element between the incoming and outgoing wave, and I'll end up with a sum over the interaction potential and then these creation and annihilation operators acting. Notice that I only get something if the destruction, that A sub km and A dagger sub ki happen to line up, and equivalently with the second two have to line up. Let's think about another possible process we could imagine. Let's say we want to describe a decay at a definite place, but at an unknown time. You might imagine trying to compute Fermi's golden rule or something like that. You have Fermi's golden rule. It says that the probability of a decay goes something like the matrix element between the incoming and the outgoing situation. So I need that matrix element in order to compute the probability of a decay. But notice that if I have a definite place but an uncertain time, I have to express my psi and my psi dagger with some kind of superpositions of creation and destruction operators in the plane wave representation. And if I let x equals 0 and I go to do that calculation, my x is at a definite place, but I'm going to have to integrate over all possible times when this interaction could occur. And notice that the kx's are all going to go to 0 in that integral, but the omegas are still going to be there, even if I put in x equals 0. And so I'm going to end up with a factor in my calculation that looks like an integral over all possible times of e to the I omega sub L plus omega sub m minus omega sub k. They come right out of the definition of the interaction. And notice that that is nothing other than a delta function. It's a delta function that ensures that the energy is the same at the end of the scattering experiment as it was at the beginning. In other words, if I allow the time to be unknown, I have to integrate this process over all possible times when it could occur. That in itself is automatically going to ensure conservation of energy. Similarly, what if I have an interaction at a definite time but in an uncertain place? In a similar way, we're going to have to integrate over all the places where this could happen. But if I know when it happens, I can just put in t equals 0. And again, I'm going to end up with an integral, but this time it's going to be an integral of e to the I kl plus km minus kk. In other words, it'll be an integral that looks like a delta function, but it's a delta function that ensures conservation of momentum. So the moral is that if I have a process that I don't know where it's going to happen, when I'm done with the calculation, the total momentum of the system before and after is going to have to be conserved. And if I have a situation where I know neither when exactly it happens nor where exactly it happens, then the same process, I'm going to have to integrate over all possible times and all of space, the same exact process that describes the interaction in terms of these the plane wave representation is going to ensure that the momentum and the energy are both conserved. So that's an interesting insight. I just want to point that out to you, and we'll encounter this as we do other calculations. But what I really want to finish with today, I'm going to finish up here in a little bit, is to describe how forces come about in a field theory context. So you remember that we studied the simple harmonic oscillator, and I want you to imagine we have a field that can be thought of as having a position-like part and a momentum-like part. For example, this would be like the electric and magnetic field. The electric field is a little bit like position. You can formally identify magnetic field as a little bit like momentum, and you can write down a Hamiltonian that looks like the sum of the squares. Remember that the energy density of an electric field, electromagnetic field, goes like 1/2 epsilon 0 E squared plus 1/2 B squared over mu 0, and so that smells a little bit like a simple harmonic oscillator if you identify one as position and the other as momentum. The good news is if you can do that, then you can write out the Hamiltonian exactly analogously to the simple harmonic oscillator. And since we already know the solutions to the simple harmonic oscillator and we cooked up the creation and annihilation operators, we call them ladder operators or raising and lowering operators, but they're exactly the same thing. We cooked those up for the simple harmonic oscillator, and using those we could work backwards and solve for the position operator and the momentum operator in terms of the raising and lowering operators. We can do exactly the same thing with the field. Basically, what we get are in a box of volume V, we end up with these fields that look like the modes of the field in the box. And so we can write out for every single mode, we can write out the plane wave representation of the field using the the creation and annihilation operators for the field. And the total Hamiltonian of the field just works out to be the sum of the energies in each of the modes. And each mode then acts like a simple harmonic oscillator. That's the idea. Very quickly, I want to suppose we want to model an interaction between two objects which interact with this field. So let's let the objects be the psi field, and the interaction, the things that mediate the interaction, we'll call that the phi field. But I don't want to really let the psi particles move around. So what I'm going to do is say, let's imagine that the psi particles are stuck at some particular place. So instead of psi dagger psi, which would sort of measure the number of psi particles at a particular place, I'm going to replace the psi dagger psi with just a delta function. That has the effect of saying, well, basically the psi particle is going to be stuck at R1. It's going to have an infinite mass, essentially, so it's not going to move around or do anything. But it's still going to interact with the phi field. So I'm going to forget about the psi field for the moment. I'm going to focus on the phi field, which would be the field of the bosons with which these phi particles interact. That's the idea. Now the delta function is in the Hamiltonian density. Hamiltonian density is a Hamiltonian operator per unit volume. So I need to integrate over all of space in order to compute anything like the Hamiltonian itself. And so we can integrate over all space, and what we get is a superposition of plane waves. But notice that because the delta function put the psi density at all focused in one place, R1, that this Hamiltonian now has a definite R1 in it in the plane wave representation. Now here's the question. I want to use perturbation theory to calculate the effect that being in this field of phi particles has on the psi particle. And so I could compute the perturbation. The first order perturbation of the energy is simply going to be the expectation value of the Hamiltonian in the unperturbed state. Well, the unperturbed state is the vacuum of the phi field. And so if I plug that in, notice that every single term has an A dagger and an A, but if I apply A to the vacuum, I get nothing. If I apply A dagger to the vacuum, I get one phonon, or one boson in the field. But notice I'm then taking the inner product with the vacuum, and I'll get nothing. So it turns out there is no first order perturbation. The question is, what happens if I calculate the second order perturbation? Remember how you do that is you take the sum of all the states except for the vacuum. You don't include the vacuum because we don't want to introduce a degeneracy here. And you compute the inner product between the vacuum and the kth mode, and then the kth mode back to the vacuum, and you divide by the difference in energy between the kth mode and the vacuum. That's the idea, and you see what you get. Now I want you to think about this. This is actually corresponds to an emission of a boson and the reabsorption of a boson. You can think of the 0 H1K as the emission
process, and then the K H10 as the absorption process. In other words, that's the amplitude to excite one boson through the interaction, and the amplitude to de-excite one boson, again through the interaction. That's what's in the numerator there. And you got to divide that, according to the rules of perturbation theory, by the difference in energy between the boson in the field and the vacuum. So let's think about that. If I calculate 0 H1 on K, notice I just get I get a G squared, I get a 1 over V, and I get e to the IKR. Remember, e to the IKR1 was what was in those the coefficient of those creation and annihilation operators. And so I get something. I can add those guys up. The bad news is that when I go ahead and put in the density of states, remember that we're adding up all the K vectors, which means we're in K space. We're going to put in the density of states in K space. We're going to go ahead and put in the energy. And if you do all that, you end up with this terrible monstrosity. But the terrible thing, the truly terrible thing is, notice that when K becomes large, I get a K squared upstairs, and downstairs, I use the relativistic energy formula for the energy squared. I get a K squared plus a constant. And so as K gets bigger and bigger, the K squared upstairs and the K squared downstairs will cancel, but it's an integral over all K, all the way out to infinity. And so the bad news is this integral diverges. It's infinity. So that's bad. I mean, it looks like perturbation theory might not have been such a good idea. But never mind that. Let's march ahead and see what happens if I put in 2 psi particles. In other words, I put in 2 delta functions. I put a delta function at R1, I put a delta function at R2, and I repeat that whole process. I mean, if the first one was infinity, then the second one's got to be infinity too, right? So this is hopeless. But let's try it. Again, there's no first order perturbation for the same reason as last time. But if I put in both of the interactions into the second order perturbation formula, notice that I get an interesting thing happening. I get when I multiply all those products out, I get the same thing I had before. I get the charge 1 interacting with itself. I get charge 2 interacting with itself. And remember, we already know that if we calculate the integral for a charge interacting with itself, we're going to get infinity. So this is not looking any better. Now we have 2 infinities. But these middle 2 terms are more interesting because notice what they represent is the vacuum interacts with the charge and puts a boson in the field. Then that boson in the field interacts with the other charge and goes back to the vacuum. So this corresponds to an emission and absorption of a boson by one and an absorption by the other. And the other term is the same thing, except it's the complex conjugate. Well, let's think about that. If we have Hi1 and Hi2 given as these expressions that we already worked out before, and we compute this inner product, notice that a dagger on the vacuum gives me 1, and 1 on 1 gives me 1. So this actually produces a non-zero result. A on the vacuum gives me nothing, so that doesn't contribute. But for the other inner product that I need to compute, I go 1, H12 on 0, and so starting with 1, it's the annihilation operator that produces something. It gives me the vacuum, and then the vacuum on vacuum gives me 1. And so in this case, it's the annihilation operator that contributes to the inner product. And when I multiply those two guys together, notice I'm going to get an e to the ik r2 minus e to the ik r1, or e to the ik r1 minus r2. The other term is exactly the same, except it's the complex conjugate. So what I'm going to wind up with is e to the ik r2 minus r1 plus e to the ik r1 minus r2. That's, of course, nothing other than the cosine of k r2 minus r1. And
as you know, the 1 is from the it's from the two outer terms, which were the charges interacting with themselves, and that part gives us infinity. Still gives us infinity, twice as much infinity, in fact. But the second part is interesting. Let's go ahead and work that out. If we put in what k times r1 minus r2 is, let's imagine r1 minus r2 is just called r, and it points along the z-axis. Then k dot r is going to be kr cosine theta, where theta is the angle relative to the z-axis. And so I get this integral. This integral actually looks very much like the integral in Griffiths that he does to study the Born approximation in scattering. I'm going to repeat parts of it. I can separate the cosine into the e to the ikr cosine plus e to the minus ikr cosine. I can do the integral over sine theta, and that gives us a sine kr times k over the energy denominator. Again, the energy denominator I've converted to the relativistic expression for energy. And this can be done with the contour integral, similar to the contour integral that Griffiths does, except this time there's no poles along the axis. The only poles are in the upper complex plane and the lower complex plane. This is what the integral reduces to. In the upper complex plane, there's a pole when k is equal to imc squared over h bar c. And in the lower complex plane, there's a pole when k is equal to minus imc squared over h bar c. But in both cases, we can evaluate the integral by using Cauchy's complex integral formula or whatever. We calculate 2 pi I times the residue at the pole. To find the residue, we simply plug in, we get rid of the pole part and we plug in the value of k in the rest of the expression. So downstairs we're going to get 2mc squared. Upstairs we're going to get imc squared over h bar c for k. And if you put that in, you get a real exponential, e to the minus mc squared r over h bar c times some junk out in front. You get the same result for both of these integrals. And so plugging that all back in and looking at, forget about the units. The units are whatever they have to be in order to make this thing work out to be energy. What I want to focus on is that the energy goes like minus the coupling constant squared divided by the distance between the two charges times an exponential factor that's related to the mass of the bosons. This is Yukawa's famous formula, and we worked it out for a simple kind of a field theory that has the simplest possible context, to just bosons with no polarization and no other special features. These are not photons, these are not mesons, because we haven't invoked any of the necessary technicalities in order to handle photons. Photons are, they've got polarization, and the charges are not electrons or quarks or anything, because those guys have other features as well, like spin and so on, that we haven't taken into account. But I just want to point out that this is the sort of mechanism through which a field theory can give you an attractive force. And the interesting thing is that if you let the mass of the bosons become 0, then this gives you a 1 over r potential. If the mass of the bosons is not 0, then this is the Yukawa potential. And in fact, you can see very easily here, h bar c is 197 MeV Fermi. In order to make an exponential factor that goes away in about a Fermi or so, you need a mass. The mc squared has to be something like 200 MeV. And that's exactly what Yukawa predicted. He said there'd be a meson with about 200 MeV. And in fact, the pi meson is just about like that. And so it's the so-called meson theory of the strong interaction. And the g, the coupling constant, is basically like the charge. It sort of plays the role analogous to electric charge. So that's it. That's a little longer than I had hoped, but that's the way it goes. We'll see you guys in class. Hey guys, welcome back. It's lesson 37. It's part 2 of our slides on the standard model and quantum field theory. Today I want to focus on one thing in particular, but I wanted to point out that there's 3 different kinds of calculations we're going to learn how to do. There's bound states, which we'll do today. Decay rates and cross-sections we're going to handle next time. So let's get started with bound states. First of all, I want to remind you that in the hydrogen atom, you guys know all about the bound states of the hydrogen atom, but there's this fine structure thing, which is a combination of the relativistic corrections plus the coupling between the angular momentum and the spin of the electron. And that produced a correction that depended on the total angular momentum of the electron spin plus the orbital angular momentum of the electron, and we called that total angular momentum quantum number J. But then there was also the hyperfine interaction, which was the interaction between the magnetic moment of the nucleus and the magnetic moment of the electron. And it was much, much smaller, that's why they called it hyperfine, but it depended on whether the electron and the nucleus, in this case the proton, were in the singlet or the triplet configuration. And so it went like this. So I just wanted to remind you that that exists, and then I want to point out that you can make a hydrogen-like thing out of an electron and a positron. And that hydrogen-like thing is called positronium. And of course, the one big difference between positronium and hydrogen is that the mass of the positively charged partner is equal to the mass of the electron, 2,000 times lighter than the proton. And so the reduced mass of the system is half the electron mass. And that means that the bound state energies are all halved if you work through the math. And it also means that the Bohr radius is doubled. So the Bohr radius of positronium is, well, I should say, the radius of the positronium wave function, the scaling factor that goes in the exponential, is twice the Bohr radius, which is like half an angstrom, so this is more like an angstrom. And if you work through the fine structure calculations, it's a little bit more, it's a little pesky because of the differences in mass and so on, but it comes out to be something like this. It looks fairly hideous. And it also has to include a term which involves the electron and the positron periodically annihilating one another and then emerging from their annihilation to be an electron and positron again. That term actually has it's the so-called annihilation shift, and it's basically the same kind of order of magnitude as the fine structure. So it is important to understand to get the spectrum right. The other thing is that in this process where the an electron and positron annihilate and produce a photon, it's possible for them to produce even numbers or odd numbers of photons when they finally do annihilate. If they annihilate permanently, not like this Feynman diagram I have here, but if they go through a permanent annihilation where they're gone forever, then there's a selection rule that comes into play that has to do with the charge conjugation symmetry. And basically it says that L plus S has to have the same parity as N. In other words, if L plus S is odd, then N has to be odd. If L plus S is even, then N has to be even. Of course, for these guys to annihilate, they have to come right up next to each other, and so that means only S states work, so L is going to be 0. And so in the singlet configuration, where the two spins are opposite, S equals 0, L equals 0, that means N has to be even. So you could produce 2 photons in the singlet configuration. On the other hand, if it's in the triplet configuration, S is 1, and then N has to be odd. So in the triplet configuration, the thing can only decay if into 3 photons, or 5 or 7, any odd number of photons. It can't decay into 1 photon because then there's no way it could conserve momentum. So 1 photon is definitely not allowed. Anyway, let's oh, and by the way, the decay time, which we'll talk about how you compute decay times next time, is about 1/8 of a nanosecond. So these guys stick around on a sort of time scale of electromagnetic radiation and electromagnetic frequencies. That's a pretty long time. Okay, let's talk about the spectrum of positronium. It's similar, kind of behaves a little bit like the hydrogen spectrum. You can see you've got the fine structure and so on going in there. The n equals 1 state and the n equals 2 state are shown on the left in unsplit energies, but because of the fine structure and the what you call annihilation effects and so on, the states get shifted. Notice the singlet states are a lower energy than the triplet states, and if you look at the 2p states, they get split into a triplet and a singlet, depending on what's going on with the spin. So L equals 1, you've got singlet 1p1 and a triplet 3p, 0, 1, and 2. So that's how positronium looks. Now here's the interesting thing. Not only can you make positronium out of a particle and its antiparticle, it's possible to make quark superpositions of particle and antiparticle, or quark combinations of particle and antiparticle. And an example of such a thing is called charmonium. Charmonium is made from a charm and anti-charm quark together in a sort of a meson configuration. Again, you've got a reduced mass. How do you make these guys? Well, you can make them in the same way you make positronium in a way. You bombard electrons with positrons, and you produce quarks and antiquarks. In this case, a charm and anti-charm quark can come out together in a bound configuration. The question is, how do we model that? And the answer is, you could think of the charm-charm interaction as kind of a 1 over r potential plus something else, because you know that you can't separate quarks. They don't like to be separated and left out alone. So you model the quark-quark interaction as a force that grows with separation. In this case, it's the simplest thing you can think of. It's just a linear force. It's a constant force because, of course, the force is the derivative of the potential, and the potential here is linear. So we model this as a constant force that lets the potential grow at larger and larger r. And the question is, what do we get with that? Well, there's no Bohr formula for a 1 over r potential plus a linear potential, but you can work it out numerically. And if you work it out numerically and try to match the excited state energies of charmonium with the eigenstates of this potential, you end up with a force that's like 900 million electron volts per Fermi. So that means if you try to separate these guys by a Fermi, you're going to have to do 900 million electron volts of work. That's enough for 3 or 4 quarks. Okay, so that means these guys don't like to separate at a large distance. But notice that at small distances, that second term goes away, and you end up with just a simple 1 over r potential. And understand, this is not, nobody's pretending this is the correct formula for a potential for the quark-quark interaction, but it is a simple model that agrees roughly with experimental data. What I want to focus on is the spectrum of charmonium. When charmonium was first discovered, it was discovered using the same experimental setup that I mentioned here. But notice that a gamma is a photon with a spin of 1, and so the charmonium has to come out in a triplet configuration. Its ground state, it turns out, is actually a singlet, but when it's born in the laboratory through this process, it's born in the triplet configuration, and that particle was called a psi. There's another friend of the psi, which turns out to be nothing other than an excited state. It's the 2,3s1 configuration of charmonium, and it's called the psi prime. The ground state was called a different name, and it was called the eta c for charm, and eta prime c is the n equals 2 singlet configuration of the charmonium. You can see that these guys are different in energy by hundreds of millions of an electron volt. Compare that to positronium, where the scale was actually multiplied by 1,000 just so I could draw it on the screen. And in this case, the difference in energies here are hundreds of millions. So we're looking at sizable fractions of a neutron or proton mass, and which is why it's understandable that people thought of them as different particles, even though they're actually just excited states of the same particle, different excited configurations of the same particle. And then also notice we've got the 3p states and the 2p state. Now the 2p state's never actually been measured to my knowledge. That could be wrong now, but last I heard it was not measured. So it's suspected to be there, but experimental difficulties make it hard to actually measure. All right, so that's charmonium. Let's talk about the light quark mesons. The light quark mesons are these guys. Actually, this is 9 of them. This is a nonnet, the pseudo-scalar nonnet. This is a bunch of different quarks, or mesons, which are superpositions of 2 quarks that are in a spin 0 configuration. So for example, the K plus, the K0, the K minus, and the K bar 0 are combinations of up, down, and strange. The K0 and the K plus have anti-strange quarks combined with up and down quarks. And if you check the charges there, you'll notice the charges are right. Down is a negative 1/3, and S bar is a plus 1/3, so that's a neutral strange meson. And K plus is an up, which is plus 2/3. Strange bar is anti-strange, so that's plus 1/3, and so you get a plus 1 charge on the meson. The quarks always combine in nature to form integer numbers of charges, and they also form colorless combinations, so that has to be colorless. But what I want to talk about first, before we get into the pi and the pi minus and so on, these other mesons that are in here, is the idea of isospin. So isospin is the notion that the charge is related to an isotopic spin. Folks noticed that the neutron and proton were almost identical, except for the charge business, but that the binding of the proton and the neutron didn't depend, the strong force binding didn't really depend on the charge at all, that they behaved about the same. And so they invented this concept of isospin, and they said that the proton was isospin plus 1, and the neutron, isospin plus 1/2, and the neutron was isospin minus 1/2. And then if you drill down and see what does that mean about the quarks, it means the up quark has to have a spin 1/2 in isospin space of plus 1/2, and the down quark is isospin minus 1/2. In order to get the behavior of isospin correct for antiparticles, it turns out the anti-down has to have an isospin of minus up, and the anti-up is a spin of minus 1/2. Minus 1/2, but plus minus 1/2. If you see, the algebraic phase is positive, but the spin is down. In the anti-down, the algebraic phase is negative, but the spin is up. Now, what good is that? Well, what good it is that if you think about the pi plus, you can think of it as a isospin up-up. And if you go and look at what it takes to make an isospin up-up out of an up and an anti-down, you can see you end up with negative up anti-down. The pi minus, on the other hand, is down anti-up. So it turns out to be the antiparticle of the pi plus. And what good is that? Well, what good that is if you look at the pi 0, it is an isospin of 1, just like the pi plus and the pi minus, but it's rotated in isospin space through 90 degrees. So just like angular momenta add, if you think of the pi plus is the 1, 1, and the pi minus is the 1, minus 1, the pi 0 is the 1, 0. And if you remember how 1, 0 added together, it was up, down, plus down, up. So that is an isospin eigenstate, and it's formed out of two different flavors of quark. It's up, anti-up, minus down, anti-down. And what's wacky about that is the pi 0 is actually not made out of a definite combination of quarks. If a pi 0 decays, or if you tore it apart somehow and looked inside, half the time you'd see an up and anti-up quark, but half the time you'd see a down anti-down quark. So it doesn't have a definite quark composition, which is kind of wacky and new. And that's actually the reason I'm bringing it up, is that these particles, you don't think of them as just definite superpositions or combinations of quarks, but some of them are actually quantum superpositions of different kinds of quarks. So that's kind of wacky. This business of isospin, it's called isospin flavor symmetry. All right, let's look at another kind, another set of mesons. These are called the vector mesons, and they're called vector because the spin is 1. The two spins are aligned. That's the only difference between these guys. So we're still talking about up and anti-strange and down and anti-strange for the K0 star and the K plus star. It's just now the two spins are aligned. If you go and measure the mass of these different mesons, you get the following results. Notice the mass goes up, but notice also that the pi's and the rhos have significantly different masses. So you'd think that, wait a minute, the rho is an up the rho is an up anti-down, and the pi is an up anti-down, pi plus and rho plus. So why the heck does it matter? It means that there must be significant spin-spin interaction between the quarks. In other words, just in the same way that the electron suffers spin-orbit interaction and the electron and the proton have spin-spin hyperfine interaction, there must be corresponding hyperfine interaction in the quarks because the energy of the rho plus is much, much greater than the energy of the pi. And so you think about that and you say, well, maybe the mass, there's a term that corresponds to the mass of the first quark, the mass of the second quark, plus there's a spin-spin interaction term. And if you remember from hyperfine structure, the spin-spin interaction in the singlet state went one way, the spin-spin interaction in the triplet state went the other way. And if you plug all that in and do a fit for the observed energies, you get the mass of the up and the down is a certain amount, the mass of the strange is a bit more, and the coefficient that gives you the correct energy dependency is 159 MeV times this coefficient. So you can actually measure it. But if you plug all that in and go back and compute the masses of these particles, you get the following list. These are calculated using the formula right there on the screen. And you'll notice the agreement is not exact, but it's pretty darn close. And that means that there's more going on than just the sum of the masses plus the spin-spin coupling, but that's a lot of the story. And that's why this is such a successful theory. So let's say we want to do baryons. Baryons, it turns out, are similar, but now every particle has 3 quarks. The other problem is we need color symmetry, plus we need to deal with the Pauli exclusion principle, because in most of the baryons there are more than one quark of the same flavor. And so in order to do that, we need to consider the space symmetry, the spin symmetry, the flavor symmetry, and the color symmetry. And the overall wave function, these are fermions, remember, the overall wave function has to be anti-symmetric with respect to interchange of any two identical quarks. And it turns out the color part is always anti-symmetric. So that means that the space, spin, and flavor parts have to be completely symmetric. And so that could mean that the spin and the flavor and the space are all 3 symmetric, or one could be symmetric and the other 2 could be anti-symmetric. And you can see that there are lots and lots of combinations. Plus remember that we're talking about interchange of 3 different particles. So you got to talk about the symmetry with respect to the first 2, the symmetry with respect to the second 2, and the symmetry with respect to the first and third. My only point in bringing this up, we don't really have time to go into all the details. You can take a course in particle physics and see how that all goes. But my main point is that this is complicated. And it's not trivial business, but it is just application, I guess, of the same principles we've been talking about all semester. So next time, we're going to talk about decays, we're going to talk about scattering, and I hope to get to the Higgs boson and how it fits into all this mess. So we'll see you then. Okay guys, welcome back. It's lesson 38, part 3 of our 3-part series on the standard model of particle physics and quantum field theory. Let's just talk about what's left to do. Last time we discussed bound states, including positronium and charmonium, and a little bit about isotopic spin and pions and so on. Today I want to discuss decays and scattering, and that means basically Feynman diagrams. We're going to get into that a little bit. I had hoped to get the Higgs mechanism in today, but I just couldn't make it fit, so we're going to have to do that one next time. So sorry about that. Next time is just going to be fun stuff, and I don't know exactly what yet, but we'll find out on Tuesday. But for now, let's talk about these guys. Now there's two basic aspects to the problems of decay and scattering. One is the kinematic constraints that are placed on the process by basically relativity and Lorentz invariance of results and things like that. Because we're going to be doing sort of relativistic calculations, I'm going to try to simplify the math by letting c be equal to 1 most of the time. We're going to be using 4 vectors, which are 4 component objects. The time component is the energy, and the 3 spatial components are the momentum in the 3 space directions. The metric we're going to be using has a trace of -2. That means that the time comes in with a positive sign, and the 3 components of momentum come in with a minus sign when you're calculating inner products between momenta. And basically, everything that goes into and comes out of a reaction has to be a real particle. And what that means is it has to be on the mass shell. That's a technical lingo that basically means its energy is equal to its rest energy squared. Its energy squared is equal to its rest energy squared plus its momentum squared. So it would be like E squared equals m squared plus p squared in units where c is equal to 1. And all real particles have to have that property. What we're going to find out is that the internal particles that are involved in various reactions don't need to lie on the mass shell. In fact, generally they don't. In the end, energy and momentum have to be conserved. You may remember many lessons ago, 3 or 4 lessons ago, I talked about when you go to calculate the amplitude of something happening anywhere, you end up conserving momentum, and if you add up all the amplitudes of happening any when, you end up conserving energy. And or you could say that the 4 momentum is conserved. That's all 4 components, x, y, z, and time, and that includes energy and momentum conservation automatically. Now let's talk about Fermi's golden rule. We ran into this back when we were talking about the neutron capture reaction, and it goes back to time-dependent perturbation theory. It's actually a consequence of time-dependent perturbation theory, and we want to generalize this to the situations we're going to discuss today, particle decays and scattering. I pulled this page right out of the Particle Data Group handbook. I think this was maybe a couple years ago, but it hasn't changed much, I don't think. So it's basically, this is Fermi's golden rule for particle decays in a relativistic framework that we're going to be using today. And notice it looks a fair amount like the one we had before. The d capital phi is basically the phase space. It's the density of states in the phase space. The script m squared is the amplitude to go from the initial to the final setup squared. That sort of corresponds to our old VAB squared. There's a 2 pi to the 4th over 2m. The 2 pi to the 4th shows up because we're working in 4-dimensional space-time now, and m is basically the initial mass of the particle that's decaying. So anyway, that's the math. Now, the thing I want to focus on is that the only thing that isn't prescribed by the momentum of the outgoing particles here is the script m. The script m is the thing that we need to calculate with quantum mechanics. Everything else in this page is dictated just by the Lorentz invariance of the result and the requirement that energy and momentum be conserved, basically. So let's also look at they have a similar page, it's a couple of sections later in the handbook that describe cross-sections in the same sense. And basically, again, there are kinematic constraints that have to do with relativistic invariance, and then there's this script m thing, which is the quantum mechanical amplitude to go from the incoming particles to the outgoing particles. And that's really what I want to focus on today. Understand that you can, once you get that, you can just plug into these formulas for the kinematic aspects and then figure out the cross-section and the decay rate. So, moving ahead, how do we calculate that script m? That's the question. So, I want to do a little overview first, and then we'll get into the nitty-gritty. The first thing is, if you make a diagram that describes the process, whose cross-section or decay rate you want to compute, each vertex is going to get a factor that depends on the particles connected. So, for example, if you have a photon emitted by a charged particle, there's going to be a vertex factor which describes the amplitude of that process happening. So, in the case of a particle emitting a photon or absorbing a photon, it's going to be proportional to the charge, and it's also going to have things like h bar and c floating around in there. In units, when h bar and c is 1, basically it's just the size of the charge is the only thing that matters, and that's usually reflected in something called the fine structure constant. But if it's a different particle being emitted and a different particle doing the emission, I guess, then it'll have a different vertex factor. So if it's a gluon being emitted by a quark, that'll be a factor. If it's a weak boson being emitted by an up quark or something like that, it'll be a different factor. And the factors can get quite complicated depending on the complexity of the force that's involved. So we're going to do some simple examples today. Understand that it can get much more complicated. It also depends on the spin of both the particle that's emitted and the particle that's doing the emitting, and we'll see kind of how that works here in a little bit. Then, in addition to that, each internal line gets a propagator, and the propagators also depend on spin and mass. And the difference with the propagators, the internal lines, is that they don't need to be on a mass shell. They don't need to be on the energy shell. The energy squared doesn't have to equal the momentum squared plus the mass squared. These guys are never actually measured. They're used as a part of the calculation. You integrate over all possible momenta that could happen. And so they're called virtual particles. They're not real. So they don't have to behave like real particles. They can behave like virtual particles. But once they get to be external, so external lines that come in and external lines that leave the diagram correspond to real particles that you could actually measure in the laboratory. And so they are constrained to lie on the mass shell. Okay, and then finally we need to keep track of all the 2 pi's. We'll see how to do that in a minute, but there's a lot of them. So let's get to the nitty-gritty now. What does this actually work? Let's say we have a process where we have particles coming in and particles going out, and we want to compute the script m for some definite process. So the first thing we do is we label the momenta of all the things coming in and going out with p's, p1, p2, p3, up to pn. Okay? Then the internal momenta, this momenta of the particles that are inside the diagram that never actually leave, they don't come in from the outside and they don't go out to the outside, we're going to label those with q's just to have some way to tell the difference between the the incoming and outgoing and then the purely internal. Okay. For each vertex, we're going to put in the vertex factor. I already talked about that. For each internal line, we're going to put in the propagator. I already talked about that, so you get the idea what that means. And now for each vertex, we're going to include a delta function. Now, what does this delta function do? The notion, the k's could be either p's or q's, but the intent is that the 4 momentum coming into a vertex and the 4 momentum going out of a vertex have to be equal. That means if you add up the 4 momenta coming into any vertex, where the arrows are going away from the vertex, we count that as a negative, and it's kind of like the Kirchhoff's current law. You know, you could write it as the sum of the currents going into a junction is equal to 0, as long as you count the currents that are leaving the junction as negative. It's the same idea, except it's expressed in terms of 4 momentum, and since 4 momentum includes not only energy but also the 3 components of translational momentum, then this is the conservation of energy and momentum at every internal vertex. So, but remember, we're conserving energy and momentum at each vertex, but the particles involved in each vertex, if there are some internal particles, they don't necessarily behave like real particles. Their energy and momenta don't add up the same way they do if they were real particles. So it's mathematically conserving energy and momentum, but allowing for the particles involved to not behave like normal real particles. Then what we're going to do is integrate over all the internal momenta. So that means integrate over all possible energies, all possible x components of momentum, all possible y and z components of momentum for every internal particle in the diagram. So we're basically saying that any way it can possibly happen, we're going to let it happen, and we're going to calculate the amplitude for every possible way, and we're going to add all those amplitudes together to get the total amplitude. That's the idea. And then at the end, it turns out we're going to be left with a delta function that looks something like P1 plus P2 plus, and then minus P4, 5, up all the way up to n. Sort of looking at the diagram at the top, it would be plus P1 plus P2 plus P3 minus P4 minus P5 minus P up to P sub n. And notice all that does is it conserves the form momentum for the entire diagram. All the incoming momenta, four momenta, have to add up to the same thing as all the outgoing four momenta. So we're just going to throw that one away. And the reason we're going to throw it away is because that constraint is already satisfied with the kinematic part of Fermi's golden rule. We don't need it. And furthermore, we're calculating the script m here. Script m turns out to get squared when you go to calculate the decay rate or the scattering amplitude. And unfortunately, if we kept this delta function in, it would get squared and we'd be in trouble because delta functions squared are bad news. So you're going to just throw it out and you'll put it back in again when you calculate the actual scattering amplitude or the decay rate. And then finally we're going to multiply by I. We're going to check to see if we have more than one diagram that contributes to a process, and the diagrams differ only by the interchange of two fermions. Then we're going to add the two amplitudes together but with a minus sign. That takes care of the Pauli fact that when you swapped two fermions you need to include a minus sign. So, and I'm not using the creation annihilation operator formalism today, but if we did use that formalism, it would be taken care of by the commutation relations among the creation and annihilation operators for fermions. But we're just taking a different approach. In this case, we're going to just keep track of the signs by sort of manually noticing if the amplitudes that get added together correspond to simply swapping two fermions. Okay, so let's look at a simple example to kind of see how this works. I want to discuss electron and muon scattering. So here's the diagram. Notice that I've labeled the incoming momenta, the outgoing momenta, and the internal momentum. What do we have here? We have a muon coming in at the bottom, emitting or absorbing a photon. That photon is also emitted or absorbed by the electron that comes in on the top. And we want to use these rules to calculate the cross-section, or actually we're just going to calculate the script m of this process. And so let's get started. The first thing we want to do is to deal with that first vertex at the top. Now, the thing is, this is a relativistic calculation, and so we need to use the relativistic form of the wave function. It turns out the solution to the relativistic form of the wave function is something called a Dirac spinor. It's not the Schrödinger equation, it's the Dirac equation, and the solutions are four-component objects called spinors. And so psi1 is the momentum space wave function. We're in momentum space here because we're integrating over momentum, right? It's the momentum space wave function of the Dirac electron coming in on the top. So that's the psi. It's a four-component object. Then we've got the vertex factor, which in this case is just the electron
factor g times I, and notice there's a gamma to the mu. Now gamma is actually a 4x4 matrix, and not only that, it's a set of four 4x4 matrices. The set of four 4x4 matrices have to do with the Pauli matrices and the four components of the spinners and so on. So it's a little complicated, but the point is we've got the incoming electron wave function, we've got the outgoing electron wave function, and we've got the vertex factor. And the fact that these are 4x4 matrices and there's four of them and so on is just a technical complication, but the idea is pretty straightforward. Then we've got a similar oh, and don't forget the delta function. We need a delta function here to conserve momentum. So I'm taking P1 minus P3 minus Q and making a delta function with that as an argument, and that will require that P3 plus Q equals P1. So I'm thinking of Q as sort of leaving the top vertex and emitted by the top vertex and being absorbed by the bottom vertex. Of course, we're going to integrate over all Q's before we're done, so Q will be positive and negative, and so in the end, as long as I'm consistent between the two delta functions for the two vertices, everything will turn out okay. Now let's go to the bottom vertex. It's similar. We've got the wave function for the outgoing particle P4, we've got the vertex factor, and we've got the incoming muon psi 2 at P2, and oh, I didn't mention yet the S's. The S's count for the spins of the particles coming in and going out. In general, if we don't have polarized particles, we're going to have to average over the incoming spins and add for the outgoing spins. But basically all this stuff depends on the spin, and so we have to include that. And again, we get a delta function for this vertex. So there's a delta function, and this time notice I've got P2 plus Q equals P4, and that means that I'm thinking of the photon as being absorbed at this vertex and emitted at the top vertex. Of course, you could change the signs of the Q's to go the other way, but when you integrate over all Q, it doesn't matter, because Q is going to go positive and negative in any case. Now, the only thing we have left is the propagator of the photon. It turns out the propagator for a photon, which is a massless particle, is simple. It's just 1 over Q squared. And the G mu nu is the metric. So that's going to allow us to contract the gamma matrix from the upper vertex and the gamma matrix for the bottom vertex. When we calculate all those numbers, we will get a pure number. So when you plug all that in, okay, oh, and we're going to integrate over all Q. So when you plug all that in and do the integral, it turns out the delta function, let's look at the top delta function. It requires that P1, that Q equals P1 minus P3. So when I integrate over a delta function, that means I can simply replace Q with P1 minus P3, and it's all right. So that's a trivial integral. I can just stick it right in, and notice what I end up with is a number. It's a number because the thing in the brackets there on the bottom is the outgoing, it's the outgoing muon bar. Now a bar is kind of like a row version of the Dirac spinner, and psi 2 is the incoming mu. It's a column vector of the Dirac spinner, and that row and that column, when they multiply together, they make a number. But including the gamma matrix, the gamma is a 4x4, so what we get in that right-hand bracket is a number for every value of mu, and then the left-hand bracket, we get a number for every value of mu. Notice that the right-hand gamma now has a subscript. That's because the original gamma sub nu got contracted with the G mu nu from the propagator of the photon. So that's a lot of monkey business, and if you haven't done any relativistic math before, that may be all gobbledygook for you. What matters is that when you get done, when the smoke clears, this is a number. It's a number that depends on the value of P1 and P3, but it is just a pure number. There's no matrices, there's no vectors, nothing left here but the amplitude. So
the point is you can do the calculation. If you know how to fill in the blanks for the various vectors and matrices, you get a pure number. And once you have this number, of course, you can go back to Fermi's golden rule, stick it in, and calculate the cross-section for this process. And that's the idea. So if you don't feel like you have a great understanding of how this actually works, it's okay. I just wanted to give you a flavor of the kinds of things that go into the process. And the notion that we're really doing is adding up, that this diagram represents really a lot of different things that can happen physically, but we're adding up the amplitude of each of those things happening to get the overall amplitude for the diagram. Okay, let's look at another case that I promised I would look at. This is electron-positron annihilation. So it's a similar setup, a similar deal, except this time it's photons that are leaving and electrons and positrons that are coming in. So now I've got a phi bar that corresponds to the positron coming in. Notice that that's an electron line going backwards in time, so that's like a positron coming in. And then the epsilon has to do with the polarization of the photon. Photons are spin 1 objects. They have polarization, right or left circular polarization in this case. And so, and then the vertex factor, again, is the same thing we had before. It's the gamma. But this time the gamma is contracting a little differently. It's contracting against the polarization of the photon rather than contracting with the propagator of the, there's no photon propagator in this diagram because there's no virtual photon exchanged. These are both real photons, and so there's no photon propagator. So the contraction is a little different. The delta function works the same way, and then the bottom vertex, it's very similar to the top vertex, except this time we have an electron. That's a psi. So the psi's are the electrons and the phi's are the positrons, basically. They're different in the Dirac spinner. The psi's have large values on the top 2 components and the phi's have large values on the bottom 2 components. But anyway, those are all technicalities. We also get a delta function from that bottom vertex. And finally, there's a propagator in this diagram, but it's an electron propagator, not a photon propagator. So that's a little different. And notice that it's got a gamma matrix in it, but it contracts with the momentum of the internal virtual electron. So it's a little different technically. Also notice this propagator has mass, whereas the propagator for the photon doesn't. And so we end up with a little more complicated expression when the smoke clears. Again, you're going to integrate over all the internal momenta. And so that's how it works. And I want to define a shorthand. It's called slash notation. Basically, you'll notice that there are these gamma matrices. The epsilon for photon 3 contracts with the gamma for that vertex, and the epsilon for photon 4 contracts with the gamma for that vertex, and then the gamma and the internal momentum of the virtual electron contracts with its own gamma. And so we can save ourselves a lot of writing if we use that substitution, and then we end up with putting in the delta functions again. We end up with an amplitude that looks terrible. It's got slashed photon 3, it's got slashed photon 4, it's got slashed momentum 2 and slashed momentum 4. But those are basically just sums over various gamma matrices multiplied by components of various 4 vectors. So anyway, the point is this is again just a number. It's a number that depends on momentum 1 and momentum 2, but you can compute it. And momentum 4, I should say. So you can compute the thing, and it'll come out something. Then it turns out there's also another diagram. I'm not going to go through all the vertices and the propagator for this diagram, but I'll just point out what the answer turns out to be. It looks like this. And if you plug all that in and add them up and do the calculations of the various slashes and so on, astonishingly, what you get, if you consider only the singlet of the positron and the electron. So you force the positron and electron in a singlet state, which is a superposition of spin up and spin down, and you
plug all that in, it turns out you get minus 4 times GE squared. That's how the whole thing turns out. If you plug that back into the kinematic equation for the scattering cross-section, and you put in what GE is in terms of the fine structure constant, and I'm going to go ahead and put the H bars and the C's back in now so we can get the units right, you end up with a partial differential cross-section that just has the mass of the positron and the mass of the electron, and then their relative velocity v. So it's actually an astonishingly simple result. It's very complicated to get there, but once you get there, it's not too bad. Notice that there's no angular dependence left here. The cross-section is independent of angle, and that means that the total cross-section for this is simply 4 pi times that. And you might recognize this looks a little bit like the neutron capture cross-section we got back when we studied the formation of a deuteron, and it goes like 1 over v, just like that one did. You may also remember that there was a relationship between the lifetime, the rate at which the capture occurred, and the cross-section for the capture. In fact, I think we did this thing backwards. We used Fermi's golden rule to get the cross-section, or to get the rate of capture, and then we worked backwards to get the cross-section. But in this case, what we're going to do is use the cross-section to calculate the rate. I can just multiply by the density of the probability density, in this case, of the electron-positron pair, and multiply that by the velocity. Notice that sigma times velocity is independent of velocity, so that it doesn't matter how fast these guys are going. The rate turns out to be the same either way. What do I use for density? Well, I could just use the wave function evaluated at the origin, because that's where the two guys are coming into contact. And that turns out to be, remember, the wave function is nothing other than the hydrogenic wave function with the reduced mass of the proton and the positron. So that comes out pretty easy. And when you plug all that in, you get a lifetime, 1 over the decay rate, of about 1/8 of a nanosecond, which is what I mentioned the other day. And that's a triumph for all this crazy theory that you get an answer that corresponds to the actual lifetime of positronium. So there you have it. All right, next time, I promise, I'll talk about the Higgs and other fun stuff. We'll wrap up. This will be our last actual lesson for the semester. Lesson 40 is just going to be review and prep for the final exam. So we'll see you guys next time. Welcome back, guys. It's time for lesson 39, our very last lesson of the semester. This is basically just for fun. I wanted to make an attempt to describe for you guys the idea of the Higgs boson and just a tiny bit about string theory, just to kind of get you started. And so let's begin. First of all, we need to talk about Lagrangians. This monstrosity is the complete Lagrangian of the standard model, at least in one formulation. This is due to Veltman and Gutierrez. And Gutierrez just typed it up. Veltman, I think, describes it in his book on the standard model, and it doesn't appear in this form in the book, but the pieces of it are all there, and then Gutierrez sort of put it all into one monstrosity, one enormous Lagrangian. And it's pretty overwhelming, but so what good is it? What good is a Lagrangian? So the reason I put this up here is I wanted to talk about Lagrangians, and I wanted to point out that you could express the entire standard model in a single algebraic expression that describes the fields and the particles and their interactions and everything else. It evaluates to a number. This all the vector notation and so on, when you get done and the smoke clears, all you get is a number that depends on where you are and what the value of all the fields and so on are. So, why? Basically, the Lagrangian encapsulates everything we can know about what's going on. So, it's a very compact notation that contains a lot of information, and from it we can
figure out how to compute the probability of different kinds of events occurring. So that's why they're useful. It includes the strength of interactions and all the masses and charges and everything else. And basically, at the end of the day, all the fundamental theories that we have can be expressed using this formalism. And it turns out that not only that, but the Lagrangian has embedded in it all the conservation laws, because it turns out the symmetry of the Lagrangian dictates what's conserved and what's not. And that is also another interesting thing. Sometimes it's not what you'd expect. And finally, there's a famous quote by Einstein that says, you want to make things as simple as you can, but no simpler. As simpler as you can get away with, but if you make it too simple, you'll throw away something interesting. So let me remind you guys how Lagrangians work. Here's a classical physics Lagrangian. You might have run into this in your study of theoretical mechanics. It's the Lagrangian of a mass on a spring. So it's got two pieces. It's got the first piece, which is 1/2 mx dot squared. You probably recognize that as the kinetic energy of a mass that's moving around. X dot is just the velocity. And the next term is the potential energy, but it's negative. So it's the kinetic energy minus the potential energy. In this case, the potential energy is 1/2 kx squared, but as usual, I don't want to use k because I don't want you to get mixed up with some kind of a wave number. So we used m omega squared instead. And the idea is that from the Lagrangian, you can compute something that's called the action. And the action is simply the integral of the Lagrangian over some time interval. And when you integrate that, you get, again, a number. The Lagrangian evaluates to a number. It's the difference between the kinetic energy and the potential energy. When you integrate the Lagrangian over time, you get another number. It has units, excuse me, it's going to be units of energy times time. So that starts to smell a little bit like, well, it's an action. It's like momentum times distance or energy times time. That is the same units that h bar has, by the way. And so what's the deal? Well, the idea of using a classical Lagrangian is that the path that minimizes the action is the path that the particle actually follows. So the idea is to demand that the action be minimized, and that's written as delta S equals 0, where the delta here doesn't represent a change in S. What it means is small variations of the trajectory do not affect S. It's kind of like the condition to find a minimum of a function. You look for the place where the slope is 0, where changing x by a little bit doesn't affect y very much, or at all, where the slope goes to 0. So I guess technically this isn't looking for a minimum, it's looking for an extremum, but in the case that I'm giving you, it's actually a minimum. And you can show, and you probably did show when you took your analytical mechanics class, that the requirement that S be, that the variation in S be 0 gives rise to a differential equation that works for any Lagrangian. That is, the time derivative of the partial of the Lagrangian with respect to the x dot is equal to the space derivative of the Lagrangian with respect to x. And in this case, of course, dl dx dot, you can see right away, it's just going to be the momentum. It's mx dot. And the time derivative of the momentum, of course, is mx double dot. Then dl dx is going to be m omega squared x with a minus sign. Minus m omega squared x, of course, that's nothing other than the force. So in this example, you can see that this reduces to force on the right and rate of change in momentum on the left. And so what we have is simply Newton's second law. And you can see right away that that gives you a differential equation for the motion of a mass on a spring. So that's how Lagrangian works in the classical case of a particle moving around in a potential. The point is, from the Lagrangian, you can extract equations of motion. Now, how do we generalize this to a field? Okay, so a field exists at any point in time and space. So it's not just a coordinate, but it's actually a function of time and space. And this I'm describing in this slide a scalar field is just like a temperature or a mass density or something which just depends on, it's just a number which depends on time and space. You can also have, of course, vector fields like the vector potential or the electric field or the magnetic field or something like that. Or and we're going to talk about spinor fields and so on. But in this case, the funny notation there is the relativistic notation for a coordinate in space. The superscript, if it's a Greek letter, is going to go from the 0 to 4, where 0 is the time, and 1, 2, and 3 are x, y, and z, the spatial coordinates. So that's the meaning of that. Also, for derivatives, if you want to take the derivative with respect to a spatial or time coordinate, you get a subscript now, because notice the thing downstairs has a superscript, but when you divide by something with a superscript, you get a subscript. That's kind of the way it works. And so we'll either use partial with our subscript or we'll use comma. So comma also means differentiation. And the other thing is, if you want to evaluate a derivative with a superscript, that's a little bit different thing. You do the subscript version and then you use the metric to convert back to a superscript. So, and remember, the flat spacetime metric is just 1 for time and -1s for all the other spatial coordinates. And so all it does is flip the sign of the x, y, and z derivatives if you have the superscript version. And then what you do is express the action now. It used to be the integral of the Lagrangian over just time, but now we're doing a Lagrangian density. So in order to calculate the action with a Lagrangian density, you have to integrate over the volume of space and time. And the old Lagrangian depended on x and x dot, the coordinates and the time derivatives of the coordinates. This Lagrangian is going to depend on the field and the derivatives of the field. So comma sub nu means that. And if you play the same game, try to make the action have zero variation under fluctuations in the field. Again, you get a differential equation. It's a little bit like the differential equation for the simple classical Lagrangian, but in this case, it's got derivatives of the Lagrangian with respect to the field and with respect to the derivatives of the field. So that's kind of how that works. And I want to point out a couple things. The zero component of the derivative of phi is just d phi dt. The first spatial component is d phi dx, but the superscript version of d phi dt is still d phi dt because the metric is a 1 in the time component, but the superscript 1 derivative of phi is minus d phi dx, and of course that's also true of d phi dy and d phi dz. So if I come up with an expression like this, d mu phi d mu phi, the fact that the mu's are repeated, there's a convention that Einstein cooked up. When you have the same index upstairs and downstairs, that's a shorthand that means you're supposed to sum over all the indices. So if we let mu go from 0 to 1, so we're going to do the time and the space part, this is shorthand for the expression I have there. It's the time derivative squared minus the space derivative squared. And that's the minus comes from the metric, and you can see that that gives you a scalar. And it's a scalar that's the difference between the time and space derivatives of the field squared. Okay, so I want to start with those pieces, and then let's do a simple example that is a Lagrangian that has the thing we just described, plus a term that's proportional to phi squared. Notice that it's like a potential energy term, but it goes like phi squared. In fact, it may remind you a little bit of the simple harmonic oscillator. But let's then write out the Lagrangian explicitly in terms of the time and space derivatives. It looks like this. And then use the Euler equation, basically the differential equation that minimizes the action using this Lagrangian density, and see what we get. First, it's the derivative of the Lagrangian density with respect to the time derivative of phi. Well, the time derivative of phi comes in squared, so if we take the derivative of L with respect to that, we're going to get d phi dt. That's the same thing as d super phi, which is the same as d sub phi since they're equal to each other. But I want to write it as d super phi for now, because if you take the derivative with respect to the space component, you'll notice that you get minus d phi dx, but that's the same as phi super 1, or partial super 1 phi. So both of these look like partial super, and what that means is, in general, I can write dl d phi comma mu as partial super phi. In other words, this is a shorthand. It comes out the same for both the time and the space components. That's the idea. Now, let's take what we got there and go ahead and rewrite it. So you can see that if I take the mu derivative of dl d phi comma mu, it's going to be the second derivative of phi with respect to time minus the second derivative of phi with respect to x. In other words, I'm using the Einstein summation convention to add those pieces together, and you can see that that's how it comes out. Starting to look a little bit like a wave equation. Now what about the right-hand side? I just want to take dl d phi. The only term that has just phi in it is that mass term. And so we put that in, and we get an expression that looks a little bit like a wave equation, shockingly. And let's look at the pieces. Notice that in our conventional quantum mechanics we've been doing, the Schrodinger equation, that d phi dt kind of looks like an energy. It's minus an energy, squared in this case, if you take the second derivative. And then the second derivative with respect to space looks like a momentum squared. And the last term is a mass term. If we work in units where c is 1 and h bar is 1, which is often convenient, then you recognize here the relativistic relationship between energy, momentum, and mass. And so what we have here is a wave equation that describes a relativistic particle of mass m. This is the so-called Klein-Gordon equation. Now, the other thing is that because phi is a simple scalar, it turns out that it represents a particle with spin 0. And the point is, the whole point of that exercise was to notice that if you start with a free field Lagrangian of a particle, you end up with a wave equation, in this case an equation of motion, that tells you how the field behaves. That's the idea. Now this was the Lagrangian of a spin 0 particle of mass m. Just for fun, I want to point out some other Lagrangians that also lead to well-known equations, and I'm just going to tell you what they are. We're not going to try to do a lot with them. The first is a spin 1 vector field. It's called the Praca Lagrangian, and it produces equations of motion for a vector field with a spin of 1. And then the Dirac Lagrangian, if you apply the minimization or the extremation of the action with this guy, out pops the Dirac equation, which is sort of, so both of these guys give you wave equations that are appropriate for particles of different spin, and the Dirac equation, of course, is the relativistically correct equation that describes particles of spin 1/2. Okay, let's look at the Dirac Lagrangian a little bit, and I want to describe a kind of basically it's the way that conservation laws are related to symmetries in the Lagrangian. At least this is part of the story. There's a great deal of literature on this relationship, the fact that momentum conservation and energy conservation and charge conservation can all be derived through symmetries from the Lagrangian. But here's a simple transformation you can imagine. Let's see what happens if we transform the wave function everywhere by multiplying by a phase factor. This is called a global
phase transformation. And the thing you have to realize is that the psi bars in this expression are kind of like complex conjugate. They're sort of spinor equivalents of complex conjugates. And they get, if you multiply psi everywhere by e to the plus I theta, you're going to multiply psi bar everywhere by e to the minus I theta. And you'll notice that psi and psi bar always show up in pairs. There is a spatial derivative on one of the psi's, but if theta is just a number, the spatial derivative doesn't do anything, and you see that the Dirac-Lagrangian is invariant under this transformation. So this is called a global phase transformation because we're multiplying the wave function, we're multiplying the field everywhere by a constant phase. Now what happens if we try to do the same trick, but this time we use a local phase? What that means is that at every point in space we're allowed to use a different value of theta. Theta can be now a function of position. Well, if we do that, you see right away there's trouble, because the first thing that the Dirac-Lagrangian has in it is a derivative with respect to x mu, and you know if you take the derivative with respect to x mu, you're going to get a term that's got the derivative of theta with respect to x mu, and that thing is not going to be invariant. In other words, the Lagrangian is not invariant under the influence of a local phase transformation. So that's unfortunate. That means the Lagrangian goes to the Lagrangian minus some junk. But here's an idea. What if we invented a new field? We define gamma to be proportional to theta, and we define a new field which transforms under a local phase transformation, a local phase factor. It transforms in such a way that you have to add a piece to it, the gradient of a scalar, and mix that in the Lagrangian. In other words, put in the Lagrangian a term that's got this new field in it in such a way that when you make a local phase transformation, the extra term that shows up from the Dirac-Lagrangian is absorbed by the extra term that shows up from this new field Lagrangian. So that's what we're going to do. And but once we create this new field, this sort of field to pick up the slop that comes out as a consequence of the local gauge transformation, it's going to need a free Lagrangian of its own. And so in this case we could talk about it's a vector field, and so we could add the Praca Lagrangian. But here's the trouble. While the first part of the Praca Lagrangian, the part that has to do with the differences in the derivatives of the field, it isn't unaffected by this additional piece. The second part that has a nu, a mu, it turns out it is affected, and so we can't keep it. That means that this term, which has mass, has to be 0. So what we discovered is that in order to keep the Lagrangian locally gauge invariant, we can do it by adding a spin 1 field into the thing that transforms under the phase transformation with a kind of a gauge transformation, the same kind of gauge transformation we talked about before. Then everything will work out so long as this new vector field doesn't have any mass. So the full Lagrangian now that is locally gauge invariant, or locally phase invariant, I guess, is going to look something like this. We've got the original Dirac-Lagrangian that describes free electrons and positrons. We've got, and that could be, you could think of that as a Feynman diagram, which is a straight line. We've got the this new field, which turns out to be, you can guess already, I suppose, it's the vector potential. It's the vector potential field, and that describes photons. Photons are basically spin 1 particles with no mass. Okay, and what's the thing in between? Oh, of course, photons are the squiggly lines. What's the thing in between?
it's the interaction between the spin 1/2 particles and the photons. And so that's our interaction term, and that came for free just by trying to make the theory, the Lagrangian, independent of a local phase variation. That's the idea. So let's think about that. In order to make the thing invariant, we had to add a new field that slopped up the extra term, and that new field turns out to be a spin 1 particle, and it had to have no mass because the mass term would have spoiled the gauge invariance that we got, that we started out to produce. So interesting. Okay, let's march ahead. I know this is very quick and I've left out details, but I just wanted to get the idea out there. Now, here's the Lagrangian density we used for our spin 0 scalar field. And I wanted to point out, and I've already said it basically, but the first term acts kind of like a kinetic energy. The second term acts a little bit like a potential energy. And notice it's the second term that has the mass. The mass came out of the second term in the Lagrangian density. And by the way, this, if you pushed on this same theory, the force, if this field carried a force, the force would behave like the Yukawa potential. This is basically the same field we talked about a few lessons ago, and out came the Yukawa potential. So it's the same idea, but the mass determines the distance over which that interaction is effective. Let's imagine, here, start with a new Lagrangian. This one looks a little bit similar, but notice the mass part is positive, and then it's got this other term that goes like phi to the fourth. What we just learned about Lagrangians is that the phi squared term sort of looks like the particle moving along, and the phi to the fourth, if you remember, the interaction was psi times a mu. So, and the Feynman diagram had three pieces: the electron coming in, the electron going out, and the photon going out. And it turns out there's a connection between the structure of the Lagrangian and terms that can appear in the Feynman diagram. So this phi to the fourth looks like a Feynman diagram where you've got phi coming in, you've got four phi's connected together. So this looks like a self-interaction term of some kind, which is mildly interesting. But what I want to point out, that corresponds to a potential energy. Remember that Lagrangian is kinetic energy minus potential energy. So the structure of this Lagrangian is that it's got a potential energy that goes like minus 1/2 m squared phi squared plus 1/4 L squared phi to the fourth. And let's think about what that looks like. It's kind of a weird mass term because the mass terms we've been dealing with come in with a minus sign. This one has a plus sign in the Lagrangian, which means the mass is somehow imaginary. And if you graph the potential energy as a function of phi, you'll see what the trouble is. The trouble is that the slope of the potential does go to 0 at the origin, but it's not stable. The mass squared is negative. On the other hand, there are places in the potential where there are minima, and you can see where they are. You set the derivative of u with respect to phi equal to 0, you solve for phi, and you get two places where phi has a minimum, and it turns out to be plus or minus m over L. And the question is, what do we make of that? Well, one way to make some sense of it is to let's expand the field around the minima. So we can write eta as phi minus its minimum value, phi minus the value it has when it's a minimum, and then put that back into the potential, put that back into the Lagrangian, and see what comes out. Notice that now, as in contrast to what we had before, now we have a mass term that has the proper sign. It's minus m squared eta. So it looks like this describes particles that have a mass of the square root of 2 times m. A little bit heavier, but at least they're real. At least they're real. Also notice that in the eta field, we've got an eta cubed term, and that would correspond to a new Feynman diagram that didn't exist in the old one. just because we're expanding the field about a different place. So this also relates to symmetry breaking. There's another field we could study where you've got a real part and an imaginary part. It would be a complex scalar field. And in that case, everything basically is the same except the phi has a real part and an imaginary part. And so this diagram can be rotated, revolved about the central axis, and it becomes a sort of a three-dimensional picture with a symmetry about the axis, but you've got a continuous set of minimum values. And when you pick one, that process of picking a particular place to expand the field is called symmetry breaking. In other words, you got to choose a point where you're going to expand the field about and proceed from there, and that process, that's where the term symmetry breaking comes from. You can see, just looking at it, that expanding the field about the minimum, the symmetry that was there at the beginning about the origin is no longer there. So just a little lingo, kind of brighten your day. So the point is, the mass of the field expanded about the minimum is related to the curvature of the potential about that point. And the other thing to notice is that now the new ground state of the eta field is also going to be the lowest energy state of the phi field, but it's not at a place where phi is 0. In other words, phi has a non-zero value even in its vacuum or ground state. So the phi field exists. What I want to point out is now if we imagine going back to our another Lagrangian, which is kind of a superposition. Imagine we had a Lagrangian that described a free massless field. Notice there's no mass term. Then we have another field that has mass, but a non-zero ground state. So the chi field here is some kind of a field that has a non-zero ground state, and it's got the symmetry breaking and all that stuff. And there's an interaction between the chi field and the phi field. This interaction term effectively behaves like a mass. Because the chi field is non-zero in vacuum, it means that even in the vacuum, there's a term here that takes the place of a mass term. And notice that there's a proportionality between this term and what would normally be called mass, and it has to do with the strength of the interaction between the chi field and the phi field. So there you have it. That's also, I forgot to mention it on the slide. I don't want to leave it out. If you go back to the slide that described the interaction between the Dirac field and the photon field, you'll notice that it was proportional to the charge. That proportionality constant has to do with the strength of interaction between the spin 1/2 particles and the photons. The g here plays exactly the same role. So the g would be something like the mass charge, but it's just a number which represents how strongly do the phis and the chis interact with each other. Okay, now on to strings. This is going to be really quick because I know I'm taking a long time. First of all, I want to describe Einstein's theory. I want to describe the extension to Einstein's theory called the Kaluza-Klein theory. And then we're just going to describe the string action. In other words, what does the action look like for strings? And let's march ahead. First, general relativity. The idea of general relativity is that matter and energy distort space-time. Matter and energy tell space-time how to curve. On the other hand, space-time tells matter how to move. Matter moves through space-time in such a way that minimizes the space-time distance that it goes, okay? And that also gives you a hint about how you could formulate a space-time Lagrangian. The bottom line is gravity is a geometrical effect. Geometrical in the sense that it has to do with the geometry of space and time itself. So what's the idea of quantum gravity? To generate a theory of quantum gravity, it turns out the field is the space-time metric. In other words, the thing that corresponds to the field is actually the metric that describes the geometry of space and time. The Lagrangian depends on the space-time metric, and the Einstein-Hilbert action, which is what we're going to get to here in a minute, it has problems. It's worse than the Yang-Mills theory, which describes the color Lagrangian. It's not renormalizable, and it doesn't terminate. You just have to keep going on and on and on. And so that's the trouble, and that's part of the reason why string theory was developed. But there was another reason. It had to do with this Kaluza-Klein extension. So this is the metric that describes general relativity. It's I'm not saying that right. This is the action that describes general relativity. If you apply the minimization procedure to this action, out come Einstein's equations. It has two pieces. One is the determinant of the space-time metric, and the other is the Ricci scalar. What is a Ricci scalar? Well, it has to do with the Christoffel symbols, which are related to derivatives of the space-time metric. And they basically tell you how to take derivatives in space-time when space-time is curved. So how do you take complete derivatives of things? You need to take into account the derivatives of the metric, is what it boils down to. From the Christoffel symbols, you can generate something called the Riemann curvature tensor. It's a four-component object that depends on the derivatives of the Christoffel symbols and their products. You can see how it's formed here. You can contract the Riemann space-time curvature tensor in two indices and generate what's called the Ricci tensor. It's a two-component object that describes the curvature of space-time. And from that you can contract further, you can contract further and get a scalar. This is the Ricci scalar. Wow, it's complicated. But anyway, if you minimize this action, the differential equation that you get is basically the Einstein equation. Now, Kaluza and Klein developed a model where you extend space-time to a fifth dimension. So you've got time, 3 dimensions of space, and then another dimension that's somehow hidden. You could think of it as kind of a loop that goes around and meets itself, a rolled-up dimension, a cylinder of some kind. What I want to do is to integrate over that last dimension and see what that tells us. Well, if you integrate over the last dimension, you're going to end up multiplying by a, and so you see that if you just integrate over that one dimension, you're going to get back to the original metric. And so if you embed in the 5-dimensional metric and the 4-dimensional metric of Einstein's theory of relativity, you will recover Einstein's theory of relativity if you simply integrate the action over the last dimension. But that's not all, because you can show that if the deviation of the metric from the flat spacetime metric is small, in other words, if HAB is small, then shifting all the positions in 5 dimensions by a little bit affects the perturbative part of the metric by amounts that are proportional to the derivative of the shift with respect to the different directions. Okay. Now, if you make the 4 spacetime components of the shift 0, in other words, you don't shift in real time or real space, or the conventional 4 dimensions of space and time, and you make the shift in the 5th dimension independent of the value of the 5th dimension coordinate. In other words, if the partial with respect to x5 of the 5th component of the shift is 0, then it turns out that the 4 components of the metric don't change, and the 5th component of the metric in the 5 direction doesn't change. However, you will get a shift in the 0 to 4 components of the 5th element of the metric. And so you get a shift that only affects the last dimension in terms of its effect on the metric. But if you identify that vector as a vector a mu, and you identify a E5 as the scalar gamma, you get exactly the same result as the gauge shift that we did back on the Dirac equation. In other words, this behaves just like a vector field from E and M. So the idea is that if you add a fifth dimension, that you can get out of that fifth dimension a force that's not gravity, but it behaves like electricity and magnetism. And you can also show that it's possible to extend to higher dimensions and get something like a Yang-Mills theory. Now this is all not right, because you end up predicting other things that don't actually happen, but one of the consequences is a force like electromagnetism. And the idea of string theory, at least part of the idea, is to extend the dimensions of space and time to incorporate the properties of all the other forces of nature. So let's talk about that. Basically, this is the action of general relativity. In string theory, you basically come up with an action of strings. So this is an action of a world sheet. A world sheet is kind of like a world line, except it's a two-dimensional surface in a higher dimensional space. In fact, it could be a 9-dimensional surface in a 10-dimensional space. But a couple of things that does, because we're converting world lines to world sheets, there are no longer any point interactions. And you can show that a lot of the trouble with conventional quantum field theory, with the standard model, is that when we model interactions as point interactions, it leads to infinities. And the hope is that by changing to world sheets and strings that interact over an extended space, that will eliminate some of those infinities. And that is a hope of string theory. The other thing is different string modes, vibrations of strings in different modes in these dimensions, higher dimensions, lead to different energies and then different string properties. So in the current iteration of string theory, it's basically something like a 10-dimensional theory, and those 10 dimensions, the ones you can't see, are sort of wrapped up, curled up tightly in such a way that they don't appear in our everyday lives, and they fit into what are called Calabi-Yau spaces on very tiny scales, and the strings vibrate and have different properties depending on the modes of vibration, is the idea. All string theories have a graviton and other particles, but there's no single string theory yet that predicts the standard model. So interesting. I know this has all been very vague, but it's interesting business, and I hope you decide to pursue it and kind of learn a little bit about it. We'll talk to you guys soon.